The universe is an enigmatic and boundless expanse, brimming with countless mysteries that continue to baffle and intrigue us. The deeper we probe into the cosmos, the more questions arise. Questions that seem to stretch beyond the limits of our current understanding. What is the invisible force that binds galaxies together? Why do some stars appear to defy the laws of physics? These profound inquiries fuel the drive to explore the most puzzling phenomena lurking within the vastness of space. Join us as we embark on a journey to uncover the greatest unsolved mysteries that the universe has to offer. One such mystery is the phenomenon known as the axis of evil. This curious feature was first identified in the cosmic microwave background, CMB radiation, the faint afterglow of the Big Bang, which serves as a snapshot of the universe's infancy. The axis of evil refers to a peculiar alignment of large-scale structures in the universe that seems to point toward a specific direction in the sky. This alignment has captivated cosmologists and ignited heated debates as they attempt to understand what it means for our comprehension of the universe's structure and origins. Under typical circumstances, the CMB radiation is expected to be uniformly distributed across the sky, reflecting the isotropic nature of the early universe, essentially the idea that the universe looked the same in all directions at its inception. However, what has puzzled researchers is the discovery of anisotropies, regions of irregularity in the CMB, appearing to align with the orientation of our solar system and the Milky Way galaxy. This unexpected alignment raises profound questions. Could it be a mere statistical anomaly, a result of the limited volume of the universe we are able to observe? Or might it point to a deeper, as yet undiscovered structure that extends beyond our immediate cosmic neighborhood, perhaps reflecting an influence from the early universe, or even suggesting the presence of forces we do not yet fully grasp? Despite years of extensive study and investigation, the origin of the axis of evil remains an unresolved mystery. Some scientists argue that this alignment could simply be a product of observational biases, while others propose it could indicate new physics at play on cosmological scales. As technology advances, offering us more sophisticated tools for observation, the search for answers to this cosmic puzzle continues. Unraveling the true nature of the axis of evil could revolutionize our understanding of the universe and the forces that shaped its formation. Another perplexing anomaly in the cosmos is the strange cold spot in the universe, once simply known as the cold spot. This is a region of the cosmic microwave background that appears unusually colder than its surrounding areas, a discrepancy that has puzzled astronomers and astrophysicists since its discovery. Spanning roughly 10 degrees in the sky, this cold spot has raised a host of questions regarding its origins and the implications it might hold for our comprehension of the universe's larger structure. One prevailing theory suggests that the cold spot may be the result of a supervoid, an immense, nearly empty region of space that contains far fewer galaxies and matter than the surrounding areas. If this cold spot coincides with such a void, the diminished density of matter could lead to reduced gravitational effects. This, in turn, might cause the cosmic microwave background radiation to lose energy as it traverses the void, resulting in the cooler temperature we observe when the radiation finally reaches us. Alternatively, the cold spot could be a remnant of fluctuations in matter density that occurred in the early universe. This concept aligns with the theory of cosmic inflation, a rapid expansion of space that occurred shortly after the Big Bang, which could have created regions of lower density and temperature. The cold spot, in this case, could be a lingering imprint of these quantum fluctuations that occurred in the very first moments of the universe's existence. Some researchers entertain even more radical possibilities, including the notion that the cold spot could be a consequence of interactions with other universes. This hypothesis suggests that our universe may not be alone, and that the cold spot could be evidence of a larger multiversal structure. If this is the case, it would imply that our universe is just one of many, each with its own unique properties and dynamics. While these ideas push the boundaries of conventional scientific thought, they reflect the vast potential for new discoveries that could fundamentally alter our understanding of reality itself. Despite the many competing theories, the true nature of the cold spot remains an enigma, one that continues to captivate scientists and provoke further investigation. The answers we uncover may not only reveal new insights into the origins of our universe, but could also provide us with a glimpse into the very fabric of space and time, challenging the very laws that govern our understanding of the cosmos. Finally, we turn our attention to the vast cosmic voids, enormous, nearly empty regions scattered throughout the universe, often containing far fewer galaxies than their surrounding environments. These voids, some stretching across hundreds of millions of light years, are key to understanding the large-scale structure of the cosmos. While their sheer size and emptiness might suggest a lack of significance, they actually offer valuable insights into the processes that have shaped the universe since its very beginning. The formation of cosmic voids is intricately linked to the universe's evolution following the Big Bang. In the early stages of the cosmos, matter was distributed relatively uniformly, but as the universe expanded and cooled, slight fluctuations in density began to emerge. Over time, these fluctuations became more pronounced, creating regions where galaxies and other cosmic structures formed, while other areas remained devoid of matter, creating what we now recognize as voids. The study of these voids not only sheds light on the forces that have shaped the universe's structure, but also offers clues about the nature of dark matter and dark energy, mysterious entities that continue to elude direct observation. As our technology and observational tools continue to improve, the investigation into these voids and their role in the universe's formation is bound to deepen. Understanding their origins and how they interact with the surrounding galaxies and clusters could offer groundbreaking insights into the very nature of space, time, and the forces that govern our universe. Each of these cosmic anomalies, the axis of evil, the cold spot, and the vast voids, challenges our understanding of the universe and beckons us to probe deeper. They remind us that despite the tremendous strides we've made in our exploration of the cosmos, the universe is still full of mysteries waiting to be unraveled. The more we discover, the more we realize how much there is left to learn, an endless journey of curiosity and discovery that may one day reveal the ultimate truths of our existence. Quantum fluctuations, though minute, set the stage for the universe's grand evolution. As the cosmos expanded and cooled, these fluctuations in density began to cause small irregularities, subtly altering the fabric of space. Gravity, the fundamental force that governs the motion of matter, acted on these early density anomalies, gradually pulling matter toward denser regions. Over eons, this process led to the formation of galaxies and galaxy clusters, while the less dense regions evolved into vast voids, empty expanses of space where matter seemed to be nearly absent. As the universe continues its expansion, these voids undergo further transformation. Matter from surrounding regions continues to fall into the more densely packed areas, causing the voids to grow even larger. This intricate and ongoing process contributes to the cosmic structure known as the cosmic web, a vast network of interconnected galaxies, clusters, and empty spaces that forms the framework of the universe on the grandest scales. These galactic filaments, which connect the densest regions of the universe, trace a delicate, web-like pattern across the cosmos. The cosmic web is not just a marvel in itself, but it provides profound insights into the larger-scale distribution of matter. While voids may seem empty at first glance, they are far from devoid of interest. These regions, though lacking the dense concentrations of galaxies, still host pockets of intergalactic matter and even dwarf galaxies, small galaxies that exist in the outermost stretches of space. These voids, far from being unremarkable, offer a unique lens through which astronomers study the forces that drive the universe's expansion, particularly the mysterious and elusive force known as dark energy. The presence, size, and dynamic behavior of cosmic voids challenge our understanding of the universe's evolution and deepen our appreciation for the complexities of the universe's architecture. What's equally intriguing is how the filaments that form the cosmic web are not just static structures, they are in constant motion. These filaments serve as cosmic highways linking galaxies and clusters, allowing matter, gas, stars, and galaxies themselves to flow from one region of space to another. The formation of these filaments can be traced back to the early universe, where gravitational forces, influenced by dark matter and ordinary baryonic matter, led to the clumping and alignment of galaxies along these invisible threads. Over time, these filaments grew rich in galaxies, and as galaxies merged and interacted, they became more densely concentrated along these paths, further reinforcing the web structure. Remarkably, these filaments are not merely roads for galaxies, but also active sites of cosmic development. The interaction between galaxies, the streams of gas, and ongoing star formation within these filaments suggests that they are far from inert. The gas and dust within these structures reveal more about the chemical composition of the universe, providing astronomers with valuable information about the processes shaping cosmic evolution. By studying the diffusion of elements like hydrogen along these filaments, scientists can glean details about the universe's content, the distribution of matter, and the cosmic forces that have shaped its present state. At a broader scale, the cosmic web is a testament to the gravitational dynamics that govern the universe. These filaments are not random. They form due to the intricate interplay of forces, where dark matter, through its gravitational influence, shapes the very structure of the universe itself. Understanding the origins of these filaments gives us critical insights into how the universe developed over time, revealing the ongoing tug-of-war between matter, energy, and the mysterious forces that shape them. The cosmic web is a powerful reminder of how the universe, in all its vastness, is intricately connected and constantly evolving. Moving from the filaments to the cosmic structures that influence the motion of galaxies brings us to a fascinating anomaly, the Great Attractor. Located in the direction of the constellation Centaurus, this gravitational anomaly exerts a powerful pull on the galaxies of our local supercluster, the Laniakea supercluster, including our very own Milky Way. This force draws galaxies toward itself at incredible speeds, revealing the presence of a massive yet invisible concentration of matter. The Great Attractor is a gravitational focal point believed to be home to thousands of galaxies and substantial amounts of dark matter, which, though undetectable by conventional means, can be inferred through its gravitational effects on visible matter. The Great Attractor remains one of the most mysterious and elusive features of the universe, its true nature obscured by the dense gas and dust of the Milky Way's galactic plane, which makes direct observation difficult. Despite these observational challenges, studies suggest that the Great Attractor contains a mass equivalent to approximately 10 million billion times that of the Sun, an incomprehensible amount of matter, which provides the necessary gravitational influence to shape the flow of galaxies in our region. This gravitational pull extends beyond the Great Attractor itself, extending to larger cosmic structures like the Shapley supercluster, which may also be contributing to the movement of galaxies in our neighborhood. These enormous structures create a network of gravitational forces that orchestrate the motion of galaxy clusters across vast distances, weaving the universe into a cosmic web of connected forces. The influence of the Great Attractor highlights the complex and interconnected nature of the universe. It offers a tangible example of how gravity, on the largest scales, directs the motion of galaxies, and how our own galaxy is subject to forces that stretch across millions of light years. The existence of such a gravitational anomaly underscores the role that dark matter plays in shaping the universe's structure and evolution, and how much remains to be discovered about the invisible forces at work. Dark matter itself is a key player in the cosmic drama. Although it does not emit, absorb, or reflect light, and is thus invisible, its presence is undeniable. Dark matter makes up about 25% of the universe's total mass and plays a crucial role in the formation of galaxies, clusters, and the large-scale structure we observe today. The first evidence of dark matter's existence came from observations of galaxies and galaxy clusters, where the visible mass alone was insufficient to explain the observed gravitational forces. The true scale of dark matter became apparent when studying the rotation curves of galaxies. According to traditional physics, stars located farther from the galactic center should orbit more slowly than those near the core. However, observations show that stars maintain high velocities even at significant distances from the center of galaxies. This anomaly suggests the presence of an unseen mass which provides the extra gravitational pull needed to keep galaxies intact. Dark matter's role extends beyond individual galaxies. During the early stages of the universe, it provided the gravitational scaffolding around which visible matter gathered, eventually forming galaxies and clusters. As the universe expanded and cooled, dark matter's influence shaped the cosmic landscape, causing galaxies to form along the dark matter's gravitational threads. The intricate interplay of dark matter, visible matter, and gravity continues to shape the structure of the universe today, guiding the evolution of the cosmic web and determining how galaxies and clusters are distributed across the universe's vast expanse. In conclusion, the universe's structure is far from random. It is a dynamic, evolving masterpiece shaped by the interplay of gravity, dark matter, and visible matter. From the formation of cosmic voids to the growth of galactic filaments, and from the gravitational pull of the great attractor to the unseen influence of dark matter, each element of this vast network plays a role in shaping the universe's architecture. As we continue to explore the cosmos, we uncover more about how the universe evolved and how the fundamental forces of nature work together to create the magnificent and intricate structure we observe today. The presence of dark matter is absolutely essential in shaping the cosmic web that we observe across the universe. Despite its undeniable influence on the fabric of the cosmos, dark matter remains one of the most elusive and enigmatic substances known to science. While its existence is critical in the formation and structure of galaxies and other cosmic phenomena, we have yet to fully identify what dark matter actually is. Several theories have emerged in the search for an explanation, with leading candidates such as weakly interacting massive particles, WIMPs, and axions offering intriguing possibilities. However, the quest to understand dark matter is ongoing, with researchers tirelessly pushing the boundaries of science to uncover its true nature. Dark matter is responsible for the gravitational effects that we observe in galaxies, galaxy clusters, and the cosmic web structure itself, yet it cannot be detected through conventional means. Its presence is inferred from its gravitational interactions, but its exact makeup remains a mystery. The importance of understanding dark matter is underscored by the fact that it plays a significant role in the evolution and history of the universe, from the formation of galaxies to the structure of the cosmic microwave background radiation. In many ways, the universe as we know it would be entirely different without dark matter. One of the leading theories in contemporary astrophysics is that dark matter could be composed of particles that have yet to be discovered. These particles would account for the gravitational effects of dark matter while remaining invisible to ordinary detection methods. This hypothesis has led to an exciting area of research that, if successful, could offer profound insights into the fundamental nature of the cosmos. Some of the most discussed candidates include weakly interacting massive particles, or WIMPs. WIMPs are hypothetical particles predicted by extensions of the standard model of particle physics. These particles are theorized to interact only via the weak nuclear force, a force that is much weaker than the electromagnetic and strong forces that govern the behavior of normal matter. This makes them incredibly difficult to detect directly. Despite decades of experimentation using some of the most advanced scientific techniques, no direct evidence of WIMPs has yet been found. Researchers continue to employ underground laboratories, particle accelerators, and other highly sensitive instruments in their search, hoping that any interaction between WIMPs and regular matter will reveal itself in ways that are yet to be discovered. If WIMPs are ever detected, it would not only confirm their role in the dark matter puzzle, but would also open up a new chapter in our understanding of particle physics. Another intriguing possibility involves axions, hypothetical lightweight particles that arise from theories attempting to unify the fundamental forces of nature. Axions are thought to interact even more weakly with matter than WIMPs, making them another difficult-to-detect candidate for dark matter. If axions exist, they could form a cosmic background that permeates the universe, contributing to the gravitational effects attributed to dark matter. Their potential role in the dark matter equation represents an exciting area of exploration. other more exotic candidates have also been proposed, including sterile neutrinos and primordial black holes. Sterile neutrinos are theoretical particles that, like axions and WIMPs, are predicted to interact minimally with ordinary matter, making them another viable candidate for dark matter. Primordial black holes, on the other hand, are black holes that could have formed in the very early universe and might contribute to the dark matter population. Each of these potential candidates presents unique behaviors and properties that could explain the observed phenomena associated with dark matter. The pursuit of these elusive particles has led to vast research efforts involving both experimental and observational techniques. Underground laboratories, high-energy particle colliders, and advanced telescopic observations are just some of the tools being used to search for clues. The discovery of any one of these particles would not only confirm their involvement in dark matter, but would also lead to groundbreaking advancements in our understanding of physics, opening doors to new discoveries about the universe's fundamental composition. In parallel to the mystery of dark matter, another major force remains at the forefront of cosmological research: dark energy. This mysterious force is thought to be responsible for the accelerated expansion of the universe, a phenomenon first observed in the late 1990s. During this period, astronomers studying distant supernovae made an unexpected discovery. These cosmic explosions were much farther away than previously anticipated. Instead of slowing down as the universe expanded, the rate of expansion appeared to be accelerating, suggesting the presence of a repulsive force that was driving this acceleration. Dark energy is believed to make up about 70% of the total energy density of the universe, and it is thought to dominate the universe's overall dynamics. Unlike matter, which exerts a gravitational pull, dark energy exerts a form of negative pressure. This negative pressure pushes matter apart, counteracting the attractive force of gravity. As the universe expands, the effect of dark energy increases, which leads to an ever-accelerating rate of expansion. This process continues to unfold, and the acceleration is expected to continue into the far future. One of the most well-known models that describes dark energy is the cosmological constant, introduced by Albert Einstein. This constant suggests that dark energy is a fundamental property of space itself. As the universe expands and more space is created, the overall effect of dark energy grows stronger. This model fits well with many observations, but it also leaves important questions unanswered. For example, why does dark energy possess the specific properties that it does? And why does it have the effects it does on the universe? Alternative theories about dark energy have also emerged, including dynamic models where dark energy evolves over time. These models suggest that dark energy's influence could change as the universe ages, potentially altering the ultimate fate of the universe. In the distant future, the properties of dark energy might evolve in such a way that the universe's expansion could take on entirely new dynamics. Understanding dark energy is one of the most significant challenges in modern cosmology, as its effects on the structure and future of the universe challenge our fundamental understanding of gravity and the very fabric of space-time. Through continued observations and experiments, scientists are steadily working to unravel the many mysteries surrounding dark energy. Each breakthrough brings us one step closer to understanding the nature of this powerful and enigmatic force that drives the accelerating expansion of the cosmos. These investigations are vital not only for understanding the present state of the universe, but also for predicting its eventual fate. In essence, both dark matter and dark energy represent the hidden forces that shape the universe in ways that we are only beginning to understand. These two mysterious components of the cosmos profoundly influence its structure, behavior, and evolution. Whether through the search for elusive particles or the study of the repulsive force behind dark energy, scientists continue to push the boundaries of knowledge in an effort to unveil the deepest secrets of the universe itself. However, dark matter and dark energy, while both deeply interconnected with the structure and evolution of the universe, are fundamentally distinct in their nature and behavior. By examining their relationship, we can deepen our understanding of the cosmos, even though they each play vastly different roles in shaping the universe. Dark matter is primarily concerned with the gravitational architecture of the cosmos. Despite being invisible and elusive, it constitutes a large portion of the universe's mass. Its gravitational influence helps govern the motion of galaxies and the formation of large-scale cosmic structures. Without the presence of dark matter, the observed movements of galaxies and galaxy clusters would be incomprehensible, as visible matter alone lacks the necessary mass to generate the observed gravitational effects. Essentially, dark matter acts as a stabilizing force, preventing galaxies from flying apart and helping shape the intricate cosmic web that binds the universe together. On the other hand, dark energy is a mysterious force linked to the accelerated expansion of the universe. Unlike dark matter, which pulls matter together, dark energy exerts a repulsive force that pushes galaxies apart, causing space itself to expand at an increasing rate. Dark energy makes up the majority of the universe's total energy density, and its effects are integral to our understanding of cosmic evolution. While dark matter behaves as a form of mass, exerting gravitational attraction, dark energy operates in direct opposition to gravity, accelerating the expansion of the universe. Despite these stark differences, some speculative theories suggest that there might be a deeper, hidden connection between dark matter and dark energy. These theories propose that both could arise from a single, unified origin, possibly reflecting aspects of a broader framework that humanity has yet to fully understand. Some scientific models speculate that interactions between dark matter and dark energy could subtly influence cosmic evolution, potentially offering new insights into the workings of the universe. However, concrete evidence to support such connections remains elusive, and ongoing research continues to explore these possibilities. At present, dark matter and dark energy serve distinct yet complementary roles in the universe. While dark matter helps form and stabilize the structures we observe, dark energy is responsible for driving the rapid expansion of the cosmos. As researchers continue to investigate these enigmatic forces, they aim to uncover any potential links between them, providing a more cohesive understanding of the universe's intricate dynamics. In parallel, alternative theories of gravity have emerged, proposing different explanations for the cosmic phenomena typically attributed to dark matter and dark energy. These theories are driven by the need to address certain inconsistencies and challenges present in the standard cosmological models, particularly those related to gravitational behavior at cosmic scales. One such theory, known as modified Newtonian dynamics, MND, suggests that at very low accelerations, such as those found at the edges of galaxies, the laws of gravity might differ from Newton's laws. According to MOND, the observed galactic rotational curves could be explained without invoking dark matter, providing a novel way to understand gravitational forces in the cosmos. While MOND has succeeded in explaining some galactic phenomena, it struggles to account for large-scale structures in the universe or the cosmic microwave background radiation, two key elements that are crucial to our understanding of cosmology. Another alternative theory, known as scalar tensor gravity, introduces additional scalar fields that interact with gravity, offering a potential explanation for the effects attributed to dark energy. These scalar fields could modify the behavior of space-time, leading to accelerated cosmic expansion without requiring the presence of dark energy. However, this theory, too, is still in its infancy and must be reconciled with a wealth of observational data. Some researchers are also investigating theories that attempt to unify gravity with quantum mechanics, such as loop quantum gravity or string theory. These cutting-edge ideas hold the potential to reveal new insights into the nature of both gravity and the unseen components of the universe, possibly linking dark matter and dark energy to the fundamental structure of reality itself. Despite the intriguing possibilities offered by these alternative theories, the current cosmological framework, which includes dark matter and dark energy, remains robust, supported by a wide array of observational evidence. The ongoing quest to test and validate these alternative theories is still very much alive, with researchers hoping to refine our understanding of the universe's most fundamental forces. The detection of fast radio bursts, FRBs, sudden and intense flashes of radio waves originating from distant galaxies, has opened up new avenues for understanding the cosmos. First discovered by accident in 2007, These enigmatic bursts have captivated the scientific community due to their immense energy, brief duration, and their mysterious origins. Each burst lasts only a few milliseconds, yet the energy released is equivalent to what the sun emits over an entire day. This extraordinary energy output has prompted astronomers to investigate their source and what they might reveal about the universe. The cause of FRBs remains largely unknown, but several hypotheses have been proposed. One leading theory is that FRBs are produced by neutron stars, specifically magnetars. These dense, highly magnetic remnants of supernova explosions may, under certain conditions, emit massive bursts of energy. When a magnetar undergoes a starquake, a sudden shift in its internal structure, it could release a burst of radio waves that we detect as an FRB. This theory is particularly compelling because some FRBs exhibit repeating patterns, suggesting that they may originate from a specific source that produces bursts under certain conditions. Alternatively, some have proposed that FRBs could be the result of cataclysmic events involving black holes or the merger of compact objects such as neutron stars. In such violent cosmic occurrences, immense amounts of energy are released, potentially producing the radio waves that we detect, FRBs. This potential link between FRBs and high-energy astrophysical events opens up new possibilities for studying the extreme behaviors of matter in the universe. Whether these bursts arise from relatively common astrophysical processes or are tied to more exotic phenomena remains a subject of intense study. As technology continues to advance, the ability to detect and study FRBs becomes more refined, and researchers are making significant strides in pinpointing the sources of these bursts. Understanding their origins could offer critical insights into the processes that govern the evolution of galaxies, the behavior of matter in extreme conditions, and the nature of cosmic events that occur on the largest scales. An even more speculative yet intriguing hypothesis surrounding FRBs is the idea that some of these bursts could be signals from advanced alien civilizations. While this theory is highly speculative and controversial, it has nonetheless captured the imaginations of both scientists and the public. Proponents of this idea argue that the regularity and certain unique characteristics of some repeating FRBs could hint at a technological origin. Unlike natural cosmic phenomena, which often exhibit unpredictable and erratic patterns, artificial signals might be expected to display more structured and consistent traits. To explore this possibility, researchers have begun analyzing FRBs for any patterns or behaviors that might indicate intentional communication, rather than random astrophysical occurrences. While this theory remains speculative, it adds an exciting layer to the ongoing search for extraterrestrial intelligence, demonstrating the diverse range of possibilities that FRBs might represent. In conclusion, whether the result of dark matter and dark energy or the product of previously unconsidered cosmic events, both of these phenomena challenge our current understanding and continue to drive scientific inquiry. As our ability to detect and interpret these mysteries improves, we may find that they reveal fundamental truths about the nature of the universe itself, truths that could reshape our entire perception of space, time, and the cosmos. However, validating the extraterrestrial hypothesis is far from straightforward. The sheer diversity of fast radio bursts, FRBs, and their detection across multiple galaxies strongly suggests that these signals most likely arise from natural astrophysical processes rather than being the result of artificial signals. As scientists have delved deeper into the nature of these bursts, refining their understanding of their origins, many have concluded that the characteristics of FRBs align more closely with high-energy cosmic events, such as those triggered by neutron star activities or black hole interactions. In the broader context of searching for extraterrestrial intelligence, dedicated programs like the Search for Extraterrestrial Intelligence, SETI, have played a pivotal role in actively scanning the skies for signals that exhibit signs of intelligence. These signals are carefully distinguished from naturally occurring radio waves to ensure that any potential discovery is meaningful. While the notion of FRBs being linked to extraterrestrial civilizations remains an enticing possibility, the prevailing scientific consensus leans toward interpreting these phenomena as the result of cosmic forces rather than alien communications. As research advances, the mystery of FRBs may provide us with crucial insights into the universe's inherent nature, potentially shedding light on the existence of life elsewhere in the cosmos. One particularly fascinating cosmic phenomenon is the gamma-ray burst, GRB, a rare and extraordinarily energetic explosion that releases intense bursts of gamma radiation, the most powerful form of electromagnetic radiation known. These events can briefly outshine entire galaxies, with their intensity lasting from mere milliseconds to several minutes. Understanding the causes of GRBs has become a focal point for astrophysics, and numerous leading theories have emerged to explain their origins. Gamma-ray bursts are typically categorized into two groups: long-duration and short-duration bursts. Long-duration GRBs, which last for more than 2 seconds, are often linked to the collapse of massive stars during supernova events. When a massive star exhausts its nuclear fuel, its core collapses under gravity, leading to the formation of a black hole. This cataclysmic collapse can produce highly focused jets of material traveling close to the speed of light, resulting in the release of intense gamma radiation as these jets break free from the star's outer layers. The subsequent explosion becomes one of the most energetic events in the universe, lighting up the cosmos and providing a spectacular display of nature's raw power. In contrast, short-duration GRBs, which last less than 2 seconds, are typically associated with the merger of compact objects like neutron stars or black holes. As these incredibly dense objects spiral inward and ultimately collide, they release enormous amounts of energy in the form of gamma rays, often accompanied by gravitational waves. Observations of these bursts have not only expanded our understanding of the universe, but also contributed significantly to the field of gravitational wave astronomy. By studying these phenomena, scientists have gained valuable insights into the behavior of neutron stars and the processes that govern the formation of black holes. The study of GRBs holds immense value, not just because of the raw energy they emit, but because of the vital information they offer about the early universe. By analyzing the light emitted by GRBs and their afterglows, astronomers are able to peer into the distant past, investigating the conditions of the universe when it was still in its infancy. This research continues to deepen our understanding of stellar evolution, the formation of exotic cosmic objects, and the behavior of matter in extreme environments. Ultimately, it reveals fundamental aspects of our universe's history, offering a glimpse into its earliest stages. Another enigmatic cosmic phenomenon that has puzzled scientists is the disappearance of stars, which may seem to vanish without a trace. The explanation for this often lies in the final stages of stellar evolution and the specific conditions surrounding a star's collapse. While stars generally follow a well-defined life cycle culminating in dramatic events, there are cases where the outcome can be both elusive and deceptive. One intriguing explanation for disappearing stars is linked to supernova, the explosive deaths of massive stars. Typically, when such a star exhausts its nuclear fuel, it undergoes a supernova explosion, producing a brilliant flash of light visible across vast distances. However, in certain cases, the core of the star may collapse into a black hole, while the outer layers of the star are ejected with little to no luminosity. If the supernova lacks sufficient energy to produce a noticeable burst of light, the star can appear to vanish, leaving behind no visible remnants, such as a bright explosion. In some instances, stars may also be obscured by interstellar material. Cosmic dust and gas can block our view of celestial objects, causing stars to appear to fade from sight. In regions of dense star formation or within complex nebulae, light from certain stars can be absorbed or scattered, making them invisible to our telescopes. Until improved observational techniques or advanced instruments reveal these hidden stars, they may be thought to have disappeared, despite still existing in the depths of space. Moreover, some phenomena or temporary variables can give the impression that stars vanish. For instance, certain types of variable stars undergo fluctuations in their brightness. During their dimming phases, they may appear to fade from view, as if they have disappeared altogether. However, the advent of new observational techniques, especially those using different wavelengths like infrared and radio waves, has greatly improved our ability to detect such stars. These innovations have allowed us to uncover celestial bodies that were once thought to be lost in the vast expanse of space. The study of these so-called disappearing stars not only deepens our understanding of the intricate life cycles of stars, but also underscores the critical need to observe and interpret a broader spectrum of astronomical signals. As ongoing research continues to shed light on these enigmatic phenomena, we are uncovering the dynamic and often hidden nature of the cosmos. These discoveries are pushing the boundaries of what we know about the universe, revealing that the universe is more unpredictable and mysterious than we could have ever imagined. One of the most captivating and puzzling events in the search for extraterrestrial intelligence, SETI, is the WOW signal. Detected on August 15, 1977 by astronomer Jerry R. Amon using the Big Ear radio telescope, this intense burst of radio waves lasted for 72 seconds. What made the signal so intriguing was its apparent origin. It seemed to come from the direction of the Sagittarius constellation, more specifically from a point near the star Chi Sagittarii. The signal stood out due to its remarkable intensity, coupled with the fact that it was recorded at a frequency of 21 centimeters, a wavelength that is significant because it is where hydrogen, the most abundant element in the universe, radiates. This wavelength is often considered a key marker for potential extraterrestrial signals, which led some to speculate that the signal could have originated from an intelligent source rather than from typical cosmic phenomena such as stars or planets. Upon seeing the data, Eamon was so astonished that he circled the alphanumeric string that represented the signal and wrote, "Wow," in the margin, forever naming the phenomenon after that single reaction. Despite numerous attempts to detect the signal again, it has never been observed since that initial event, leading to an array of theories about its origin. Some scientists have speculated that the signal might have been caused by a comet emitting a radio wave, while others have suggested the possibility of terrestrial interference or even the intentional transmission of a signal from an alien civilization. However, no explanation has been definitively proven, leaving the WOW signal as one of the most enduring mysteries in the search for extraterrestrial life. The lack of follow-up detections only adds to the allure of the signal, making it an essential part of the ongoing conversation surrounding the quest for life beyond Earth. As technology advances and our searches expand into new realms, the possibility of detecting similar signals continues to fascinate researchers. The WOW signal remains a tantalizing reminder that the cosmos still holds many secrets, some of which may challenge our understanding of the universe and our place within it. One of the most exciting and promising areas in astrobiology is the potential for Earth-like exoplanets to harbor life. Astronomers have already discovered thousands of exoplanets, some of which reside within their star's habitable zone, the region where conditions might be right for liquid water to exist, a key ingredient for life as we know it. One of the most intriguing candidates for this search is Proxima Centauri b, an exoplanet that orbits the closest star to our solar system, Proxima Centauri. This planet lies within its star's habitable zone, raising the possibility that it could have conditions favorable for the presence of liquid water. However, many questions remain about its atmosphere and whether it has a magnetic field capable of shielding life from harmful cosmic radiation. Another notable exoplanet is Kepler 186f, which is roughly 1.1 times the size of Earth and also resides within its star's habitable zone. Though much remains unknown about the planet's composition and atmosphere, the discovery of this planet alone has sparked significant excitement in the scientific community. Future studies will focus on the search for biosignatures in its atmosphere, key indicators that could suggest the presence of life. While these exoplanets may have the right conditions to support life, it's important to note that the mere existence of Earth-like qualities does not guarantee that they can harbor life. Conditions on these planets could be vastly different from those on Earth, meaning that life, if it exists, may take forms or survive in ways we cannot yet imagine. This ongoing quest to understand the potential for life beyond our planet is a driving force behind modern astrobiological research, with each new discovery inching us closer to answering one of humanity's most profound questions. Are we truly alone in the universe? The search for microbial life within our own solar system is equally compelling. Mars, in particular, has long been a prime target for exploration, owing to evidence that it once had liquid water on its surface. Past missions, including the Opportunity and Curiosity rovers, have uncovered minerals that form in the presence of water, suggesting that the planet may have had a much wetter and perhaps more hospitable past. More recently, the Perseverance rover has been tasked with searching for biosignatures on Mars, with the goal of determining whether life once existed there, or whether it might still persist in some microbial form. Similarly, Europa, one of Jupiter's moons, is another prime candidate for the search for extraterrestrial life. Beneath its icy surface, Europa is thought to have a subsurface ocean, which could harbor the conditions necessary for life. Researchers are hopeful that missions targeting these distant worlds will provide answers to some of the most fundamental questions about life in the cosmos, helping us understand not only the potential for life elsewhere, but also the history of life on Earth. As our exploration of the universe continues, driven by humanity's relentless curiosity and desire for knowledge, the search for life beyond Earth remains one of the most exciting endeavors of our time. With each new discovery, we take one step closer to understanding whether we are truly alone in the vast, enigmatic expanse of the cosmos. The discovery of seasonal methane fluctuations in the Martian atmosphere offers a tantalizing glimpse into the potential for life beyond Earth. Methane, a compound that can be produced by biological processes, raises intriguing possibilities about the conditions on Mars. While no direct evidence of life has been confirmed, the data gathered by both current and future missions could shed light on the red planet's ability to support microbial life. In particular, the seasonal variations in methane levels suggest that some underlying process, possibly biological, could be at play. Understanding these fluctuations may be crucial for evaluating Mars's potential habitability. As exploration continues, each new mission adds valuable pieces to the puzzle, providing greater clarity on whether Mars could once have harbored life, or perhaps still does beneath its icy surface. Meanwhile, another celestial body is also drawing significant attention in the quest for extraterrestrial life: Europa, one of Jupiter's moons. Beneath its thick icy crust, Europa hides a vast ocean of liquid water, a fundamental ingredient for life as we know it. This ocean, kept liquid by the immense gravitational forces from Jupiter, may offer the necessary environment for microbial life to thrive. The warmth generated by tidal interactions with the gas giant could create a chemical environment rich in the compounds required for biological processes. NASA's upcoming Europa Clipper mission is set to study this moon in greater detail, focusing on its surface and assessing the potential for habitability. As technology advances and we develop a deeper understanding of Earth's extreme environments, our optimism grows. We are now more confident that microbial life may not be confined to Earth, but could be found elsewhere within our solar system, such as on Europa or Mars. Though the evidence for life on these distant worlds remains indirect at best, the ongoing exploration of these celestial bodies offers hope. Each discovery brings us closer to answering one of humanity's oldest and most profound questions. Are we alone in the cosmos? The discovery of even microbial alien life would drastically alter our understanding of the universe and our place within it. It would affirm that life is not an exclusive trait of Earth, but rather a phenomenon potentially widespread across the vast expanse of space. This realization would prompt a paradigm shift in our view of the universe, challenging the long-held notion of Earth's uniqueness. Philosophically and scientifically, such a discovery would ignite debates on life's resilience, adaptability, and the factors that contribute to its survival in the harshest conditions. The consequences of confirming extraterrestrial life extend beyond the realm of science and into the broader culture. Religions and belief systems would be forced to reconsider their teachings, attempting to reconcile the existence of life beyond Earth with their spiritual narratives. At the same time, the confirmation of alien life would undoubtedly spark a surge of interest in science, particularly in space exploration. Governments and private entities would likely increase their investments in planetary exploration, with the hope of uncovering more about the origins and nature of extraterrestrial life. The very notion of life beyond our planet would raise fundamental questions about communication, intelligence, and the possibility of interstellar cooperation or conflict. Moreover, the discovery of microbial life on another world would prompt scientists to revisit the question of how life evolves and under what conditions it can thrive. Would these organisms share biochemical similarities with life on Earth, or would they rely on entirely different processes? This could open up entirely new fields of study in biology and astrobiology, broadening our definition of life itself. The implications for our understanding of the universe and the nature of life would be profound, potentially altering the trajectory of scientific inquiry for generations to come. Whether single-celled organisms or more complex forms of life, the discovery of extraterrestrial life would have a profound effect on our collective imagination. It would urge humanity to look beyond our home planet, encouraging exploration of the broader universe. This realization would serve as a reminder of our shared existence within the cosmos, fostering a sense of connection to the infinite reaches of space. It would also raise important questions about our responsibility as stewards of Earth, urging us to consider the implications of our actions on both our planet and beyond. As the search for alien civilizations continues, scientists are employing a range of innovative techniques to uncover signs of intelligent life. One of the most well-known methods is the Search for Extraterrestrial Intelligence, SETI, which focuses on detecting radio signals from distant civilizations. By scanning specific frequencies for non-random patterns, researchers hope to identify signals that might indicate deliberate communication. Given the vastness of the universe and the background noise that permeates space, any distinct signal would stand out as a potential sign of extraterrestrial intelligence. Another promising approach involves the study of exoplanet atmospheres for biosignatures and technosignatures. By analyzing the light that passes through a planet's atmosphere during a transit, scientists can detect certain gases, such as oxygen and methane, that could suggest biological processes. If the combination of gases is not in equilibrium, it may point to industrial activity, perhaps hinting at the existence of advanced civilizations. Transit observations, like those made by the Kepler mission, could also reveal unusual patterns of light that might indicate the presence of megastructures, such as Dyson spheres. These hypothetical constructs are designed to capture the energy of a star, and any significant alteration in a star's brightness might be a clue to their existence. In addition to these efforts, advances in optical SETI are helping to expand the search for alien life. This method involves looking for laser pulsar pulses or other optical emissions that might indicate the presence of advanced technology. Unlike radio waves, which spread out as they travel, lasers can be more efficient for communication over long distances. Researchers believe that at certain distances, a focused laser beam may be more effective than traditional radio signals. As technology advances, these new approaches ensure that the search for extraterrestrial civilizations remains dynamic and adaptable, increasing the likelihood of discovering life beyond Earth. Despite the ongoing efforts and the vastness of the universe, the absence of conclusive evidence for alien life can be attributed to a number of factors. One of the most significant challenges is the sheer scale of the cosmos. With an estimated 2 trillion galaxies, the distances between stars and planets are so vast that even our most advanced telescopes and space missions are limited in the volume of space they can effectively explore. As a result, the search for extraterrestrial life remains a daunting task, requiring patience, persistence, and the continued advancement of technology. The search for life beyond Earth is not only a scientific endeavor, it's a quest that taps into the very heart of human curiosity. It drives us to look beyond the confines of our home planet and ponder our place in the universe. As we continue to explore the cosmos, the question of whether we are alone will undoubtedly remain one of the most profound and enduring mysteries of our time. The possibility of alien civilizations existing at vastly different stages of technological development presents an intriguing conundrum in the search for extraterrestrial life. It is conceivable that the technological evolution of civilizations may vary drastically, leading to scenarios where we are either too advanced or too primitive to detect each other. In this vast, cosmic expanse, civilizations could exist at different levels of technological sophistication. some far beyond us, capable of communication across the stars, while others may still be in their infancy, barely emerging from the cradle of evolution. It is equally possible that some civilizations may have reached their peak eons ago, only to perish, leaving behind no traces of their existence. The way in which these advanced civilizations might communicate is another critical factor to consider. If they have developed methods of communication that we have not yet discovered or do not yet understand, such as using different frequencies, technologies, or even forms of intelligence that go beyond our current comprehension, we may be entirely incapable of recognizing their signals. These forms of communication could be beyond our scope, hidden in plain sight, yet eluding us due to the limitations of our current scientific and technological knowledge. Moreover, the conditions necessary for intelligent life may be incredibly rare across the universe. The environmental factors that support the development of life, particularly complex and intelligent life, could be so specific that they only occur in a tiny fraction of all possible worlds. This leads to another pressing question. Are we searching in the right places? Are we using the correct methods to detect signs of extraterrestrial life? The search for answers may not only be a matter of technology, but also of perspective and approach. This puzzle is elegantly encapsulated by the famous Fermi paradox. If extraterrestrial civilizations are indeed common, why have we not encountered any evidence of their existence? This paradox highlights the contradiction between the seemingly high probability of alien life, given the vast number of planets that could support it, and the utter lack of evidence to support such claims. It is a paradox that continues to intrigue and challenge scientists, prompting new theories and methods of exploration as our understanding evolves. With each passing year, our technological capabilities expand, and our reach into the cosmos extends further. We remain hopeful, for every new discovery brings us one step closer to answering one of humanity's most profound and elusive questions. Are we alone in the universe? When matter and information fall into a black hole, they approach an event horizon, the boundary beyond which nothing can escape, not even light. As objects draw closer to this threshold, they encounter extreme gravitational forces which stretch and compress them in a process known as spaghettification. This phenomenon occurs because the gravitational pull is far stronger at the point closest to the black hole, causing the object to elongate and eventually be torn apart as it moves deeper into the singularity. The fate of information, in particular, raises profound questions about the fundamental nature of reality. According to classical interpretations of physics, once matter crosses the event horizon, the information it contains is lost forever to the outside universe. This notion has led to what is known as the information paradox, a dilemma that challenges our current understanding of physics. According to quantum mechanics, however, information cannot be destroyed, leading to a major contradiction. If the information about the matter that fell into a black hole is not lost, then it must somehow be preserved. This has led to various speculative theories, some of which suggest that the information might be encoded on the event horizon itself, a concept known as holography. In this view, the surface area of a black hole contains all the information about what has fallen into it, challenging our conventional understanding of space, time, and matter. Other theories propose the existence of black hole firewalls, which suggest that an energetic boundary exists at the event horizon, radically altering our perceptions of black holes and their interaction with the rest of the universe. These theories push the boundaries of our understanding, suggesting that the very fabric of reality may be far more complex and mysterious than we previously imagined. As our knowledge of black holes deepens, driven by both observational discoveries and theoretical advancements, we may one day find a resolution to these paradoxes. These breakthroughs could lead to a fundamental shift in our understanding of the universe, potentially revealing answers that have eluded us for centuries and transforming the way we perceive the cosmos. The concept of black holes as potential gateways to other universes or dimensions has long captivated both scientists and the general public. While traditional physics treats black holes as regions of intense gravitational pull, where nothing can escape, More recent theories in the realms of quantum mechanics and string theory propose that black holes might act as conduits to other realms entirely. The idea of a wormhole, a hypothetical tunnel-like structure connecting two separate points in space-time, suggests that black holes could serve as shortcuts, allowing travel not just within our universe, but potentially to entirely different universes governed by their own set of physical laws. One of the more fascinating hypotheses posits that the core of a black hole might contain a wormhole that leads to another dimension, offering a portal to a completely different universe with a unique set of physical rules. However, these ideas are still highly speculative and face significant hurdles from both theoretical and observational standpoints. The conditions within the singularity, the point at which gravity is thought to become infinite, remain a profound challenge to our understanding of physics. As science continues to explore these extreme phenomena, the questions surrounding the true nature of black holes and the possibility of parallel universes or alternate dimensions will persist. It is a realm where the known and the unknown collide, offering tantalizing glimpses into the potential future of physics and our understanding of reality itself. While these theories remain speculative for now, they continue to inspire research and exploration, pushing the boundaries of what we know and expanding the horizons of human knowledge. Black holes, long a source of fascination and speculation, continue to captivate the imagination of scientists and enthusiasts alike. Their enigmatic nature is both a challenge and an invitation for exploration. However, any potential wormhole, even if one could be created within a black hole, would likely be inherently unstable, collapsing almost instantly and making practical traversal an exceedingly remote possibility. This aligns with the core principle of the no-hair theorem, which suggests that black holes can be described by only three observable characteristics: mass, charge, and angular momentum. All other details, including any potential hidden pathways to other dimensions, remain concealed within the event horizon, obscured from our view. Despite these limitations, the idea of black holes serving as potential gateways to other realms remains an alluring topic within theoretical astrophysics. As we continue to deepen our understanding of quantum gravity and the fundamental nature of space-time, the hypothesis that black holes might connect to alternate dimensions could offer transformative insights into the very fabric of reality itself. At present, there is no direct empirical evidence to suggest that black holes function as portals to other universes or dimensions. Yet this tantalizing concept continues to fuel scientific inquiry and spark the boundless creativity of the human imagination. At the heart of most galaxies, including our own Milky Way, reside supermassive black holes. These giants, with masses ranging from millions to billions of times that of our Sun, represent some of the most powerful and mysterious objects in the universe. While the precise processes responsible for their formation remain a subject of intense debate and research, several theories provide fascinating clues. One prominent theory proposes that supermassive black holes form through the merger of smaller black holes and massive stars in the early universe. In this scenario, dense star clusters emerged, some of which gave birth to massive stars. These stars eventually ended their lives in cataclysmic supernova, leaving behind remnants that could collapse into black holes. As these smaller black holes were drawn toward the center of their host galaxies, they merged over time, creating progressively larger black holes. Another compelling theory suggests that supermassive black holes could arise from the direct collapse of enormous gas clouds in the early universe. In regions of exceptionally high density, gas could rapidly collapse under its own gravitational pull, bypassing the typical process of star formation entirely. This collapse could give birth to a massive black hole in a fraction of the time it would take for stars to form, potentially within the first few 100 million years after the Big Bang. This hypothesis is supported by observations of extraordinarily massive black holes in young, distant galaxies, which suggests that such events may have occurred much earlier than previously thought. The merger of galaxies is another crucial factor in the formation and growth of supermassive black holes. When two galaxies collide, their central black holes can also merge, creating even larger supermassive black holes. This gravitational dance, marked by violent interactions between the galaxies, can trigger intense bursts of energy and lead to the formation of active galactic nuclei, regions around black holes that radiate tremendous amounts of energy as they consume surrounding gas and matter. This process highlights the intricate interplay between gravity, matter, and energy, bringing us closer to understanding how the colossal structures we observe in the cosmos came to be. As technological advancements in telescopes and detection methods continue, scientists are hopeful that they will eventually unravel the mysteries surrounding the formation and growth of these supermassive black holes. The questions about their influence on galaxy formation and evolution remain central to our quest for understanding the cosmos. More specifically, the relationship between black holes and galaxies, though complex, has profound implications for our understanding of the universe. Supermassive black holes residing at the centers of galaxies are thought to play a pivotal role in shaping their host galaxies. One of the key aspects of this relationship is the way in which supermassive black holes regulate star formation within their galaxies. As they accrete matter and radiate energy, black holes can produce powerful jets and winds that influence the surrounding gas. These outflows have the potential to suppress or stimulate star formation, either by blowing gas away from the central regions or by causing gas to cool and collapse into new stars. This feedback mechanism helps to shape the galaxy's structure and growth over cosmic time, suggesting that black holes and galaxies are intricately linked throughout their evolution. Observations reveal a significant correlation between the mass of a supermassive black hole and the characteristics of its host galaxy. More massive black holes are often found in larger galaxies, supporting the idea that there is a co-evolutionary relationship between the two. This relationship is further exemplified by the correlation between the mass of the black hole and the velocity dispersion of stars in the galaxy's bulge. This connection suggests that the formation of the black hole and the galaxy may have occurred simultaneously during the early stages of their development. Galaxy mergers further underscore the connection between black holes and galactic evolution. When galaxies collide, their central black holes inevitably engage in the dramatic process of merging. The resulting gravitational interactions can lead to the formation of even more massive black holes, which in turn can profoundly influence the dynamics of the newly formed galaxy. These mergers are often accompanied by bursts of star formation and shifts in the galaxy's overall structure, further illustrating the interconnectedness of black holes and galaxy formation. As research into these cosmic phenomena continues, scientists are gaining crucial insights into how black holes and galaxies evolve together, shaping the structures we observe in the universe today. The study of these interactions is helping to reveal the intricate and dynamic relationship between gravity, matter, and evolution across vast stretches of cosmic time. Within the classical framework of physics, once an object crosses the event horizon of a black hole, it is considered irretrievable. The gravitational pull of the black hole is so immense that not even light can escape its grasp. The mysteries that lie beyond the event horizon remain one of the most profound and unresolved questions in physics, promising new insights into the nature of space, time, and the universe itself. Black holes, enigmatic and mysterious, have long been subjects of deep fascination and intense research in the realms of theoretical physics. While the prevailing notion is that nothing can escape a black hole once it crosses the event horizon, certain phenomena, especially those linked to quantum mechanics, suggest otherwise. The consideration of escape from black holes thus takes on new dimensions when viewed through the lens of quantum theory, revealing unexpected possibilities for how these cosmic giants interact with the universe. One of the most intriguing ideas to emerge in the study of black holes is Hawking radiation, proposed by physicist Stephen Hawking in 1974. According to quantum theory, the vacuum of space is not truly empty. Instead, it is constantly teeming with virtual particles that spontaneously appear and annihilate each other. Near a black hole's event horizon, these virtual particles can be separated, with one of the particles falling into the black hole while the other escapes into space. This escaping particle would be detected as radiation, providing a means for energy and information to be emitted from the black hole. Over time, this emission could lead to the gradual evaporation of the black hole as it loses mass in the process. However, while Hawking radiation remains a theoretical construct and has not yet been directly observed, it represents a groundbreaking possibility: the idea that black holes are not entirely isolated entities, but may in fact be capable of losing mass and energy. The immense strength of a black hole's gravitational pull may keep objects from escaping once they cross the event horizon, but quantum effects suggest that black holes could still shed radiation from their surroundings. Beyond Hawking radiation, there are other phenomena occurring around black holes that also hint at the possibility of escape, albeit indirectly. The material surrounding a black hole can be drawn toward it by its gravitational force, forming what is known as an accretion disk. As matter spirals inward, it becomes incredibly hot and emits vast amounts of energy. This process can generate powerful jets of particles and radiation, which shoot out from the poles of the black hole. These jets carry away energy and information, offering a fascinating window into the workings of a black hole's environment. Although nothing can escape once it crosses the event horizon, these energetic interactions occurring just outside of it create observable effects that challenge our understanding of the black hole's true nature. The concept of escape from a black hole thus presents a complex intersection of gravity, quantum mechanics, and our understanding of space-time. As research into the complexities of black holes continues, particularly with regards to Hawking radiation and the nature of space-time, scientists remain engaged in unraveling the mysteries of these cosmic entities. In the process, they might discover new ways in which black holes interact with the universe, forcing us to reconsider what we think we know about one of the most enigmatic objects in the cosmos. Another area of intense fascination in theoretical physics, and one that has captivated human imagination for centuries, is time travel. While time travel is a frequent theme in science fiction, the possibility of manipulating time has also been explored in the field of physics. Although no empirical evidence currently supports the feasibility of time travel, certain theoretical frameworks in physics suggest that, under specific conditions, time travel could be possible. One of the most compelling theories related to time travel is grounded in Albert Einstein's theory of relativity. In this framework, time is not a fixed, unchanging quantity. Instead, it is influenced by factors such as speed and gravity, leading to the phenomenon known as time dilation. According to this idea, as an object approaches the speed of light, time slows down for that object relative to an outside observer. This means that if a spacecraft could travel at relativistic speeds, the astronauts aboard could, in theory, jump forward in time, experiencing time at a slower rate than those remaining on Earth. This kind of time travel, however, is essentially a one-way journey into the future and does not allow for a return to the past. But time dilation is not the only theoretical avenue for time travel. Another intriguing possibility is found in the concept of wormholes, hypothetical shortcuts through space-time that could connect distant points in the universe or even different times. In theory, a wormhole could provide a pathway for time travel, allowing an object to travel instantaneously between 2 points in time or space. However, the existence of stable wormholes remains an open question in physics. Even if they do exist, creating or stabilizing a wormhole would likely require exotic matter with negative energy density, something that has yet to be discovered. As such, while wormholes offer tantalizing possibilities, their practical existence is far from certain. Additionally, the concept of closed time-like curves presents another avenue for exploring time travel, particularly to the past. A closed time-like curve is a path through space-time that loops back on itself, creating a possible route for time travel to earlier moments. These curves could, in theory, allow for time travel to the past, but they also raise numerous paradoxes, such as the grandfather paradox, in which a time traveler could potentially alter the past in such a way that their own existence would be prevented. These paradoxes challenge our understanding of causality, the principle that causes precede effects, and raise deep philosophical questions about the nature of time and reality. Despite these fascinating theoretical concepts, practical time travel remains speculative at best. Current technological limitations and our incomplete understanding of the laws of physics make it impossible to say with certainty whether time travel will ever be achievable. Nonetheless, the continued exploration of these theories, particularly regarding wormholes, closed time-like curves, and fabric of space-time, ensures that time travel remains a captivating subject for scientific and philosophical debate. Time travel brings with it a host of profound implications and paradoxes that force us to rethink the very nature of physics, causality, and reality. One of the most significant implications centers around the concept of causality. If time travel to the past were possible, could it allow individuals to change events that have already happened? The ability to alter past events could lead to contradictions within the timeline, raising fundamental questions about the stability and consistency of the universe. As scientists and philosophers continue to explore the boundaries of space-time and time travel, we are left to wonder, could time travel one day become a reality, or is it forever confined to the realm of speculative fiction? The answers may be closer than we think, or perhaps they remain beyond the horizon of our understanding. The grandfather paradox stands as one of the most perplexing and widely discussed conundrums in the realm of time travel. The scenario unfolds when a time traveler journeys into the past, only to unwittingly prevent a pivotal event, such as their grandfather meeting their grandmother. In this instance, the implications are profound. The time traveler's existence becomes impossible. If their grandfather never meets their grandmother, the time traveler could never have been born. And yet, if they were never born, how could they have traveled back in time in the first place? This paradox encapsulates the heart of the issue with time travel, the potential for contradictory outcomes that emerge from attempting to alter events that have already occurred. The grandfather paradox reveals just how intricate and problematic it can be to alter past occurrences, especially when such changes could lead to logical impossibilities. But time travel's challenges go beyond simple contradictions. There's the mind-bending idea of alternate timelines or parallel universes, which introduces a new level of complexity. Some theories posit that if a time traveler changes an event in the past, it doesn't directly affect the original timeline. Instead, it creates a divergent timeline, a parallel universe where the changes they made are isolated from the reality they came from. In this view, the time traveler doesn't undo the past, they merely start a new reality. This possibility introduces fascinating questions about personal identity and causality. If different versions of oneself could exist simultaneously across multiple timelines, what happens to the individual who steps into those alternate realities? Would they still be the same person, or would their identity be fractured across different versions of themselves in divergent worlds? This is where the many worlds interpretation of quantum mechanics comes into play. It proposes that every possible outcome of an event actually takes place, each in its own parallel universe. While this theory could potentially resolve some of the paradoxes inherent in time travel, it brings with it new layers of complexity. If a single change in the past can create an entirely new universe, what does that mean for the responsibility of influencing past events? Could time travelers be held accountable for the creation of these new realities, and by extension, the destinies they shape within them? The ethical considerations surrounding such power would be staggering. The more one delves into the potential consequences of time travel, the more one is led to consider the fundamental nature of free will, fate, and the interconnectedness of all things. Despite all these captivating theories, time travel remains purely speculative. Current physical theories, though they provide fascinating insights, offer no practical method for achieving time travel. And yet, paradoxes like the grandfather paradox and the implications of alternate timelines fuel an ongoing exploration of the nature of time, space, and reality itself. The more we learn about the universe, the deeper our engagement with these profound questions becomes, pushing the boundaries of our understanding of existence. The idea of time travelers from the future visiting our time is equally captivating, but it raises an entirely new set of questions. Could individuals from the future be here, among us, experiencing our present day? While there is no direct empirical evidence to suggest that time travelers walk among us, numerous anecdotal reports, cultural narratives, and speculative theories continue to fuel interest in the possibility. One of the major counterarguments to the notion of time travelers existing in the present is the glaring lack of irrefutable proof. If time travel were possible, it seems likely that some evidence would have surfaced by now. Technologies far beyond our own, unexplained phenomena, or even documented encounters with individuals who seem out of place, these are the types of evidence that might point toward time travelers. But despite the many claims of sightings and mysterious figures, no definitive proof has emerged to validate the existence of time travel. Adding another layer of complexity to the situation, certain theories in physics, particularly those surrounding causality, raise significant issues. If time travel were possible, why hasn't there been any clear evidence of historical changes linked to time travelers? This question suggests that if time travel does indeed exist, future beings might be operating under strict regulations preventing them from altering the past, much like the fictional prime directive seen in science fiction. Such a directive would likely prevent them from intervening in historical events to avoid catastrophic paradoxes. In this light, the lack of evidence for time travelers could be intentional, part of a broader effort to protect the integrity of the past. Another possibility is that time travelers, if they do exist, might be blending in with the present world, adopting contemporary appearances and behaviors to avoid drawing attention to themselves. This would make them nearly impossible to detect. The advanced technology and knowledge they would possess could manifest in subtle, unnoticeable ways. They may not use futuristic gadgets in public for fear of giving away their true origin. However, this remains speculative. While the idea of time travelers among us intrigues and inspires our imaginations, it remains squarely within the realm of theoretical possibility, unsubstantiated by any concrete evidence. At the core of the time travel discussion is the question of how time behaves under extreme conditions, particularly near a black hole. The gravity of a black hole is so intense that it warps the fabric of space and time itself. According to Einstein's theory of general relativity, gravity isn't just a force, but a curvature of space-time caused by massive objects. When an object approaches a black hole, time behaves in strange and remarkable ways. This phenomenon is known as time dilation, where time passes at different rates depending on how close an object is to the black hole. As an object draws closer to the event horizon, the point of no return around a black hole, time appears to slow down dramatically. For an observer falling toward the black hole, time would seem to flow normally. But to an outside observer watching from a safe distance, the person falling into the black hole would appear to move slower and slower as they approach the event horizon. From the outside perspective, it would seem as though time itself is stretching out, dragging the experience of the fall into an eternal moment. The concept of time dilation near a black hole is a powerful illustration of how time is relative. Its passage varies depending on the gravitational influences acting upon it. What might feel like a few minutes for someone falling into the black hole could appear as hours, days, or even centuries to an external observer. This is the essence of the relativity of time, where the experience of time is not uniform but is shaped by the very structure of space and gravity itself. Once an object crosses the event horizon, classical physics suggests that it is lost to the black hole, unable to escape. The further consequences of crossing this threshold are still shrouded in mystery. For the observer falling in, time would continue to move forward, but as they approach the singularity, where the black hole's density and gravitational forces become infinite, the laws of physics as we know them begin to break down. What happens beyond this point remains one of the great unsolved mysteries of modern physics. The very nature of time and space in such extreme environments is radically altered, presenting profound questions that remain unanswered and inviting us to reconsider everything we thought we knew about the universe. The effects of gravitational forces extend far beyond the intense confines of black holes, influencing the very fabric of time itself. While black holes are the most dramatic and well-known example, any massive object in the universe, from stars to planets, can bend the flow of time around it. Take, for instance, the phenomenon of gravitational time dilation. Satellites orbiting Earth experience a slight difference in time compared to clocks on the planet's surface. This occurs because the satellites move at high speeds and are situated at a different distance from Earth's gravitational field. As a result, time for these satellites ticks slightly faster than for us on Earth. This subtle effect, though seemingly insignificant, has profound implications for modern technology, particularly for systems like the Global Positioning System, GPS, which must constantly adjust for this time dilation in order to maintain precise positioning data. The behavior of time in such extreme conditions challenges our intuitive understanding, which usually treats time as a constant. The reality, however, is much more nuanced. By studying how time behaves in varying gravitational environments, we not only deepen our understanding of physics, but also gain insight into the nature of the universe itself. In a more mysterious realm of time, reports of time anomalies, sometimes referred to as time slips, have captured the fascination of both researchers and enthusiasts. These accounts, though often met with skepticism, involve individuals who claim to experience time in a way that deviates from what is recorded by clocks or calendars. In some of these stories, people describe finding themselves briefly transported to different eras, encountering historical figures, or even being immersed in settings that feel out of sync with their current reality. These occurrences, though tantalizing, remain mostly anecdotal and lack empirical evidence. While such tales provoke wonder, scientists often explain them as psychological phenomena rather than actual disruptions in the fabric of time. The brain's perception of time can be influenced by a range of factors, including stress, trauma, and altered states of consciousness. These psychological states can create the illusion of time anomalies, making moments feel stretched or compressed in ways that don't align with physical clocks. Though the idea of traveling through time is not supported by science, the stories of time slips offer a compelling glimpse into the complexities of human consciousness and our often mysterious relationship with the passage of time. They raise profound questions about reality itself, what it is, how we experience it, and whether we truly understand its intricate nature. The concept of multiple universes, or the multiverse, is another captivating idea that stems from the realm of quantum physics and cosmology. This theory suggests that our universe might not be the only one, but rather one of many, each with its own unique laws of physics and distinct variations of reality. The possibility that what we perceive as our singular universe is just a small part of a vast cosmic collection is both mind-boggling and awe-inspiring. Several models of the multiverse have emerged from various interpretations of quantum mechanics, cosmic inflation, and string theory. One of the most intriguing is the many worlds interpretation of quantum mechanics. This theory proposes that every time a quantum event occurs, such as a particle existing in one state or another, the universe splits into multiple branches. Each branch represents a different outcome, potentially creating an infinite number of parallel realities. This challenges our conventional understanding of causality, decision-making, and the notion of free will, suggesting that every choice or event could lead to an entirely different outcome in another branch of the universe. Similarly, the theory of cosmic inflation offers another tantalizing view of the multiverse. According to this model, in the earliest moments after the Big Bang, regions of space expanded at an extraordinarily rapid rate. This led to the formation of bubble universes, each with its own separate space-time. These bubbles could develop vastly different physical characteristics depending on their initial conditions, resulting in universes that could function in entirely different ways. While these theories are mathematically robust and deeply intriguing, direct evidence for the existence of parallel universes remains elusive. Despite the theoretical foundation, no experiment has yet provided a clear way to observe or measure these other realities. The implications of a multiverse are not just limited to abstract theory. They have the potential to reshape our understanding of fundamental aspects of existence, such as time, space, and the very nature of reality. If our universe is merely one of countless others, it forces us to reconsider our place in the cosmos. It encourages both awe and humility as we recognize how small we are in the grand scheme of things, while also stoking our curiosity about the infinite possibilities that might lie beyond the observable universe. Could there be other forms of life in these parallel realities? What different laws of physics might govern them? These questions invite us to look beyond the horizon of our own universe, pondering not only the vastness of the cosmos we inhabit, but also the countless other worlds that may exist just beyond our reach. While evidence for the multiverse remains theoretical, the very possibility of its existence challenges us to think more expansively about the nature of reality and our role within it. However, scientists have proposed several compelling ideas that invite us to reconsider the fundamental nature of existence, the fabric of reality, and the potential for parallel universes. These theories, while speculative and often based on interpretations of existing data in physics and cosmology, open up a vast array of possibilities. One key area of interest is quantum mechanics, particularly the many worlds interpretation. This theory suggests that every possible outcome of a quantum event occurs in its own separate universe. While the idea does not provide direct physical evidence, it offers a coherent framework in which parallel realities could exist. According to this view, the universe is not a single, linear reality, but a branching tree of countless versions, each sprouting from the decisions made at the quantum level. Another theory that fuels the multiverse discussion is cosmic inflation. This model proposes that in the very early moments of the universe, just after the Big Bang, it underwent an extraordinary period of rapid expansion. This inflationary phase could have created bubble universes, each one developing its own set of physical properties. While no bubbles have been directly observed, some scientists believe that disparities in the cosmic microwave background radiation, the afterglow of the Big Bang, may provide faint hints of interactions between neighboring universes during this inflationary period. Researchers are combing through these subtle anomalies, looking for patterns that could support the idea of multiple coexisting universes. Mathematics, too, plays an indispensable role in the search for parallel universes. String theory, which aims to unify the fundamental forces of nature, suggests the existence of numerous possible configurations of dimensions. These higher dimensions could give rise to an array of expansive, separate realities. While these mathematical models are intriguing and have inspired significant theoretical research, they remain speculative. As exciting as the math may be, it does not constitute concrete evidence. Only empirical, physical validation can lead to broader acceptance within the scientific community. Despite the tantalizing nature of these theories, the actual experimental evidence supporting the existence of parallel universes remains elusive. The quest to prove or disprove the multiverse hypothesis continues to drive scientific exploration. As researchers dive deeper into the mysteries of physics, they ponder how our understanding of the universe might evolve. The idea of parallel universes invites us to consider profound questions about the nature of existence, the limits of human knowledge, and the untapped realms that might lie beyond our observable reality. If parallel universes do exist, their characteristics could be vastly different from our own. One fascinating possibility is that the physical constants, the values that govern the fundamental forces of nature, could vary between universes. Imagine a universe where gravity is much stronger than in ours, potentially altering the entire structure of that reality. Such a difference could have far-reaching consequences, including the possibility that life, as we understand it, might never arise in such a universe. Alternatively, other universes might operate under entirely different laws of physics, perhaps allowing phenomena that are unimaginable within the current confines of our scientific knowledge. In these parallel realities, the very rules of space, time, and matter could be rewritten. This opens up a world of possibilities, where realities far beyond our comprehension could be unfolding in ways we cannot even begin to understand. Beyond the physical laws, the histories of these parallel universes could unfold in divergent ways. Key events that shaped our timeline, such as the rise and fall of civilizations, crucial scientific discoveries, or even the outcome of individual decisions, might have played out differently in alternate universes. This brings to the forefront the tantalizing question of identity and the nature of existence. In some universes, we might find alternate versions of ourselves, living entirely different lives, following paths that diverged from the ones we know. The idea that there could be versions of us existing in other realities is a captivating thought, one that sparks both scientific and philosophical inquiry. If these parallel versions of ourselves exist, how would we recognize them? What does it mean to be us in a universe where infinite possibilities unfold with each choice we make? The potential for encountering alternate versions of reality blurs the lines between science fiction and science fact, urging us to rethink the limits of our understanding. However, detecting or interacting with these parallel universes presents significant challenges. Our current scientific tools and observational methods are designed to measure phenomena within our own universe. This makes it incredibly difficult, if not impossible, to access or establish contact with alternate realities. Some researchers speculate that if multiverses are interacting with one another, there might be subtle traces of their existence that could be detected in the form of anomalies in cosmic background radiation or unusual patterns in quantum mechanics. These anomalies, though, remain hypothetical, and no concrete evidence has yet emerged to support these theories. The prospect of interacting with parallel universes raises even more complex questions. Could we travel through dimensions or even wormholes, hypothetical passages through space-time that could connect separate universes? While these concepts are popular in science fiction, practical implementation remains far beyond our current scientific understanding. The idea of traveling between realities challenges the very foundations of physics and requires advances in both theoretical and experimental science that are yet to be achieved. Nevertheless, the thought of encountering alternate versions of reality is a powerful motivator for scientific inquiry. It pushes the boundaries of our imagination, forcing us to consider what might lie beyond the observable universe. Could these parallel realms remain forever beyond our reach, or will future breakthroughs in physics lead us to new dimensions of understanding? The mystery of parallel universes invites us to think about existence itself, offering profound questions about the nature of reality, time, and the infinite possibilities that may be out there. Central to the discussion of parallel universes is the many worlds interpretation of quantum mechanics, which has profound implications for our understanding of existence. At its heart, this theory suggests that every quantum event results in the branching of the universe into multiple, distinct realities, each one representing a different outcome. This concept challenges the traditional view of a single, unbroken timeline. Instead, it posits that each quantum decision leads to the creation of a new universe, with each possibility being realized in one of the infinite branches. In the many worlds interpretation, every decision we make results in the creation of a new branch of reality, each one unfolding in a different direction. For instance, imagine choosing between two paths. In one universe, you take the left path, while in another, you take the right. The many worlds theory suggests that both versions of you continue to exist, each in a separate reality, following different trajectories. This opens up fascinating philosophical questions about free will, destiny, and the nature of choice. If every possible outcome is realized somewhere in the multiverse, what does it mean to make a choice? Are we truly in control of our destinies, or is everything already predetermined, branching into infinite versions of reality? Such a perspective also prompts deeper questions about the nature of consciousness and how we perceive the world around us. If every decision we make creates a new universe, what role does our consciousness play in shaping these realities? Do we exist in all of them simultaneously, or are we simply observers of the universe we inhabit? The many worlds interpretation, with its radical departure from classical ideas of reality, forces us to reconsider not only the structure of the universe, but also the fundamental nature of existence itself. In the realm of quantum mechanics, the many worlds interpretation presents a revolutionary perspective on how we understand reality itself. Traditionally, quantum mechanics relied on the concept of wave function collapse, a process in which probabilities resolve into a single definitive outcome upon observation. In this traditional framework, reality is often thought to narrow into a singular event when it is observed, leaving behind a deterministic path forward. However, the many worlds interpretation challenges this view, proposing a radically different idea. The role of the observer is not merely passive. Instead, it is the observer's consciousness that plays an active role in the unfolding of the universe. Rather than collapsing into a single resolved state, the universe splits, branching into countless parallel realities, each one corresponding to a different outcome. The observer, too, experiences only one of these possibilities, effectively becoming a participant in a vast and ever-expanding cosmic web of realities. This shift in thinking not only redefines our place in the universe, positioning us as active agents in the cosmos, but it also prompts a profound reevaluation of what reality itself means. If the universe is not a single objective entity, but a sprawling network of potentialities, the boundaries of scientific inquiry are pushed further. What was once seen as a static, unchanging framework now opens up into an ocean of possibilities, each one awaiting exploration. Though the many worlds interpretation remains controversial, it serves as a catalyst for rethinking some of the most fundamental questions about existence. Could there be more than one version of reality? Could alternate histories and different futures exist simultaneously, coexisting across parallel universes? Such questions have long been the domain of philosophy, but now, thanks to quantum mechanics, they are beginning to take on a new dimension. As scientists continue to investigate the potential of the many worlds interpretation, they are forced to reconsider how we measure, observe, and understand the fundamental nature of the universe. While conclusive evidence remains elusive, the very concept encourages a fresh perspective on everything, from quantum phenomena to the nature of time, leaving open the possibility that we might one day find ourselves on the cusp of new discoveries in theoretical physics that redefine everything we think we know about the cosmos. One of the more captivating ideas that emerge from this interpretation is the possibility of alternate versions of ourselves existing in parallel universes. Every choice we make, no matter how trivial it may seem, could lead to a branching point in the quantum realm, spawning a new version of reality. In this framework, each decision we make, whether it's choosing a career, a partner, or a place to live, could result in an entirely separate universe where a different path was taken and a different version of ourselves exists. For instance, consider the seemingly simple choice of a career path. In one universe, perhaps you chose the world of art, while in another, you followed a path in science. These two parallel realities, though originating from the same person, could take drastically different trajectories, each version of you living a life shaped by the unique decisions made along the way. Now imagine this concept scaled to infinite possibilities. Each individual choice, the foods you eat, the books you read, the people you meet, could create a separate universe. A universe where different versions of yourself live out entirely different stories, exploring alternate careers, relationships, and identities. The philosophical implications of this concept are profound. If these alternate versions of ourselves are real, what does it mean for our understanding of identity? Are we simply the sum of the choices we make in this reality? Or is there something deeper, something more intrinsic that connects all versions of ourselves, no matter the universe? Each version of us might reflect a unique set of experiences, challenges, and opportunities, all existing simultaneously in an intricate web of realities. This idea also sparks thoughts about fate, regret, and personal growth. If there is an infinite array of potential versions of ourselves, does that mean our choices in this universe are somehow less significant? Or does it highlight the importance of the choices we make? It prompts us to reflect on who we are, what makes us unique, and how the path we've chosen shapes not just our own destiny, but also the fabric of the multiverse. While these musings are tantalizing, it is crucial to recognize the speculative nature of these ideas. Interacting with alternate versions of ourselves or accessing parallel universes remains, at present, a hypothetical notion. Yet the very act of contemplating these possibilities pushes us to question the nature of existence and to seek a deeper understanding of who we are, not just as individuals, but as interconnected points in an infinite web of potentiality. In the broader landscape of physics, another concept of great intrigue is that of cosmic strings. These theoretical, one-dimensional defects in space-time are predicted by certain models of string theory and field theory. Though they remain hypothetical, cosmic strings are thought to be incredibly thin, yet dense structures that could stretch across vast distances in the universe. They might have formed during the early moments of the universe, specifically during the rapid cooling phase following the Big Bang, when the universe transitioned from a state of high energy to the lower energy states that we observe today. As the universe expanded and cooled, different fields that were once unified began to break apart, leading to the formation of topological defects, such as cosmic strings. These strings could be the remnants of the early universe, created during the process of symmetry breaking, where fundamental forces and particles transitioned from a symmetric state to an asymmetric one. The properties of cosmic strings are fascinating. If they exist, they could have significant effects on the surrounding space-time, potentially warping it in such a way that it influences the formation of galaxies and other cosmic structures. As these strings move through space, they might generate gravitational waves, ripples in space-time that could be detected by advanced instruments, offering us a potential way to observe them indirectly. The study of cosmic strings, therefore, could provide valuable insights into the very conditions of the early universe, revealing the processes that shape the cosmos as we know it. Although there is currently no direct evidence of cosmic strings, they remain an important area of research. Scientists continue to explore their theoretical implications, hoping that one day they might be able to detect these structures and gain a deeper understanding of the fundamental aspects of cosmic evolution. Such discoveries could revolutionize our understanding of the universe's infancy and the complex interplay of physical forces that ultimately led to the reality we experience today. The search for cosmic strings is not just an academic pursuit. It is a journey that could unlock the secrets of the universe's most ancient and mysterious moments, offering a glimpse into the very fabric of reality itself. Cosmic strings, if they truly exist, could provide crucial insights into many of the mysteries that still elude our understanding of the universe. These elusive, one-dimensional topological defects could have profound effects on cosmic structures, matter, and energy. The presence of cosmic strings could potentially explain a variety of phenomena that we observe, phenomena that currently do not align with our established models of physics. At the forefront of these mysteries is the formation and distribution of galaxies and galaxy clusters, which display patterns of alignment and distribution that challenge existing theories and remain poorly understood. The key to understanding cosmic strings lies in their properties. They are theorized to be extremely dense and under immense tension, potentially warping space-time in ways that could have lasting effects on the large-scale structure of the universe. This warping, much like a gravitational lens, could bend the path of light from distant objects, distorting the appearance of galaxies or entire clusters of galaxies. These distortions would be particularly noticeable in phenomena like the cosmic web, a vast, thread-like structure where galaxies appear to be strung along filaments of matter, rather than dispersed evenly across the cosmos. If cosmic strings exist, they could be the missing piece of the puzzle that explains some of the strange and irregular gravitational lensing we see, as well as the uneven distribution of cosmic mass. Furthermore, cosmic strings might be intricately tied to another fascinating aspect of the universe: primordial gravitational waves. As these strings move through the cosmos, their interactions could send ripples through space-time, creating gravitational waves that could be detected by experiments designed to observe such phenomena. These waves might reveal critical details about the early universe's dynamics, especially regarding phase transitions and symmetry breaking. The existence of cosmic strings could help us refine our understanding of the universe's birth, shedding light on its formative moments when fundamental forces were taking shape. Though research into cosmic strings is still in its early stages, their potential to revolutionize our understanding of physics is undeniable. If these strange structures truly exist, they could change the way we view the universe itself. They could provide the missing link in our understanding of how the universe evolved, showing us the intricate connections between different cosmic forces. Their existence would spark new questions and drive further investigations into the nature of the cosmos, leading scientists into the uncertain realms where extraordinary discoveries may lie. Beyond cosmic strings, other topological defects are also theorized to exist, each arising from different symmetry-breaking processes that took place during the early moments of the universe. These include magnetic monopoles, domain walls, and textures, each with unique properties and potential to expand our understanding of the cosmos in different ways. Magnetic monopoles, for example, are hypothetical particles that would carry a single magnetic charge, unlike the dipoles we observe today, which always come in north and south pairs. According to grand unified theories, these monopoles could have been created during phase transitions in the early universe. Their discovery would validate certain particle physics models and offer new insights into fundamental forces and symmetries. The detection of magnetic monopoles could revolutionize our understanding of electromagnetism itself, perhaps revealing new laws of nature that govern magnetic fields. Similarly, domain walls could form as a result of symmetry breaking within scalar fields in the early universe. These two-dimensional defects occur when different regions of a field settle into distinct vacuum states, creating boundaries between them. These domain walls could have significant implications for the large-scale structure of the universe. If they exist, they could influence the distribution of matter, potentially affecting the evolution of the cosmic microwave background radiation. Their presence might even have played a role in the development of the universe's structure, helping to shape the matter that we observe today. Textures, a more complex form of topological defect, arise from fields with multiple possible vacuum states. These defects can exhibit tangled, three-dimensional structures that might influence cosmic evolution in more subtle ways. Textures could connect distant regions of space through their intricate topologies, affecting processes like galaxy formation and cosmic inflation. While the precise effects of textures remain unclear, their existence would add another layer of complexity to our understanding of the universe's early moments. Together, these topological defects present us with a unique opportunity to understand the fundamental forces that shaped the universe. As we explore these possibilities, we could uncover new information about the conditions that existed just after the Big Bang and how the universe's large-scale structure came into being. The search for these defects, whether cosmic strings, monopoles, domain walls, or textures, offers a pathway for future breakthroughs in both theoretical and observational cosmology. By studying these phenomena, we may one day gain a much deeper understanding of the profound intricacies that define the universe and its evolution. At the heart of this exploration lies the gravitational influence that these topological defects may have on cosmic dynamics. Cosmic strings, due to their immense density and tension, are expected to create gravitational fields capable of distorting space-time. This warping effect could affect the motion of nearby matter and light, creating phenomena such as gravitational lensing, where the light from distant galaxies appears distorted as it passes near a cosmic string. This could lead to observable features in the cosmic landscape, where strings act as regions of intense gravitational influence, causing galaxies and other structures to cluster in unusual ways. These gravitational interactions could act as seeds around which matter coalesces, facilitating the formation of galaxies and clusters. Similarly, domain walls and textures could affect the fabric of spacetime in unique ways. Domain walls, as boundaries between different field configurations, might create high-density regions that attract matter, promoting the formation of cosmic structures. Textures, with their tangled and complex topologies, could introduce fluctuations in the early universe that influence the dynamics of cosmic inflation and the subsequent growth of large-scale structures. These defects could contribute to the overall dynamism of the cosmic landscape, shaping the universe's evolution from its earliest stages to the present day. In essence, the study of cosmic strings and other topological defects offers a rich avenue of exploration into the nature of the universe. They could reveal new aspects of cosmic evolution, providing answers to long-standing questions about the origins of matter, the forces that govern the universe, and the dynamics of large-scale structures. As we continue to study these mysterious phenomena, we may unlock new realms of understanding that will reshape our view of the cosmos and our place within it. Moreover, the presence of defect structures in the universe may provide an explanation for some of the irregularities and anisotropies that we observe in the cosmic microwave background (CMB) radiation. The CMB, often referred to as the faint afterglow of the Big Bang, carries with it crucial information about the early universe's dynamics. It is believed that events occurring in the infant cosmos left imprints that are still detectable today, embedded within the radiation. Studying these imprints may offer profound insights into the role of cosmic strings and other topological defects, which could have played a significant role in shaping the universe as we understand it now. Thus, the exploration of cosmic strings and similar topological defects holds the potential to unlock a deeper understanding of the universe's history. It may reveal the fundamental processes that have contributed to its current structure, providing clarity on how matter, energy, and the cosmos itself came to be. As of now, however, there is no direct observational evidence confirming the existence of cosmic strings or other topological defects. Despite this, scientists have not entirely ruled out their potential existence, and research into these enigmatic structures is ongoing. The search for indirect evidence, grounded in the theoretical implications of cosmic strings and the observable phenomena associated with them, remains at the forefront of modern cosmological research. One of the most promising avenues for finding indirect evidence lies in the study of gravitational waves. If cosmic strings exist, their interactions could create a distinct pattern of gravitational waves, ripples in spacetime that propagate outward from energetic cosmic events. Scientists are optimistic that future observations might detect these waves using advanced observatories, such as the Laser Interferometer Gravitational Wave Observatory, LIGO. If gravitational waves originating from cosmic string interactions are detected, they could provide the first direct hint of these structures. Their unique signatures would help astronomers differentiate them from other sources of cosmic turbulence, offering a valuable observational tool for studying the early universe. In addition to gravitational waves, the cosmic microwave background radiation itself could serve as a window into the existence of topological defects. Variations in the temperature and polarization patterns observed in the CMB might provide further clues about the universe's early conditions. If cosmic strings or other defects influence the expansion and evolution of the universe, their presence could have left detectable imprints in this ancient radiation. Researchers are already analyzing data from the Planck satellite and other observational platforms to identify anomalies that could suggest such an influence. Another line of inquiry into topological defects comes from the large-scale structure of the universe. The distribution and clustering of galaxies may reveal subtle patterns that hint at the past existence of defects. These patterns could be the result of gravitational interactions initiated by cosmic strings or domain walls, two potential types of topological defects. Such irregularities may challenge current cosmological models, suggesting that the universe's structure is far more intricate than we currently understand. Despite the absence of direct evidence, the ongoing research into cosmic strings and other topological defects continues to expand. Each study, whether theoretical or experimental, contributes to the broader understanding of the universe's structure and evolution. As our tools and methods of observation advance, the search for these elusive features pushes the boundaries of what we know, opening new horizons in the quest to understand the cosmos. Another of the most profound and unresolved questions in modern cosmology and particle physics concerns the apparent imbalance between matter and antimatter in the observable universe, known as baryon asymmetry. According to the fundamental laws of physics, when particles interact, they typically produce equal amounts of matter and antimatter. However, observations suggest that the universe is overwhelmingly dominated by matter, with very little antimatter detectable. This discrepancy remains one of the greatest unsolved mysteries of our understanding of the universe. Several theories attempt to explain this imbalance, but no single explanation has achieved unanimous support. One leading hypothesis involves a process known as Baryogenesis. This refers to the mechanisms that might have led to an excess of baryons, matter particles, over antibaryons, antimatter particles in the early universe. Baryogenesis could have occurred under conditions that are distinct from those we observe in present-day experiments, possibly during the universe's first moments following the Big Bang. The extreme temperatures and energy levels in the early cosmos may have favored reactions that preferentially generated more baryons than antibaryons. A key aspect of baryogenesis theories is the violation of certain symmetries in particle physics, particularly the charge conjugation, C, and parity P symmetries. These symmetries, when combined, form a unified symmetry called CP symmetry. Under CP symmetry, the laws of physics should treat matter and antimatter equally. However, if this symmetry was violated during the early universe's evolution, it could explain the excess of baryons over antibaryons, leading to the matter-dominated universe we observe today. The quest to understand baryon asymmetry, like the search for cosmic strings, involves a blend of theoretical speculation and experimental investigation. While definitive answers remain elusive, the exploration of these questions continues to challenge our understanding of the fundamental forces that govern the universe. Each breakthrough, no matter how small, brings us closer to unlocking the mysteries of our origins and the nature of the cosmos. However, experiments have revealed intriguing evidence suggesting a violation of CP symmetry in certain particle decays, particularly within the realms of particles like cons and bonds. This discovery raises profound questions about the fundamental nature of the universe. The slight differences in behavior between matter and antimatter observed in these experiments might explain why there is an abundance of matter over antimatter in the observable universe, a discrepancy that has baffled physicists for decades. At the core of this mystery is the asymmetry, or imbalance, between the two, which could offer crucial insights into the very fabric of existence itself. One significant avenue of investigation focuses on various proposed mechanisms aimed at explaining this profound disparity. Among these are ideas like electroweak baryogenesis and leptogenesis, which seek to understand how specific interactions involving neutrinos or other elementary particles might have contributed to the creation of more matter than antimatter. These mechanisms, though fascinating, often delve into the realms of untested theories and physics that extend beyond the standard model, the current framework used to describe the fundamental particles and their interactions. Despite the considerable progress made in recent years, a full resolution to the question of matter-antimatter asymmetry remains elusive. It is here that modern experimental initiatives step in. Leading research centers, such as those operating at particle accelerators and neutrino observatories, are crucial in probing the properties of elementary particles to uncover potential clues about this imbalance. By exploring these issues, scientists are not just hoping to answer a specific cosmic riddle. They are also working to gain a deeper understanding of the underlying mechanisms that have shaped the very universe we inhabit. The origins of matter-antimatter asymmetry date back to the early universe, a time when the fundamental conditions of the cosmos were far different from what we see today. Several mechanisms have been proposed to account for why we observe such a pronounced abundance of matter compared to antimatter. One of the most widely discussed theories is baryogenesis, a concept that refers to the processes that led to the creation of baryons, particles that make up matter, over antibaryons, their antimatter counterparts. Several models within this framework have been put forward, each attempting to explain how the universe reached its current state. Among the leading theories within baryogenesis is electroweak baryogenesis, which posits that during a crucial phase transition in the cooling universe, known as the electroweak phase transition, conditions emerged that allowed for the violation of certain symmetries, notably charge conjugation and parity, collectively known as CP violation. This violation is thought to have created a situation where particle collisions or decays preferentially produced baryons over antibaryons. These interactions were likely governed by extreme temperatures and densities in the early universe, conditions that could have significantly influenced the rates of various particle processes. Another prominent mechanism in this search for asymmetry is leptogenesis, which suggests that neutrinos, often considered the most elusive particles in the Standard Model, might have played a crucial role in tipping the scales toward matter. According to this theory, the decay of heavy particles known as right-handed neutrinos could have resulted in an imbalance between leptons, which include neutrinos and their charged counterparts, and antileptons. This imbalance, in turn, could have led to the creation of a surplus of baryons via interactions governed by the Standard Model. Leptogenesis thus connects the often mysterious behavior of neutrinos to the larger picture of particle interactions within the universe. In addition to these mechanisms, some theoretical frameworks propose that strong CP violation, or even entirely new forces or particles, could be responsible for this imbalance. These models suggest that during the early universe, as conditions evolved and shifted rapidly, new forms of physics may have emerged, possibly interactions that remain beyond our current understanding of the cosmos. Such emerging forces could have interacted with existing ones in ways that created the necessary imbalances for matter to dominate over antimatter. Despite the wide range of hypotheses, the precise cause of the matter-antimatter asymmetry remains an open question. This ongoing research represents one of the most profound challenges in physics today. Experiments that explore high-energy collisions at particle accelerators are continually probing for potential signs of CP violation, while astrophysical observations of cosmic phenomena, such as the radiation emitted by distant galaxies or the behavior of cosmic rays, may yield clues about the conditions that existed in the early universe. These insights are not just an academic pursuit. They hold the potential to unlock some of the deepest secrets of the universe. The quest to resolve the mystery of matter and antimatter is not just about explaining why we live in a matter-dominated universe. It is about understanding the very forces and particles that govern everything around us, from the tiniest atoms to the vast galaxies that stretch across the cosmos. The existence of antimatter, for example, continues to be a captivating area of exploration. Although current observations confirm that the observable universe is overwhelmingly composed of matter, the theoretical possibility remains that antimatter could exist in separate pockets or regions beyond what our instruments have so far detected. Such a discovery would be revolutionary, offering further insights into the nature of the universe and the fundamental rules that govern it. As these investigations continue, they not only promise to answer age-old questions about the origins of the universe, but also offer a deeper understanding of the intricate and interconnected web of forces and particles that shape our reality. The existence of antimatter regions in the universe raises profound and complex questions about the very nature of reality and the fundamental forces that govern the cosmos. These questions have long intrigued scientists, driving an ongoing search for answers that could change how we perceive everything, from the origins of the universe to the balance between matter and antimatter. Theoretical models suggest that if regions of antimatter do exist, they would likely be isolated from the surrounding matter. This isolation is critical, as when matter and antimatter come into contact, they annihilate one another in an extraordinarily violent reaction. The result of such a collision is a burst of energy, with gamma rays being the most prominent form of radiation produced. This annihilation process is highly energetic, making it an unstable event for any region where matter and antimatter mix. The resulting radiation would be so intense that it would be detectable across vast distances. Thus, if large sections of the universe were dominated by antimatter, we would expect to observe significant signals of annihilation, particularly at the boundaries where matter meets antimatter. One possible origin of antimatter regions lies in the conditions of the early universe, just after the Big Bang. During this time, rapid expansion may have created localized fluctuations in energy densities, which could have led to the creation of isolated pockets of antimatter. For these regions to survive without being destroyed, the distribution of matter and antimatter would have needed to be incredibly asymmetric, allowing antimatter zones to retain their properties without being annihilated by the surrounding matter. Yet, despite these possibilities, extensive observations of cosmic background radiation and the large-scale structure of the universe have found no evidence supporting the existence of significant antimatter regions. Even the study of cosmic rays, which could potentially reveal interactions between matter and antimatter, has failed to provide any concrete signs of antimatter in large quantities. Some cosmological models suggest that if antimatter regions do exist, they are likely situated far beyond our observable horizon, making them incredibly difficult to detect. Our current inability to detect antimatter regions does not negate their theoretical possibility, but it does highlight the vast limitations of our observational tools and understanding of the universe. The search for antimatter continues to captivate scientists and researchers, and any breakthrough in this area would offer profound insights into the early conditions of the universe and the fundamental physics that shape its evolution. The interaction between matter and antimatter, should it occur on a large scale, would be nothing short of catastrophic. The process of annihilation, where a particle and its corresponding antiparticle collide and convert their mass into pure energy, would release an immense amount of radiation. According to Einstein's famous equation E = mc squared, this conversion of mass into energy results in the emission of highly energetic photons, primarily in the form of gamma rays. These gamma rays are among the most energetic types of light in the universe, capable of traveling vast distances and carrying immense power. If a quantity of antimatter equivalent to even a small object, such as a kilogram, were to collide with an equal mass of matter, the energy released would be comparable to that of a significant nuclear explosion. This energy is not limited to gamma rays alone. The annihilation process also generates a cascade of other subatomic particles, including pions, muons, and even neutrinos. The chain reaction triggered by these particles could spread, influencing nearby matter and energy, potentially causing a ripple effect across large regions of space. The radiation emitted in these events would be so intense that any nearby objects would be at risk of being obliterated, with the effects potentially extending across vast distances. In theoretical models of the universe, areas dominated by matter-antimatter collisions could become highly energetic regions in space, comparable to the phenomena observed in extreme astrophysical events such as gamma-ray bursts. These bursts represent some of the most powerful explosions in the universe and are typically linked to rapid processes involving matter and energy, such as those seen in the collapse of massive stars or other catastrophic cosmic events. While we do not currently observe these types of explosions on a large scale, likely due to the dominance of matter over antimatter, such theoretical explorations highlight the immense energy dynamics that could exist within the fabric of the universe. The study of these interactions offers a tantalizing glimpse into the extraordinary forces that could be at play in the cosmos. The exploration of matter-antimatter interactions is not just a theoretical pursuit. It also holds practical promise in a number of scientific and technological fields. One of the most exciting applications of antimatter lies in the realm of medical imaging, specifically positron emission tomography, PET scans. PET scans use positrons, the antimatter counterparts of electrons, to detect and visualize metabolic processes within the human body. By introducing a small amount of a radioactive substance that emits positrons, medical professionals can create detailed images of internal body processes. This technology has revolutionized the diagnosis and monitoring of diseases such as cancer, providing invaluable insights into the state of a patient's health. Antimatter also holds great promise for future space exploration, particularly in the development of advanced propulsion systems. The concept of antimatter propulsion is based on the incredible energy that is released when matter and antimatter collide, converting nearly all of their mass into pure energy. If harnessed effectively, antimatter could provide a propulsion system capable of achieving speeds far beyond what current rocket technologies can attain. This could revolutionize space travel, potentially allowing spacecraft to reach distant planets and stars within a fraction of the time it would take using conventional methods. However, significant challenges remain in antimatter research, particularly in the areas of production, storage, and cost. Currently, antimatter is incredibly difficult and expensive to produce in meaningful quantities, and its storage poses unique technological obstacles. Beyond practical applications, antimatter is also a vital tool in the search for answers to some of the most fundamental questions in physics. Scientists are using antimatter to explore the symmetries that underlie the universe. Experiments at facilities such as CERN are focused on understanding why the universe is overwhelmingly composed of matter, despite the fact that equal amounts of matter and antimatter were created during the Big Bang. This research could hold the key to unlocking new chapters in our understanding of cosmology and the fundamental forces that govern the universe. It may eventually lead to groundbreaking revelations about the nature of existence itself, offering insights into the balance between matter and antimatter and the fundamental origins of the cosmos. The search for antimatter, its potential existence in isolated regions, and its extraordinary properties continue to be a major focus of scientific inquiry. While antimatter remains an elusive and enigmatic component of the universe, its study offers a window into the deepest mysteries of the cosmos. As our understanding of the universe evolves, antimatter could become a key player in unraveling the fundamental workings of the universe, offering profound insights into both the past and the future of existence. Research into antimatter as a potential source of energy is steadily advancing, though it remains, for the most part, a theoretical pursuit. The energy density of antimatter is unrivaled, which is why it has captured the imagination of scientists and energy experts around the world. Antimatter, if harnessed, could revolutionize how we power our world, offering an energy source far more efficient than anything we currently possess. However, practical applications remain far from our grasp. Despite this, the allure of antimatter's potential persists, with researchers constantly pushing the boundaries of what we know about the universe and its unexplored mysteries. The idea that antimatter might one day be harnessed for energy continues to captivate, offering the tantalizing possibility of tapping into one of the most enigmatic forces in nature. The search for extraterrestrial life has long been a subject of both scientific inquiry and profound speculation. Yet, in this vast universe, teeming with billions of stars and planets, the question persists: where is everyone? This dilemma, often referred to as the Fermi paradox, presents one of the most intriguing questions in modern science. In the 1950s, physicist Enrico Fermi famously posed this question, and the paradox remains unsolved to this day. It stems from the contradiction between the high probability that intelligent extraterrestrial civilizations could exist in the universe and the complete absence of any evidence of their existence or attempts at contact with us. The more we learn about the scale of the cosmos, the more the silence becomes perplexing. One possible answer to the Fermi paradox is that intelligent life may be exceedingly rare in the universe. Despite the vast number of planets, the conditions necessary for life to evolve, especially the complex development of intelligence and technology, might be so precise and improbable that they occur only in very specific circumstances. This view suggests that while microbial life might be common across the universe, complex, technologically advanced civilizations capable of communication could be a rare phenomenon. In this scenario, the cosmos is teeming with life, but that life is mostly simple and microscopic, and the possibility of intelligent civilizations is as remote as it is fleeting. Another possibility, equally as fascinating, is that advanced civilizations do indeed exist, but they have chosen not to communicate with us. Some theories propose that extraterrestrial societies may adhere to a kind of non-interference policy, akin to a cosmic prime directive, deliberately avoiding contact with less developed civilizations. The idea is that these civilizations might wish to observe the development of other species without intervening, allowing them to evolve independently. If this is the case, we might be in a cosmic zoo, quietly observed by intelligent beings from afar, just as we watch animals in the wild without disturbing their natural progression. Alternatively, there's the hypothesis that the civilizations we search for might have already self-destructed. This scenario suggests that advanced societies, having developed the technological capacity for interstellar communication, may have destroyed themselves before ever reaching out to the stars. Nuclear warfare, environmental collapse, or uncontrolled artificial intelligence could have caused their downfall, rendering them incapable of traveling or communicating across the galaxy. If this pattern is common, the universe could be a vast graveyard of silent worlds, each one holding the remnants of civilizations that once had the potential to reach out, only to be snuffed out before they could make contact. Yet another interpretation of the Fermi paradox is that we may be living in a simulated reality, a controlled environment in which interstellar communication is deliberately restricted or monitored. In this scenario, any attempt to reach out to extraterrestrial life might be intentionally blocked or altered, making the search for alien civilizations a fruitless endeavor by design. This raises profound questions not only about the nature of our universe, but also about the very reality we experience. Each of these theories offers a unique perspective on the paradox, providing potential explanations for the silence that has characterized humanity's search for extraterrestrial life. Whether intelligent life is incredibly rare, civilizations self-destruct before reaching the stars, or advanced beings observe us from afar without interference, the answers remain elusive. The search for alien life continues to evolve, challenging our assumptions and expanding the boundaries of what we know about the cosmos. The Great Silence, the profound absence of evidence for extraterrestrial civilizations, continues to baffle researchers and enthusiasts alike. Despite the vast number of stars and potentially habitable planets scattered throughout the universe, we have found no concrete proof of other intelligent life forms. Several theories have emerged to explain this silence, each offering a thought-provoking insight into the possibilities of extraterrestrial existence. One prominent theory posits that intelligent life is exceptionally rare in the universe. While the cosmos is filled with countless stars and planets, the conditions required for intelligent life to arise might be so specific and unlikely that they occur only under extremely rare circumstances. This view suggests that while simple, microbial life may be widespread, the development of complex civilizations with technology and communication abilities might be an anomaly. In this case, the silence we hear is not due to extraterrestrial civilizations avoiding us, but because they simply do not exist. Another theory that has garnered attention is the self-destruction hypothesis. This idea suggests that technologically advanced civilizations might tend to annihilate themselves shortly after developing the ability to communicate across the stars. The reasons for this are varied, from the dangers of nuclear warfare to environmental degradation or the unchecked rise of artificial intelligence. If such civilizations repeatedly self-destruct, the universe could be filled with silent, uninhabited planets, each one once home to a species that was capable of reaching out, only to perish before they could do so. The zoo hypothesis, a concept proposed by some researchers, offers a more optimistic explanation for the silence. According to this theory, extraterrestrial civilizations may be aware of our existence, but have deliberately chosen not to make contact with us. Much like zookeepers who protect the animals in their care, these advanced beings might choose to observe humanity's development without interfering. The idea suggests that these civilizations adhere to an ethical code that respects the autonomy of less developed societies, allowing them to evolve without the influence or disruption of more advanced species. All of these theories about the Great Silence contribute to our understanding of the possibility of alien life, as well as the intricate factors that may govern the development and survival of intelligent civilizations throughout the cosmos. Whether the silence is due to the rarity of advanced life, the self-destruction of civilizations, or the deliberate non-interference of extraterrestrial observers, it forces us to reconsider the nature of life, intelligence, and communication on a cosmic scale. As we contemplate the great silence of the cosmos, the technological singularity hypothesis introduces a fascinating yet unsettling perspective. It proposes that civilizations, as their technologies progress, could evolve into forms of intelligence far beyond human comprehension. These civilizations might eventually communicate in ways we cannot even fathom today, their modes of interaction and their very essence becoming so alien to us that they remain undetectable and unintelligible. As technological capabilities advance, these entities might transform to such a degree that their presence or communications would become utterly unrecognizable to us, despite the vast potential for life scattered across the universe. This theory is a profound addition to the ongoing conversation about why, in a cosmos brimming with possibility, we are still left with nothing but the silence of space. The Great Filter hypothesis offers another layer of depth to this mystery, proposing an explanation for the absence of evidence for extraterrestrial life. It suggests that at some pivotal point in the evolutionary process, there exists a rare and highly improbable event or filter that prevents civilizations from emerging, advancing, or surviving long enough to establish contact. This filter could lie behind us, indicating that the emergence of intelligent, technologically advanced civilizations is an exceedingly rare event, one that takes place only after numerous intricate steps in the evolutionary chain. Many planets, then, might harbor microbial life, but the leap from simple organisms to complex sentient beings capable of interstellar communication might be nearly impossible. On the other hand, the Great Filter could be something that lies ahead of us in our future. In this scenario, even if intelligent life manages to emerge, it may not survive long enough to communicate with other civilizations. This interpretation suggests that the survival of such civilizations is intrinsically linked to their ability to overcome existential threats, such as climate change, nuclear warfare, or other self-destructive tendencies that may lead to their collapse. It implies that many civilizations, having reached a technological zenith, may ultimately falter and fall into oblivion before they can explore the stars or make contact with other intelligent life forms. One of the most intriguing ideas put forward by proponents of the Great Filter hypothesis is that the greatest hurdle may lie in the transition from simple, single-celled organisms to complex, multicellular life forms. This evolutionary leap could be so challenging that it drastically reduces the likelihood of intelligent life arising. Under this interpretation, microbial life would be abundant throughout the universe, but intelligent, technologically advanced life forms would be extraordinarily rare, if not virtually non-existent. If this filter does exist at such an early stage of development, it could explain the lack of detectable signals from extraterrestrial civilizations. They might never manage to make the leap from simple to complex life. Alternatively, if the Great Filter lies ahead of us, it paints a more somber picture for the future of our own civilization. It raises profound questions about our ability to survive the very challenges we face today. The growing threats of climate change, nuclear proliferation, and the destructive potential of our technologies pose significant risks to our long-term survival. These obstacles could prevent us from reaching the stars or even from enduring long enough to establish meaningful contact with other intelligent life forms. In this scenario, the cosmos would remain silent, not because other civilizations never existed, but because they too, like us, failed to overcome the challenges of their own self-destruction. The Great Filter hypothesis is more than just a thought experiment. It forces us to confront deeply philosophical questions about our place in the universe. It invites us to reflect on the fragility of our existence and the vast uncertainties surrounding the future of life on Earth. Where we find the filter, either behind us or ahead of us, could profoundly shape our understanding of the universe and our role within it. It challenges us to recognize the risks we face and consider the future trajectory of our civilization as we continue to navigate the rapidly advancing frontier of technology. In this context, the question of whether we are the only advanced civilization in the galaxy, or even in the entire universe, leads to a rich and complex tapestry of speculation and scientific inquiry. As we attempt to estimate the likelihood of our own technological singularity, numerous factors come into play. The sheer vastness of the cosmos, the frequency of planets with life-supporting conditions, and the various stages of evolutionary development required to reach intelligent, technologically advanced societies. Our Milky Way galaxy alone contains hundreds of billions of stars, and many of these stars are likely to host planets within their habitable zones, regions where liquid water and other conditions necessary for life as we know it could exist. Recent estimates suggest that there could be several billion planets in our galaxy that possess the potential to support life. This significantly increases the probability that life, in some form, could emerge somewhere in the vast expanse of the universe. Yet, even as we recognize this vast potential, we must also grapple with the complexities involved in the evolution of intelligent life. The leap from simple organisms to advanced, self-aware beings capable of technological achievement is not only complicated but poorly understood, making it difficult to assess how likely it is that we are alone in the cosmos. Further complicating matters is the question of evolutionary stages. As we consider the progression of life, we must account for the numerous potential filters that might arise at each step. The emergence of complex multicellular organisms, the rise of intelligence, and the development of technological capabilities are all critical hurdles that must be overcome for a civilization to achieve the capacity for interstellar communication. Each of these stages is marked by a mix of chance and complexity, making it nearly impossible to predict how many civilizations might succeed in navigating these challenges. Ultimately, the Great Filter hypothesis serves as a powerful lens through which we can examine the broader implications of our existence. It forces us to ask not only whether we are alone in the universe, but also how rare and fragile intelligent life truly is. Each step along the evolutionary path, from the formation of life to the development of advanced technologies, is fraught with uncertainty and risk. The path forward is not guaranteed, and whether we emerge from the filter intact or fall victim to its pressures remains an open question. In exploring the cosmos and pondering the existence of other civilizations, we may gain more than answers. We may gain a deeper understanding of our own place in the vast, silent universe. Even if other advanced civilizations do exist, there are multiple factors that could hinder our ability to discover them. The vast distances between stars and galaxies create enormous challenges, making it nearly impossible for us to detect signals from distant civilizations in real time. Time itself plays a critical role, as the window during which civilizations are detectable may be surprisingly short. Many factors could cause civilizations to rise and fall within brief periods, making their signals fleeting and difficult to detect. Furthermore, it is also possible that extraterrestrial intelligence could communicate in ways entirely beyond our current understanding, using technologies or methods that we simply cannot yet comprehend. Consequently, while statistical models, astronomical observations, and the vast number of potentially habitable planets in the universe seem to support the idea that intelligent life could be widespread, definitive evidence remains elusive. This leaves the question of humanity's uniqueness tantalizingly unresolved. Are we alone, or is intelligent life scattered across the cosmos in various forms, just out of reach? Resolving the Fermi paradox, the question of why we haven't encountered other advanced civilizations, would profoundly impact our understanding of humanity's place in the universe. It could reshape our scientific, philosophical, and cultural perspectives in ways that we might not yet fully comprehend. If we were to discover evidence of extraterrestrial civilizations, it would challenge the long-held notion that humanity is a singular, unique entity in the cosmos. Such a revelation would imply that intelligent life may be a common outcome in the universe, perhaps even a natural progression for many planetary systems. This could fundamentally alter how we view ourselves. The realization that we are not alone would foster a sense of interconnectedness with the universe. It might encourage us to see ourselves as part of a larger galactic community, where the actions of one civilization could potentially affect the whole. On the other hand, if the resolution to the Fermi paradox suggests that we are indeed the only advanced civilization, it would place a heavy burden on humanity's shoulders. Such a finding could evoke a profound sense of responsibility, as we would have to consider our role as stewards of Earth, and perhaps even as the potential pioneers of a quiet, empty universe. With no other intelligent species to share the cosmos, humanity might be tasked with preserving not just our own future, but the possibility of intelligent life ever arising again. This awareness could inspire a deeper commitment to sustainability, urging us to rethink our ecological and ethical practices. It would challenge us to make choices with long-term consequences, not only for ourselves, but for any future intelligences that might one day emerge, potentially centuries or millennia from now. We would need to ask ourselves, how do we prepare for a future that may hold nothing but silence? Moreover, the implications of either scenario, whether the discovery of other civilizations or confirmation of our solitary status, would have profound impacts on scientific pursuits. Finding evidence of extraterrestrial intelligence could ignite a new era of exploration, collaboration, and research. The prospect of learning from these civilizations, studying their technologies, and understanding their philosophies could revolutionize fields like physics, biology, and even ethics. Conversely, if we remain the sole advanced civilization in the universe, this might redirect scientific efforts toward understanding the factors that enable life to thrive or falter. This focus would provide crucial insights into how we can secure our own survival and evolution in an unforgiving and seemingly empty cosmos. Ultimately, resolving the Fermi paradox would irrevocably alter humanity's narrative in the universe. Whether we are one among many or alone in the vast expanse of space, this revelation would undoubtedly shape how we see ourselves, how we engage with one another, and how we strive to understand the universe at large. In the realm of astrophysics, magnetars stand out as one of the most extraordinary phenomena in the universe. These rare neutron stars possess some of the most powerful magnetic fields ever observed, creating an environment that challenges our understanding of physics. A typical neutron star, already an incredibly dense remnant of a supernova explosion, forms when a massive star exhausts its nuclear fuel and collapses under the weight of its own gravity. However, magnetars go a step further, featuring magnetic fields that can exceed 1,000 trillion Gauss, about 1 trillion times stronger than Earth's magnetic field. These extreme magnetic fields profoundly influence the behavior and characteristics of magnetars. They can warp the star's surface, causing it to emit intense bursts of high-energy radiation, particularly in the form of gamma rays and X-rays. These bursts are often short-lived but incredibly powerful, sometimes releasing as much energy in a few seconds as the sun does over millions of years. The magnetic fields of magnetars also lead to dramatic outbursts and flares, making them some of the most unpredictable and energetic objects in the universe. Magnetars are distinctive not only because of their intense magnetic fields, but also because of their unique behaviors. Unlike regular neutron stars, which rely on rapid rotation and moderate magnetic fields to produce periodic radiation pulses, magnetars are dominated by their magnetic forces. This gives rise to different forms of radiation and dynamic behavior. Their life cycle is equally intriguing. While magnetars are believed to form in a manner similar to ordinary neutron stars, they evolve more rapidly, with their magnetic fields weakening over time, ultimately leading them to become less active. The study of magnetars challenges our existing models of stellar evolution and magnetic fields, offering a window into the extreme conditions of the universe. They provide valuable insights into the physical laws that govern the cosmos and the complex phenomena that arise when those laws are pushed to their limits. Another fascinating concept in astrophysics is the theory of quark stars, which remain elusive yet intriguing objects within the study of stellar remnants. A quark star is hypothesized to form under extreme conditions, where the protons and neutrons that make up a regular star collapse and break down into their constituent quarks, the fundamental particles of matter. Unlike neutron stars, which consist mainly of tightly packed neutrons, quark stars would be composed of an exotic form of matter known as quark matter. This matter arises when nuclear material is compressed to such a high density that individual nucleons, protons, and neutrons lose their identity and merge into a new phase of matter. The existence of quark stars is purely theoretical, and no direct evidence has been found yet. However, they occupy a unique position in the spectrum of stellar remnants. Their properties would lie somewhere between those of neutron stars and black holes, possibly possessing characteristics, such as mass and radius, that could allow them to be distinguished through gravitational waves or electromagnetic signals. Several factors contribute to the ongoing debate about the existence of quark stars. One possibility is that they could form during extreme cosmic events such as the collapse of a supernova or the collision of neutron stars. These violent events might create the perfect conditions for the formation of quark matter, leading to the creation of a quark star. Though no direct evidence exists yet, the theoretical models and observations continue to fuel the debate and provide fertile ground for future exploration. The study of magnetars and quark stars expands our understanding of the universe, shedding light on some of the most extreme and mysterious phenomena known to science. Each discovery brings us one step closer to understanding the full range of cosmic possibilities and the forces that shape the fabric of reality itself. Quark stars, an elusive and fascinating potential class of celestial objects, may exhibit behaviors that set them apart from the more commonly observed neutron stars. These behaviors could include unique thermal emissions or specific gravitational wave signatures, offering clues to their existence. While no definitive evidence has yet been found to confirm the presence of quark stars, ongoing research into neutron star collisions, pulses, and gravitational wave detections continues to provide valuable data. The scientific community remains deeply engaged in both theoretical and observational studies, aiming to shed light on these mysterious stellar bodies. If quark stars are proven to exist, they would represent a significant challenge to our understanding of the fundamental laws of physics. These exotic stars, composed of quark matter, could reveal how matter behaves under extreme conditions, especially at the most intense densities and pressures found in the universe. Their discovery would deepen our understanding of the diversity of the cosmos and push the boundaries of current astrophysical knowledge, providing answers to some of the most profound questions in science. Meanwhile, neutron stars, another class of highly exotic and compact objects, present their own set of mysteries. Among these, the phenomenon of starquakes has captured the attention of astronomers. Starquakes occur in neutron stars that exhibit crustal disruptions similar to earthquakes on Earth. These seismic events are believed to take place in the outer crust of neutron stars, a solid layer made up of atomic nuclei and electrons. The extreme conditions within these stellar remnants, such as intense gravitational forces and rapid rotation, create a highly complex environment where even minor disturbances can lead to significant disruptions in the crust. The underlying mechanism behind starquakes is tied to the immense pressures and temperatures found within neutron stars. These stars are incredibly dense, with material packed so tightly that a sugar cube-sized amount of neutron star matter could weigh as much as several mountain ranges. Under such conditions, the crust experiences stress as a result of the gradual accumulation of strain over time. This process is similar to the movement of tectonic plates along fault lines on Earth. When the stress exceeds the strength of the crust, it causes a sudden release of energy, resulting in a starquake. These starquakes often lead to phenomena known as glitches, where the rotation speed of the neutron star suddenly increases. After a starquake, the neutron star may exhibit a temporary increase in rotational frequency, followed by a gradual slowdown. The energy released during a starquake can also have observable effects on the star's temperature and X-ray emissions, which can offer crucial insights into the star's internal structure and behavior. For astrophysicists, these observations are invaluable, helping to uncover the mysteries of neutron stars and the extreme states of matter that exist within them. Understanding starquakes also contributes to our knowledge of the intricate interactions between a neutron star's crust, core, and magnetic field. These interactions are vital for gaining a deeper understanding of the physics governing neutron stars and their role in the broader cosmic landscape. By continuing to study these remarkable events, scientists hope to unravel the complex forces that shape these extraordinary objects. In addition to these phenomena, the disappearance of stars without the typical supernova explosion is a rare but fascinating occurrence. This process, known as star quenching, can happen under specific circumstances, often involving the rapid consumption of a star's fuel. When a massive star exhausts its nuclear fuel at an accelerated rate, it can enter a state of instability. This causes the star to contract under its own gravity without producing the explosive outward pressures necessary to trigger a supernova. In such cases, the star may simply fade away, its core potentially evolving into a white dwarf. Another possibility for a star's disappearance involves the gradual consumption of its mass by a black hole. If a massive star orbits too close to a black hole, the extreme gravitational forces may strip away its outer layers over time. This process, driven by the immense tidal forces exerted by the black hole, can result in the star becoming progressively fainter, eventually disappearing as its material is drawn into the black hole, never to be seen again. In these cases, the star does not explode in a brilliant display, but is quietly assimilated by the black hole. Some intermediate mass stars may also lose significant portions of their mass due to strong stellar winds, preventing them from undergoing the usual supernova explosion. These stars, having lost enough material, may not have enough left to trigger a supernova. Instead, they may simply fade away, leaving behind only a remnant core, which could eventually evolve into a white dwarf. Furthermore, the phenomenon of stellar mergers provides another potential explanation for the disappearance of stars. In binary star systems, when two stars collide and merge, the resulting event can produce a variety of outcomes depending on the masses involved and the dynamics of the merger. In some cases, the merger may lead to a relatively quiet event, with the star disappearing from view without an explosive display. Each of these scenarios highlights the complex processes that govern the life cycles of stars, demonstrating that the universe is full of surprises and mysteries beyond conventional stellar endings. One of the most intriguing objects in modern astronomy, Taby's star, officially known as KIC 8462852, has captivated the scientific community and the public alike due to its unusual and unpredictable dimming behavior. Discovered by the Kepler Space Telescope, Taby's star exhibits fluctuations in brightness that defy the expectations of standard stellar models. Over several years of observation, astronomers noted that the star could dim by as much as 20%, a substantial decrease that raises intriguing questions about its underlying causes. One of the primary hypotheses suggests the presence of a swarm of exocomets orbiting the star. According to this theory, the transits of these icy bodies across the star's face could cause the observed dimming events. As the comets pass in front of the star, they block out a noticeable portion of its light, leading to temporary dips in brightness. While this explanation could account for some of the dimming, it does not fully explain the irregular and unpredictable nature of the brightness fluctuations observed in the star. Another, more speculative theory suggests that the dimming might be caused by the presence of a massive artificial structure, such as a Dyson sphere, built by an advanced civilization. While this hypothesis is an exciting possibility, it remains highly unlikely due to the lack of any concrete evidence supporting the existence of such technology. Still, the peculiar behavior of Taby's star continues to be a source of fascination, sparking ongoing debates about the nature of its dimming and what it might reveal about the universe. These various stellar phenomena, whether it be the potential existence of quark stars, the mysteries surrounding star quakes, or the strange behavior of stars like Taby's star, highlight the complexity and wonder of the cosmos. Each discovery brings new questions and challenges to our understanding, reminding us that the universe is far more diverse and mysterious than we can ever truly comprehend. However, the very concept of an alien megastructure surrounding Taby's star captures the profound mystery of the star itself. The star's erratic dimming patterns have sparked intense curiosity and speculation among scientists, driving them to probe deeper into the possible causes of its strange behavior. This intrigue reflects humanity's insatiable desire to uncover the unknown, as researchers explore all possible explanations, ranging from the natural to the extraordinary. Ongoing investigations continue to uncover more about Taby's star, with astronomers refining their tools and observational techniques to scrutinize its unusual fluctuations in light. Through these improvements, the scientific community aims to solve the puzzle, hoping that each new piece of data will illuminate the causes behind the star's perplexing dimming. As more observations are made, the mystery of Taby's star is not just an isolated event. It could unlock a broader understanding of stellar phenomena and push the limits of what we know about the universe. This relentless pursuit of answers speaks to humanity's fascination with the cosmos and the possibility of discovering things beyond our comprehension. In essence, the investigation into Taby's star is a vivid reminder of the vast unknowns that still await discovery, revealing how much more there is to uncover within the cosmic expanse. Gravitational waves, ripples in the very fabric of space-time, offer an equally profound window into the universe. These waves are caused by the acceleration of massive celestial objects, such as the collision of black holes or neutron stars, that disturb spacetime as they move. The concept was first predicted by Albert Einstein in 1915 as part of his general theory of relativity. When two massive objects, like black holes or neutron stars, orbit each other and eventually merge, they create disturbances that ripple outward across spacetime. Much like a stone dropping into a pond creates waves on the water's surface. These gravitational waves travel at the speed of light, carrying information about the catastrophic event that caused them, the extreme conditions in play, and the objects involved. The groundbreaking detection of gravitational waves marks a transformative moment in astrophysics, offering us a novel way to observe the universe. This method complements traditional electromagnetic observations such as light, radio waves, and X-rays by revealing cosmic phenomena that are typically hidden or undetectable using conventional methods. For example, while black holes themselves cannot be observed directly due to their inability to emit light, their merging events produce gravitational waves that can be picked up by highly sensitive instruments. The Laser Interferometer Gravitational Wave Observatory, LIGO, is one such tool designed to detect these minuscule disturbances in spacetime, allowing scientists to gather unprecedented data about some of the most mysterious and violent phenomena in the universe. Through these waves, astronomers can measure properties of the cosmic events that generated them, such as the masses, spins, and distances of the merging objects. This direct detection and analysis provide invaluable insights into the dynamics of these cosmic collisions, helping researchers refine their models of astrophysical processes. By opening a direct channel to observe extremely energetic and transient events, gravitational wave astronomy enhances our understanding of fundamental physics and the behavior of matter under the most extreme conditions. As more gravitational wave events are detected, researchers are not only focused on studying black holes, but also on investigating other astrophysical phenomena, such as neutron stars and even the earliest moments of the universe. Gravitational waves have ushered in a new era of astronomical research, introducing a completely new branch of science, gravitational wave astronomy. This field allows us to study parts of the cosmos that were once inaccessible, significantly expanding our observational reach and transforming the way we explore space. The discoveries yielded from these gravitational wave detections have been nothing short of revolutionary. By capturing signals from the mergers of black holes and neutron stars, scientists have been able to glean crucial data about these objects, including their masses, spins, and the nature of their collisions. These measurements provide important clues about the life cycles of stars, from their formation to their ultimate death, enriching our understanding of stellar evolution. One of the most remarkable findings in the field has been the confirmation of binary black hole systems. Many of the gravitational wave signals detected thus far have been the result of two black holes orbiting one another, spiraling inwards until they eventually collide. By analyzing these events, researchers have not only determined a broader range of black hole masses, but have also uncovered the existence of different pathways through which black holes form and evolve. Intriguingly, some of the black holes observed seem to be more massive than previously thought possible, challenging existing theories about how these enigmatic objects come into being. The detection of gravitational waves from colliding neutron stars has introduced another exciting dimension to our understanding of the universe. For example, the groundbreaking event known as GW10817 marked a significant milestone in multi-messenger astronomy. This event was unique because it was detected simultaneously with electromagnetic signals across a broad spectrum, including gamma rays and visible light. This rare coincidence provided invaluable insights into the creation of heavy elements like gold and platinum during the merger, linking gravitational wave astronomy directly to the origins of some of the universe's most precious elements. These discoveries, and many more, underscore the immense potential of gravitational wave astronomy. As technology advances and our ability to detect these elusive waves improves, the mysteries of the cosmos continue to unfold, diade, one ripple at a time. Gravitational waves, a phenomenon first predicted by Albert Einstein in 1915, have emerged as one of the most exciting and revolutionary discoveries in modern physics. As more gravitational wave events are detected and meticulously analyzed, the study of these cosmic ripples offers a fascinating and unparalleled glimpse into the universe's deepest secrets, especially in relation to fundamental physics and the nature of dark matter and dark energy. In fact, the ability to detect and study gravitational waves has expanded the tools at our disposal for investigating the cosmos in ways that were once thought to be beyond reach. These waves, which carry information about the most violent and energetic processes in the universe, provide a window into some of the most mysterious and difficult to study phenomena in astrophysics. The impact of gravitational waves on our understanding of general relativity is profound. As scientists detect more of these waves, they have the unique opportunity to test Einstein's theory under extreme, previously inaccessible conditions. When gravitational waves are emitted by the collision or merger of supermassive objects like black holes or neutron stars, the waves themselves contain subtle distortions that can be analyzed. These distortions can potentially validate or challenge our current understanding of spacetime, pushing the boundaries of physics further into the unknown. Gravitational waves are not only important for testing established theories, but they hold the potential to shed light on some of the universe's most enigmatic components: dark matter and dark energy. These two phenomena make up around 95% of the universe, yet remain largely invisible and elusive to traditional forms of observation. By examining the way gravitational waves interact with different cosmic structures, researchers hope to unlock new insights into these mysterious forces. For dark matter, gravitational waves offer an intriguing avenue of exploration. Though dark matter cannot be directly observed, its gravitational effects on visible matter can be detected. When gravitational waves pass through regions where dark matter is concentrated, they could be subtly altered by the presence of this invisible mass. If scientists can measure these effects, they might gain a better understanding of the distribution and nature of dark matter, which behaves differently from ordinary matter. In essence, gravitational waves could serve as indirect probes, revealing how dark matter interacts with the rest of the universe. Similarly, dark energy, the mysterious force responsible for the accelerated expansion of the universe, could be better understood through the study of gravitational waves. By observing the waves emitted from distant cosmic events, such as merging neutron stars or black holes, scientists could use these signals as standard candles, much like how supernovae are used to measure distances in space. These observations would allow researchers to track the rate of cosmic expansion over time, offering clues about the behavior and influence of dark energy on the universe's evolution. Through careful analysis of the redshift of these waves and the distances to the events from which they originated, scientists may be able to determine how dark energy has shaped the fabric of the cosmos across eons. As detection technology advances and more gravitational wave events are cataloged, an exciting possibility arises: the correlation between gravitational wave observations and the large-scale structure of the universe. This could provide vital information on how dark matter and dark energy interact to shape the cosmic web, the vast network of galaxies, dark matter, and other structures that span the observable universe. Such findings could revolutionize our understanding of how the universe evolved from the Big Bang to its current state, and how these invisible forces are sculpting the future of cosmic expansion. Despite the profound potential, it's important to note that gravitational waves alone may not directly answer the questions surrounding dark matter and dark energy. However, their role as a tool for indirect observation is undeniable. As gravitational wave astronomy progresses, scientists are confident that these ripples in spacetime will continue to illuminate the dark corners of the universe, helping us piece together a more complete picture of its composition and the fundamental forces driving its behavior. Gravitational waves are not only emitted by the dramatic events of black hole mergers or neutron star collisions, they are also produced by a variety of other cosmic phenomena, each revealing something unique about the universe's inner workings. One particularly intriguing source of gravitational waves is the merger of massive stars. As two massive stars spiral closer together in a gravitational dance, their interactions generate waves in spacetime that can be detected by observatories on Earth. This process becomes particularly intense when the stars are in close orbit, leading to a merger that may result in the formation of a supermassive black hole or a more massive neutron star. Another potential source of gravitational waves is the catastrophic event known as a supernova. When a massive star reaches the end of its life, it undergoes a violent collapse. This core collapse releases an immense amount of energy, and the resulting explosion is often asymmetrical, generating gravitational waves in the process. However, detecting these waves is no easy task. Supernovae are brief events, often occurring millions of light years away, which makes it challenging to capture the faint gravitational signals they produce. Despite these challenges, the detection of gravitational waves from such diverse events opens up new frontiers in our understanding of the cosmos. Each wave carries unique information about the objects and processes that generated it, and by analyzing this data, scientists can unravel the mysteries of the universe, from the nature of invisible dark matter to the forces that govern the life and death of stars. As we look ahead, the continued advancement of gravitational wave astronomy promises to yield transformative insights into the universe. With each new wave detected, we are one step closer to understanding the deep underlying structures of the cosmos and the hidden forces that shape it. Ultimately, the study of gravitational waves represents a journey into the very fabric of space and time, offering us a profound and exciting way to explore the universe's most fundamental secrets. The collision and merger of white dwarfs in close orbit can trigger the emission of powerful gravitational waves, ripples in spacetime that carry energy across vast distances. As these white dwarfs orbit one another, they gradually spiral inward due to the loss of energy in the form of radiation. Eventually, their merger creates a sudden release of gravitational waves, signals so profound that they could be detected by highly sensitive observatories, especially if such events occur within binary star systems relatively close to Earth. These interactions are not merely theoretical. They represent real, measurable phenomena that could provide insights into the life cycles of stars and the extreme physics governing their behavior. Furthermore, rapidly rotating neutron stars, dense remnants of massive stars, are another source of gravitational waves. These neutron stars, when part of binary systems, can generate detectable gravitational waves through their continuous interaction with companion objects. Even if a neutron star exhibits asymmetries in its shape, such as a slight deformation due to its rapid rotation, it can produce a continuous ripple in space-time. This phenomenon can yield periodic gravitational waves that are detectable by current observatories, providing valuable information about these stellar remnants and their role in the universe. On an even more elusive scale, primordial gravitational waves could hold the key to understanding the very beginning of the universe itself. These waves are thought to have been generated during the inflationary period shortly after the Big Bang. Though the detection of these early waves remains a formidable challenge, requiring technology of unprecedented sensitivity, the potential insights they offer into the universe's infancy are immense. Primordial gravitational waves could reveal fundamental truths about the forces that shaped the cosmos during its earliest moments, providing a bridge between cosmology and particle physics. As the field of gravitational wave astronomy progresses, scientists are expanding their search for signals from an ever-broadening array of cosmic events. The ongoing evolution of this field promises to uncover new facets of the universe, shedding light on phenomena that were once beyond our reach. Future gravitational wave detectors, with their advanced capabilities, will open new doors for exploration. Not only will they be able to capture signals from more distant sources, but they will also offer new ways to study events that occurred billions of years ago. One of the most exciting aspects of this evolution is the potential to observe the mergers of black holes from the distant past, events that took place long before our solar system even existed. These mergers, which send out gravitational waves across the universe, carry with them information about the formation and evolution of galaxies, stars, and black holes over cosmic time. By studying such ancient events, researchers will gain valuable insights into how the very structure of the universe has evolved since the Big Bang. In essence, gravitational waves allow us to look back in time, tracing the history of matter and energy from the earliest stages of the cosmos. As gravitational wave detectors become more advanced, their sensitivity and resolution will improve dramatically. This will allow them to not only observe waves produced by cataclysmic events, such as the merging of black holes or neutron stars, but also to detect gravitational waves from the early universe itself. These waves could provide a wealth of information about the conditions that prevailed during the first moments of the universe's existence. Such discoveries would radically reshape our understanding of the cosmos, offering new perspectives on the origins of space, time, and the very fabric of reality. Moreover, with future detectors operating in space, free from the interference of Earth's atmosphere, astronomers will be able to explore a much broader range of gravitational waves. This will enable the observation of phenomena that are currently beyond our reach, such as certain types of supermassive black holes or exotic astrophysical processes. By expanding the frequency range of detectable waves, space-based detectors will provide a more complete picture of the universe, helping to unravel mysteries that are invisible to ground-based observatories. Each new gravitational wave detected promises to add another piece to the intricate puzzle of the cosmos. With each discovery, we gain a deeper understanding of how the universe works, from its most massive structures to the tiniest quantum fluctuations. This transformative research is poised to ignite new theories and concepts that could reshape our fundamental understanding of physics itself, offering profound insights into the nature of space, time, and the forces that govern the universe. The structure of the universe is often described as a vast cosmic web, an intricate network of filaments, walls, and voids, all shaped by the force of gravity over billions of years. Early in the universe's history, shortly after the Big Bang, matter was distributed relatively uniformly. However, slight variations in density triggered gravitational instabilities that caused matter to clump together. These initial clumps began to attract more material, and over time, the universe's structure began to take shape. Dense regions of matter formed into filaments, which interconnect like the strands of a web, containing galaxies and galaxy clusters, some of the most fundamental structures in the universe. Between these filaments, vast, almost empty spaces known as voids exist. These voids can span several 100 million light years across and contain very little matter, yet they are essential to defining the large-scale pattern of the universe. Without these voids, the cosmic web would not have its current structure, and the distribution of galaxies and other matter would be vastly different. The formation of these large-scale structures is a direct result of gravitational interactions over immense periods of time. One of the key factors influencing this large-scale structure is dark matter, an invisible substance that does not emit light, but has mass and therefore exerts gravitational forces. Dark matter plays a critical role in shaping the universe by providing the gravitational framework upon which visible matter can accumulate. As dark matter interacts with ordinary matter, it helps to guide the formation of filaments and clusters, essentially sculpting the places where galaxies will form. In this way, dark matter acts as a cosmic scaffolding, shaping the very structure of the universe. It is one of the most significant, yet still enigmatic, components of the universe's overall architecture, and understanding its role is crucial for unlocking the mysteries of cosmic evolution. As we look to the future, gravitational wave astronomy is poised to offer even deeper insights into the universe's grand design. Through these ripples in space-time, we are beginning to uncover the hidden mechanisms that have shaped everything from the smallest particles to the largest galaxies, providing us with a fuller, more dynamic picture of our cosmic origins. As the universe continues to expand, its vast and intricate structure evolves in ways that affect the very building blocks of the cosmos. This expansion not only stretches the distances between distant galaxies, cosmic filaments, and voids, but it also influences how these elements evolve over time. The interplay between gravity, dark matter, and cosmic expansion drives this grand design, resulting in the large-scale structure we see today. The universe's vast architecture is a product of billions of years of complex cosmic interactions, with the forces of gravity and dark matter constantly sculpting and reshaping it. At the heart of this cosmic design are the so-called Great Wall structures. These monumental formations are not simply random patterns scattered throughout space. Rather, they represent colossal superclusters of galaxies, interconnected by filaments of dark matter and vast stretches of empty space. These superclusters are among the largest known features in the cosmos, dwarfing the size of individual galaxies. The term wall aptly conveys their immense scale, as they create boundaries within the universe's grand structure, separating the immense voids of space that exist between them. One of the most famous examples of such a structure is the Sloan Great Wall, which spans a mind-boggling 100 million light-years across. Discovered in the early 21st century, this enormous formation is a vast collection of galaxy clusters. It forms part of the larger framework that populates the universe with concentrated regions of matter. Its discovery fundamentally challenged previous notions about the universe's homogeneity. Instead of a smooth, uniform expanse, we now know that the cosmos is highly interconnected, with galaxies and clusters bound by the powerful force of gravity. This distribution of matter tells a story about the universe's creation and its ongoing evolution. The formation of these massive cosmic walls can be traced back to the very beginnings of the universe, shortly after the Big Bang. As the universe expanded from its initial hot, dense state, tiny fluctuations in the density of matter began to occur. These slight variations were the seeds from which all of the universe's great structures would grow. The force of gravity acted upon these initial fluctuations, causing matter to clump together over time. This gravitational collapse led to the formation of stars, galaxies, and eventually, large-scale structures like the Great Walls. This process took billions of years, with each step adding to the intricate and beautiful pattern that makes up the cosmos today. Understanding the formation and evolution of these Great Walls offers astronomers profound insights into the nature of dark matter, the distribution of galaxies, and the larger history of the universe. These walls provide a kind of cosmic roadmap that helps researchers understand how the universe has developed from its chaotic beginnings to its current state of dynamic expansion. By observing the walls, scientists can also gain critical information about galaxy formation, the effects of dark energy, and the complex interactions that govern the evolution of the cosmos. Every new observation offers a glimpse into the forces that shape our universe, helping us paint a more complete picture of the vast and intricate architecture of space. The evolution of the universe's large-scale structure is a remarkable story, one that stretches back over 8 billion years. After the Big Bang, the universe began as a hot, dense plasma, a chaotic soup of particles and energy. As it expanded and cooled, matter began to condense due to gravitational forces. In the earliest stages, tiny fluctuations in the density of this matter served as the seeds for all future cosmic structures. These fluctuations gradually grew larger over time, influenced by the force of gravity. In regions of higher density, gravity drew more matter in, creating the first stars and galaxies. This early period of cosmic evolution is known as the Cosmic Dark Ages. It lasted until the first stars ignited, beginning the process of reionizing the surrounding gas and marking the end of the Dark Ages. As these stars formed, they scattered heavy elements throughout the universe, enriching the cosmos and paving the way for the formation of galaxies and larger cosmic structures. Over billions of years, galaxies merged and interacted, forming massive galaxy clusters. The gravitational pull of these clusters caused long, thread-like filaments to form, which interconnected and eventually created the cosmic web we observe today. As the universe continued to expand, some areas became densely populated with galaxies, while others formed vast, empty voids. These voids, often referred to as cosmic deserts, are regions where galaxies are far less concentrated, making them stark contrasts to the rich, galaxy-packed filaments and clusters. This network of filaments, walls, and voids is what defines the large-scale structure of the universe as we understand it today. Yet, this structure is still evolving. Observations show that the universe's expansion is accelerating, likely due to the influence of dark energy, a mysterious force that counteracts gravity and causes space itself to stretch. This accelerated expansion is driving galaxies and clusters further apart, altering the dynamics of the cosmic web. Understanding the role of dark energy, dark matter, and gravity in shaping this large-scale structure is a central focus of modern cosmology. The ongoing expansion and the complex interactions of these forces continue to provide valuable data, helping scientists unravel the universe's past and predict its future trajectory. The large-scale structure of the universe is not just a fascinating subject of study for astronomers and physicists. It is a key to understanding the fundamental properties of the cosmos. By examining how matter is distributed across vast distances, scientists can gain insights into the physical laws that govern the behavior of the universe. One of the most crucial aspects of this research revolves around dark matter, an enigmatic substance that makes up approximately 27% of the total matter and energy content of the universe. Dark matter does not emit light or energy, making it invisible to traditional telescopes. However, its presence is inferred by the gravitational effects it has on visible matter. Galaxies and galaxy clusters tend to form along filaments, the same areas where dark matter is most abundant. By analyzing the distribution of galaxies and galaxy clusters, scientists can infer the characteristics of dark matter, including its role in shaping the formation of galaxies and its influence on the universe's expansion. In addition to dark matter, gravity plays an essential role in shaping the cosmos. The gravitational forces between galaxies and galaxy clusters create the large-scale structure of the universe. Understanding these gravitational effects provides scientists with clues about the mass of galaxies and the strength of the forces at work. As researchers continue to probe deeper into these cosmic phenomena, they uncover new mysteries and refine our understanding of the universe's architecture. Through these studies, the large-scale structure of the universe emerges not as a random collection of stars and galaxies, but as a dynamic, interconnected web shaped by powerful cosmic forces. From the formation of the first galaxies to the present-day configuration of walls, filaments, and voids, each discovery adds a new layer to the story of our cosmos. As astronomers continue to study these massive structures, they move closer to understanding not just the history of the universe, but its ultimate fate. The large-scale structure of the universe is not just a cosmic curiosity. It is intimately connected to the very expansion of the universe itself. This expansion, driven by the enigmatic force known as dark energy, works against gravity, continuously pushing galaxies farther apart. Understanding the rate of this expansion is crucial for refining our models of the universe's evolution. By studying how structures such as galaxy clusters and voids evolve over time, researchers can gain valuable insights into the nature of dark energy. Is it a constant, unchanging force, or does it fluctuate? This question lies at the heart of cosmological studies, as the expansion rate offers a glimpse into the deepest mysteries of the universe. The large-scale structure acts as a cosmic canvas, displaying the complex interaction between fundamental forces like gravity and dark energy. It also reveals the distribution of various types of matter across vast cosmic distances. Through detailed observations and advanced simulations, scientists are able to explore some of the universe's most profound questions. What is the ultimate fate of the cosmos? What are the fundamental building blocks of matter? And how do the laws of physics govern the reality we experience? As we dive deeper into these inquiries, the large-scale structure offers both answers and challenges, forcing us to reconsider existing theories and contemplate new ones. However, while the large-scale structure of the universe largely conforms to the expected patterns of cosmic evolution, there are anomalies that defy explanation and beckon further investigation. One of the most intriguing of these is the cold spot in the cosmic microwave background radiation, the afterglow of the Big Bang. This area appears to have an unusually low level of temperature fluctuation when compared to other regions of the sky, suggesting a significant absence of galaxy formation or perhaps an unexpected influence during the early stages of the universe's formation. Could there be an undiscovered force or event that played a role in shaping this region differently? Another perplexing anomaly involves the alignment of certain galaxy clusters and superclusters. Some of these structures seem to align with the cosmic microwave background, a phenomenon that challenges our understanding of cosmic forces. Could these alignments indicate the presence of unknown physics at work? This alignment may be the result of ancient cosmic events or interactions that have left their imprint on the distribution and orientation of galaxies across vast distances. Such a discovery could radically alter our understanding of how the universe was shaped, raising new questions about the forces that influence its structure. Moreover, the existence of large cosmic voids, regions where galaxies are sparse or entirely absent, adds another layer of complexity to our understanding of the universe. Some of these voids are far larger than current cosmological models predict. These so-called supervoids are drawing increasing attention from scientists, as their massive scale could reveal crucial insights into the nature of dark energy and the overall dynamics of the universe's expansion. The size and behavior of these voids contradict some of the predictions made by current models, suggesting that our understanding of the cosmos may be incomplete. These anomalies do not just raise questions about the large-scale structure itself, they also challenge the fundamental assumptions of cosmology. For example, the principle of homogeneity and isotropy, which assumes that the universe is uniformly distributed and looks the same in all directions, is called into question by certain observations. Some studies have shown that the distribution of galaxies is not as uniform as previously thought, with clustering patterns suggesting there may be inconsistencies in the uniformity of matter on a cosmic scale. These discrepancies invite further exploration and may ultimately lead to revisions of the foundational models that have guided our understanding of the universe for decades. Each of these unexplained phenomena presents a unique opportunity for scientific discovery. As researchers continue to probe the intricacies of the universe's structure, new insights are likely to emerge, prompting revisions of established theories and perhaps even the formulation of entirely new ones. The ongoing dialogue between observation, experimentation, and theory serves as a reminder that our understanding of the cosmos is ever evolving, shaped by new evidence and fresh perspectives. The theory of cosmic inflation provides a compelling framework for understanding the early moments of the universe's existence. According to this theory, the universe experienced a rapid exponential expansion in the first fractions of a second after the Big Bang, specifically between 10 to the power of negative 32 seconds and 10 to the power of negative 29 seconds. This period of extreme inflation would have expanded the universe by a factor of at least 10 to the power of 27, smoothing out any initial irregularities and leaving the cosmos nearly homogeneous and isotropic. Cosmic inflation not only addresses several long-standing puzzles in cosmology, such as the flatness problem, the horizon problem, and the absence of magnetic monopoles, but it also provides a crucial foundation for understanding the universe's large-scale structure. One of the key pieces of evidence supporting the theory of inflation comes from observations of the cosmic microwave background radiation. Detailed measurements taken by missions like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have revealed subtle temperature fluctuations in the microwave background. These fluctuations correspond to tiny quantum variations in the density of matter during the inflationary period, which later grew into the large-scale structures we observe today, such as galaxies and galaxy clusters. These tiny quantum fluctuations were the seeds from which the universe's intricate structure eventually blossomed, revealing a profound connection between the earliest moments of the universe and its present-day configuration. In essence, the study of the universe's large-scale structure is more than just a quest to map the positions of galaxies across space. It is a journey into the heart of cosmic forces and the very nature of existence itself. As our tools and methods for observing the cosmos become ever more sophisticated, we are likely to uncover even more anomalies and mysteries, each contributing to our ever-deepening understanding of the universe and its history. Each discovery, each new observation, only adds to the complexity of the cosmos, reminding us how much we have yet to learn about the vast, ever-expanding universe that surrounds us. Inflationary theory offers a revolutionary explanation for several cosmic phenomena, most notably the uniformity of the cosmic microwave background, CMB, across immense distances. Without the influence of inflation, regions of the universe separated by billions of light years would never have had the chance to exchange energy or information. This limitation arises due to the finite speed of light, meaning that distant parts of the universe would not have been able to share thermal energy, leading to significant temperature differences. Yet, the inflationary model neatly circumvents this problem. It proposes that, in the early moments of the universe's existence, vast regions that are now far apart were once in thermal equilibrium. A brief but rapid expansion allowed these regions to exchange energy and information before they were stretched to such extreme distances that they became effectively isolated from one another. In addition to this explanation, the theory of inflation introduces the potential for primordial gravitational waves. These waves are believed to have been generated during inflation and could serve as another vital clue to the universe's early moments. If these gravitational waves were detected, they would offer a direct signature of the inflationary epoch, providing empirical evidence of this theoretical framework. Experiments like BICEP-2 and the upcoming LIGO observations are at the forefront of this research, seeking to detect these waves and deepen our understanding of the universe's infancy. Together, these insights create a comprehensive and compelling picture of the universe's early dynamics. The theory of cosmic inflation brings together a multitude of observations and neatly explains a range of otherwise perplexing cosmic phenomena. The rapid expansion driven by inflation smoothed out any irregularities in the distribution of matter and energy, setting the stage for the nearly uniform universe that we observe today. However, this increased uniformity was not the end of the story. It laid the groundwork for the fluctuations that would later become the seeds for the large-scale structures we now see in the universe, such as galaxies, galaxy clusters, and beyond. As inflation unfolded, tiny quantum fluctuations in the energy field created regions with slightly different densities. These density fluctuations, after being stretched across vast distances, became the initial seeds for all the subsequent large-scale structures in the universe. When inflation ended, the universe transitioned into a slower, more gradual expansion, and these fluctuations began to grow under the influence of gravity. Over billions of years, regions of higher density attracted more matter, eventually forming stars, galaxies, and even larger structures like galaxy clusters. Inflation's contribution to the homogeneity of the universe is another critical aspect of the theory. The vast, rapid expansion stretched out any existing density variations to such an extent that they became undetectable on large scales. This process effectively erased any potential irregularities that could have hindered the formation of structures. Consequently, regions of the cosmos that are now separated by billions of light years would have once been in close proximity, allowing them to share similar properties. This would explain why the universe appears so uniform on large scales, with regions at opposite ends of the observable cosmos exhibiting remarkably similar characteristics. Another major outcome of inflation is its role in explaining the flatness of the universe. The theory suggests that the rapid expansion of the universe would have flattened any curvature, leading to the nearly perfect spatial geometry that we observe today. This characteristic supports the prevailing notion that the universe is in a state of critical balance, neither open nor closed, and that it continues to evolve under the influence of dark energy. This lends further credence to the idea that the universe is flat, as confirmed by various cosmological measurements. At the core of our understanding of the universe's early days, inflation is a cornerstone. The energy and dynamics associated with inflation provided a framework in which the universe's intricate structure could emerge. The end of the inflationary epoch marks a significant transition in this narrative. The rapid decay of the inflaton field, the hypothetical scalar field driving inflation, is believed to have triggered the release of energy that converted into the ordinary matter and radiation that characterized the hot, dense state of the early universe. This event, known as reheating, marked the end of the inflationary era and the beginning of what we call the hot Big Bang phase. During inflation, the inflaton field dominated the universe, fueling the exponential expansion. As the dynamics of this field shifted, its energy density began to rapidly decrease. The energy from the decaying inflaton field was converted into a multitude of particles, creating a hot and dense state composed of quarks, electrons, neutrinos, and other fundamental particles. This marked the transition from the inflationary epoch to the hot Big Bang phase, setting the stage for the universe's further evolution. Following reheating, the universe continued to expand and cool, gradually forming the building blocks of matter. As the temperature dropped, quarks combined to form protons and neutrons, which eventually came together to form light atomic nuclei in a process known as Big Bang nucleosynthesis. This took place in the first few minutes of the universe's existence, producing the lightest elements, hydrogen, helium, and small traces of lithium, that would later serve as the foundation for the formation of stars and galaxies. As the universe expanded further and cooled, it entered the epoch known as recombination, approximately 380,000 years after the Big Bang. During this period, electrons combined with protons to form neutral hydrogen atoms. This event allowed photons to travel freely through space, resulting in the release of the cosmic microwave background radiation, CMB, that we detect today. The CMB serves as a snapshot of the universe at that moment, providing a rich source of information about the conditions and structure of the universe when it was only a few 100,000 years old. It is a direct remnant of the early universe, offering crucial insights into the processes that have shaped the cosmos we observe today. Thus, inflationary theory not only resolves key cosmological puzzles, but also lays a foundation for future discoveries that could provide even more detailed insights into the universe's birth, evolution, and ongoing expansion. The rich tapestry of events that unfolded throughout the history of the cosmos set the stage for the universe as we know it today. These events began with the birth of the universe, its expansion, and the gradual formation of large-scale structures. The influence of gravity, acting over billions of years, began to shape the cosmos in ways that continue to unfold before our eyes. Yet, as we peer deeper into the mysteries of the universe, the notion of multiple periods of inflation during the early stages of cosmic development remains a hotly debated topic among cosmologists. The standard model of cosmic inflation suggests a single, rapid inflationary event. However, some alternative models propose that inflation, rather than being a one-time phenomenon, could have occurred multiple times throughout the universe's history. Each of these inflationary periods could have had its own unique characteristics, profoundly affecting the structure of the cosmos. A key motivator for considering multiple inflationary episodes comes from certain theoretical frameworks, such as chaotic inflation and eternal inflation. Chaotic inflation, a theory with far-reaching implications, suggests that inflation is not a singular event, but rather something that could occur repeatedly, albeit in different regions of space. This happens because of variations in the inflaton field, the hypothetical field responsible for inflation. In this scenario, some regions of the universe might experience brief inflationary bursts, while other areas could remain in a state of ongoing inflation for extended periods. This could, in turn, lead to the formation of what is called the multiverse, a concept wherein numerous bubble universes emerge, each governed by its own unique set of physical properties. On the other hand, the theory of eternal inflation posits that the inflaton field never settles into a stable state across the entirety of the universe. Instead, certain regions of space stop inflating, while others continue to do so indefinitely. This asymmetrical behavior suggests that the universe could consist of an infinite number of inflationary bubbles, each with its own laws of physics, space-time structures, and even dimensional properties. If true, these ideas would give rise to a multiverse where every bubble universe follows a distinct evolutionary path. The implications of these recurring inflationary periods are far-reaching. If such phenomena exist, they could offer explanations for some of the universe's most puzzling observations, including the uniformity of the cosmic microwave background, CMB. The CMB, which serves as a snapshot of the universe's earliest moments, could be better understood through the lens of multiple inflationary events. These events might also help explain the large-scale structures that we observe today. galaxies, clusters of galaxies, and the vast voids between them. Understanding these processes could help us answer crucial questions about the origins and fate of the cosmos. However, despite their intriguing nature, the concept of multiple inflationary periods remains speculative. Researchers in cosmology are exploring both theoretical and observational avenues to test these ideas. Current and future data, such as more precise measurements of the cosmic microwave background and potential observations of primordial gravitational waves, could offer valuable insights that allow us to distinguish between models that predict single inflationary events and those that foresee multiple episodes of inflation. As we continue to probe deeper into these cosmic phenomena, our understanding of the universe's early evolution could undergo a profound transformation. The effects of inflation go beyond explaining the universe's formation. They also provide us with a glimpse into its possible fate. Cosmic inflation holds significant implications for how we perceive the long-term evolution of the universe and its ultimate structure. The rapid expansion of space during the inflationary epoch played a pivotal role in setting the stage for the observed uniformity in the cosmic microwave background. However, it also influenced the dynamics of matter, dark energy, and the overall expansion of the universe. One of the most significant relationships that inflation has is with dark energy, the mysterious force believed to be responsible for the accelerated expansion of the universe. The inflationary model suggests that after the initial inflationary phase, the universe entered a more stable phase of gradual expansion. Yet, if dark energy continues to dominate the energy density of the universe, it will likely cause the universe to expand indefinitely. This outcome is often referred to as the Big Freeze, or heat death. In this scenario, galaxies would move farther apart over trillions of years, and the universe would cool down. Stars would eventually burn out, and galaxies may fade into the darkness, leaving behind a cold, sparse, and desolate cosmos. On the flip side, if inflation leads to a multiverse, each bubble universe within that multiverse might follow its own unique developmental trajectory. Some regions could experience rapid expansion, while others might evolve in completely different ways, governed by alternate physical laws. This concept presents the idea that the ultimate fate of our universe is just one of many possible outcomes, each dictated by the specific characteristics of the universe it inhabits. Such a view aligns with certain interpretations of quantum mechanics, where infinitely diverse possibilities emerge depending on the initial conditions set during inflation. Furthermore, some models suggest that the universe might not follow a singular path at all. Instead, it could undergo a series of cyclical expansions and contractions, repeatedly inflating and collapsing. This cyclical model presents a stark contrast to the conventional view of a linear, monotonous progression toward a cold, empty universe. If this hypothesis is correct, the universe's fate could be much more dynamic than previously imagined, with cycles of death and rebirth occurring over unimaginable stretches of time. Ultimately, the effects of cosmic inflation on the universe's future remain a profound area of inquiry. As both observational techniques and theoretical models continue to advance, new discoveries may allow us to determine whether our universe is on a path toward eternal expansion, a cyclical fate, or some entirely unknown destiny. At the heart of our understanding of the cosmos lies the theory of gravity, first formulated by Albert Einstein in the early 20th century. According to general relativity, gravity is not a force that acts at a distance, but rather a curvature of space-time itself. Massive objects, such as planets, stars, and galaxies, distort the fabric of space-time around them, creating a well that affects the motion of other objects within it. This means that objects like planets do not simply feel a force from other objects in a conventional sense. Instead, they move along the curved paths dictated by the shape of space-time itself. A common analogy used to illustrate this concept involves imagining a heavy ball placed on a stretched rubber sheet. The ball creates a depression in the sheet, causing smaller objects to roll toward it, mimicking how gravity influences the motion of planets and other celestial bodies. This concept also explains phenomena such as gravitational lensing, where light bends around massive objects, providing another testament to the power of general relativity. While general relativity provides a comprehensive framework for understanding gravity on large scales, questions remain about how gravity functions at the quantum level, where particles behave according to the rules of quantum mechanics. At these tiny scales, particles are governed by fields and probabilities, leading physicists to propose that a particle called the graviton might mediate gravitational interactions in the same way that photons mediate electromagnetic forces. This remains an area of active research, as scientists continue to explore the potential connection between gravity and quantum theory, hoping to reconcile these two pillars of modern physics. However, the graviton remains a theoretical concept, a hypothetical particle that could potentially unite the realms of gravity and quantum mechanics. As of now, no comprehensive theory has successfully bridged the gap between these two fundamental frameworks of physics. The search for such a unifying theory continues to be one of the most elusive goals in theoretical physics. Theories like string theory and loop quantum gravity have emerged, each proposing different models to describe the fundamental nature of gravity. This pursuit of understanding gravity at the most foundational level is not merely an intellectual exercise, but has profound implications for our broader comprehension of the universe. It promises to shed light on some of the most enigmatic phenomena, such as the behavior of black holes, the dynamics of galaxies, and the very fabric of space-time itself. Every advancement in this field brings us closer to potentially unlocking deeper layers of reality, revealing secrets hidden within the cosmos that could transform our understanding of existence itself. At the core of this exploration lies the relationship between gravity and the curvature of space-time, a central concept of Albert Einstein's groundbreaking theory of general relativity. Unlike the Newtonian view of gravity as a force acting between masses, general relativity reimagines gravity as a manifestation of the curvature of spacetime caused by the presence of mass and energy. According to this theory, the distribution of mass in the universe causes spacetime to curve, and this curvature governs the movement of objects, including light. This revolutionary shift in perspective dramatically alters our understanding of how massive objects interact and how they influence the paths of other objects. When a massive object, such as a planet or a star, is placed in the fabric of spacetime, it causes a distortion. Imagine spacetime as a stretched-out rubber sheet. Placing a heavy object like a ball on the sheet causes it to sag, creating a depression. This is similar to what happens in the actual universe, where the presence of mass deforms spacetime. Smaller objects, such as satellites or moons, are then influenced by this curvature, following the paths dictated by the bends and dips in spacetime. This is what we perceive as orbital motion, such as the elliptical orbits of planets around stars. The extent of this curvature depends on the mass of the object and the density of the surrounding space. Heavier objects create deeper and more intense distortions in spacetime, which in turn produce stronger gravitational effects. Light, which naturally follows the shortest path through spacetime, called a geodesic, also feels the effects of this curvature. When light passes near a massive object like a galaxy or a black hole, the curvature of spacetime causes the light to bend, a phenomenon that scientists observe as gravitational lensing. This bending of light allows astronomers to study objects and events in the universe that would otherwise be hidden from view. Einstein's theory of general relativity has transformed our understanding of gravity, offering a comprehensive framework for explaining various gravitational phenomena, from the precession of planetary orbits to the behavior of objects in extreme gravitational fields. It also provides critical insights into the nature of black holes, those mysterious regions of spacetime where gravity becomes so intense that not even light can escape. General relativity underscores the interconnectedness of mass, space, and time, revealing that gravity is not just a force, but an intrinsic feature of the universe's underlying structure. The Einstein field equations, which govern these principles, continue to be the cornerstone of modern cosmology, helping us decode the nature of reality itself. Another fascinating aspect of modern theoretical physics is the idea of extra dimensions, dimensions beyond the three spatial ones that we experience in our everyday lives. Advanced theories like string theory and models of higher dimensional spacetime suggest that additional spatial dimensions could exist, but they remain hidden from direct observation. These theories propose that the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings or membranes, and that to fully understand their behavior, we need to consider more than the familiar 3 dimensions. String theory, for instance, requires 10 or 11 dimensions to maintain mathematical consistency, and these extra dimensions may be compactified or curled up so tightly that they are imperceptible at everyday scales. In these frameworks, the extra dimensions have the potential to affect the properties of particles, including their mass and charge, by altering the way the strings vibrate within them. The discovery of such extra dimensions could help resolve some of the long-standing puzzles in physics, particularly the unification of the fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces. One intriguing possibility is that the weakness of gravity compared to the other forces could be explained by the way it interacts with extra dimensions. If gravity propagates through these hidden dimensions, while the other forces remain confined to our familiar 3-dimensional space, it might account for gravity's relative weakness at large scales. This concept is encapsulated in the brane world scenario, which suggests that our observable universe is a 3-dimensional brane embedded within a higher dimensional space. While these ideas are mathematically compelling and could offer solutions to some of physics' most pressing questions, direct experimental evidence for extra dimensions is still lacking. Physicists are actively searching for signs of these hidden dimensions, conducting high-energy experiments at facilities like the Large Hadron Collider. One potential way to detect extra dimensions is through the observation of unusual particle behaviors or the production of miniature black holes, both of which could provide tantalizing evidence of higher dimensional spaces. As these theories evolve and our technology advances, the quest to understand gravity, space-time, and the hidden dimensions of the universe is only just beginning. The answers we uncover could not only redefine our conception of gravity, but also open up entirely new realms of possibility in our understanding of the cosmos. Cosmological observations, alongside the study of gravitational waves, are opening up new avenues in our understanding of the universe, potentially offering tantalizing clues about the nature of reality that could lead us to uncover the existence of extra dimensions. These hidden dimensions, if proven to exist, would not only deepen our comprehension of the cosmos, but could fundamentally alter our entire worldview. The exploration of such dimensions challenges the very framework of how we perceive space, time, and existence itself, posing profound philosophical questions about the limits of human understanding. At the core of this exploration lies quantum gravity, an ambitious field aiming to unite 2 fundamental theories that have long shaped our understanding of the universe: general relativity and quantum mechanics. General relativity, the cornerstone of classical physics, governs the behavior of massive objects in the cosmos, describing the curvature of space-time around stars, planets, and black holes. Quantum mechanics, on the other hand, governs the microscopic world, where particles at the atomic and subatomic levels behave in ways that defy traditional notions of reality. Despite their immense success in their respective realms, these 2 pillars of physics remain fundamentally incompatible when applied to certain extreme conditions, such as the singularities at the heart of black holes and the early moments of the universe, where both gravity and quantum effects are at play. The quest for quantum gravity seeks to bridge this gap, developing a theory that can merge these 2 perspectives into a single, coherent framework. A key component of this quest is the idea that space-time itself is not a smooth, continuous entity, as described by general relativity, but instead is a dynamic, quantized structure. This notion suggests that space-time could be made up of discrete units or chunks at the smallest scales, particularly at the Planck scale, an unimaginably tiny realm where the laws of physics as we know them break down. This new picture of space-time challenges our long-standing assumptions about the very fabric of the cosmos, leading to a dramatic rethinking of the universe at its most fundamental level. Various models have emerged to address this radical new perspective, with 2 of the most prominent being loop quantum gravity, LQG, and string theory. Loop quantum gravity proposes that space-time is quantized into tiny loops or networks of quantum fields. These loops form the very structure of the universe, allowing gravitational fields to take on discrete values rather than existing as a smooth continuum. This framework aims to describe gravity in a way that does not rely on the classical geometric interpretation of space-time, opening the door to new insights into how gravity operates at the quantum level. String theory, another major contender, offers a different approach. It posits that the fundamental building blocks of the universe are not point-like particles as we have traditionally envisioned, but rather one-dimensional strings. These strings vibrate at different frequencies, and the specific patterns of their vibrations correspond to the various particles that make up the universe. In this view, gravity is inherently incorporated into the fabric of reality through the presence of gravitons, hypothetical quantum particles that mediate gravitational interactions. String theory, therefore, presents a potential way to unify the forces of nature, offering a framework that could seamlessly incorporate both quantum mechanics and gravity. If either of these theories, loop quantum gravity or string theory, proves to be correct, it could resolve some of the most perplexing mysteries of modern physics. For example, quantum gravity might provide a deeper understanding of the singularities that occur inside black holes, where our current models of physics break down. It could also offer insights into the so-called black hole information paradox, a long-standing conundrum that questions whether information that falls into a black hole is truly lost to the universe or if it can somehow be recovered. A coherent theory of quantum gravity might, in turn, lead to a unified description of all four fundamental forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, providing a deeper and more complete understanding of the universe's inner workings. As researchers continue to probe these theories, the search for quantum gravity remains one of the most exhilarating and intellectually challenging frontiers of contemporary physics. The potential to unify the laws of the cosmos offers not only a grand vision of the universe's fundamental structure, but also opens up profound questions about the nature of space, time, and reality itself. One of the most intriguing implications of this theoretical exploration is the holographic principle, a bold idea that suggests the entire three-dimensional universe we perceive might be an illusion, merely a projection of information encoded on a distant two-dimensional surface. This perspective radically alters our understanding of space and time, proposing that the information contained within a volume of space is not stored within the volume itself, as we might intuitively think, but rather correlates with data on its boundary. In this view, the entire cosmos, with all its stars, galaxies, and black holes, might be fundamentally two-dimensional, with our perception of three-dimensional space being merely a projection of this encoded data. One of the most remarkable consequences of the holographic principle is its connection to black holes. According to this theory, when matter and energy fall into a black hole, the information about these objects is not lost, but instead encoded on the black hole's event horizon, the boundary surrounding the black hole. This insight is deeply rooted in the principles of quantum mechanics, which state that information cannot be destroyed. The holographic principle thus offers a possible resolution to the black hole information paradox, suggesting that rather than vanishing into nothingness, the information about objects swallowed by black holes may be preserved, albeit in a different form. In addition to its implications for black holes, the holographic principle also provides a fresh perspective on gravity itself. By reimagining the structure of space-time as a projection, it challenges traditional concepts of how gravity operates, suggesting that the gravitational force we observe in our three-dimensional universe may be the result of interactions taking place on a much lower dimensional surface. This idea forces us to reconsider our most basic assumptions about the nature of space, time, and the forces that govern them, inviting a new era of thought in the field of theoretical physics. The search for quantum gravity and the exploration of extra dimensions, coupled with the holographic principle, represents some of the most profound and groundbreaking questions in modern science. If these theories hold true, they could not only unlock the deepest mysteries of the cosmos, but also usher in a new era of scientific understanding, where the boundaries of space, time, and reality are no longer confined by the limits of our current knowledge. The journey to uncover these truths is ongoing, and with each new discovery, we move ever closer to a deeper, more unified understanding of the universe. Furthermore, this principle suggests that the very fabric of space and time, as we experience them daily, might not be as fundamental as we once believed. Instead, they could be emergent phenomena, a byproduct of deeper underlying informational processes. If this is true, our understanding of the universe, indeed of reality itself, might be fundamentally reshaped. Space and time in this framework would no longer be immutable, all-encompassing entities, but rather complex consequences of interactions within a vast cosmic system, akin to the workings of an intricate database. This revelation challenges our deepest assumptions, urging scientists to rethink the building blocks of the cosmos and consider that, at the most fundamental level, reality itself could be more like a vast informational network than a fixed and unchanging stage on which events unfold. The implications of this idea stretch far beyond theoretical musings. They push forward the exploration of groundbreaking concepts in theoretical physics and cosmology, urging researchers to question everything, from the most minute particles to the largest galactic structures. These ideas prompt us to reconsider the very nature of existence, leading to profound shifts in how we visualize the universe and its components. The holographic principle, which is intricately connected to this emergent model of space and time, invites scientists to reframe our understanding of the interplay between matter, energy, and the underlying structure of space-time itself. It pushes the boundaries of what we know, urging us to see the universe not as a static entity, but as an evolving process, a vast network of information constantly reshaping and reorganizing itself. In contemplating the future of the universe, one of the most pressing and perplexing questions is its ultimate fate. This destiny hinges on a delicate interplay of factors, chief among them the universe's rate of expansion and the total amount of matter and energy it contains. From the moment of the Big Bang, the universe has been expanding, a phenomenon that continues today. More recent observations, however, have revealed that this expansion is accelerating, driven by a mysterious force known as dark energy. The discovery of this elusive force has profound implications, suggesting that the universe might expand forever, growing increasingly distant and cold. If the current rate of acceleration continues, the universe could eventually enter a phase known as the Big Freeze. In this scenario, galaxies would drift farther apart, their once close relationships torn asunder. Stars, the brilliant beacons of light that dot the cosmos, would burn out one by one, their energy exhausted. Over time, the universe would grow darker and colder, slowly becoming a barren expanse, devoid of the structured cosmic phenomena that currently define it. Stars and galaxies would become distant memories, their remnants scattered across an empty void, leaving behind only isolated remnants like white dwarfs or black holes. The universe, once teeming with life and activity, would ultimately become a silent, frozen wasteland, its once vibrant energy reduced to a faint, distant echo. On the other hand, there is the possibility of a much darker scenario, the Big Crunch. This would occur if the gravitational pull of all the matter in the universe were powerful enough to overcome the relentless expansion driven by dark energy. If that were to happen, the universe would cease expanding and begin contracting, pulling everything back together in a dramatic reversal of the Big Bang. This contraction could culminate in the collapse of all matter into a singularity, a point of infinite density, reminiscent of the state of the universe before the Big Bang. However, current observations indicate that dark energy is dominating the dynamics of the cosmos, making this scenario increasingly unlikely. The force of dark energy appears to be overwhelming the gravitational forces that would be necessary for a big crunch, leaving us with the tantalizing possibility that the universe may continue expanding indefinitely. This ongoing debate about the fate of the universe is not just a matter of physics. It is a deeply philosophical question. As scientists probe deeper into the properties of dark energy and other cosmic components, our understanding of the universe's destiny evolves. Will the universe continue to stretch outward, endlessly expanding and cooling into a state of lifelessness? Or will some unforeseen force intervene, causing the universe to contract, perhaps even leading to a cyclical rebirth of sorts? These questions are among the most profound enigmas in cosmology, sparking endless debates and inspiring new lines of inquiry into the nature of existence itself. Looking far ahead into the future, trillions of years from now, the potential outcomes become even more surreal and speculative. If dark energy continues to fuel the acceleration of the universe's expansion, the cosmos will eventually become an expanse marked by utter isolation. Galaxies will continue their drift, eventually so far apart that the once grand structures of the universe will become invisible against the backdrop of an ever darker sky. Star formation will cease as the remnants of old stars, white dwarfs, neutron stars, and black holes dominate the landscape. Over incomprehensible spans of time, even these stellar remnants will cool and fade, leaving behind only a cold, dark, and lifeless universe. In this distant future, black holes, those mysterious regions of space-time where gravity is so intense that not even light can escape, would likely become the most significant features in the universe. As stars burn out and galaxies become distant memories, the black holes, with their insatiable gravitational pull, would continue to consume matter and grow ever larger. The universe would become a place where only these enigmatic objects remain, their mysterious event horizon boundaries serving as the final vestiges of a once vibrant universe. These black holes might eventually merge, creating even larger and more massive structures, but this too would be a slow, fading process, as all matter is drawn into their depths, leaving a cosmos that is eerily silent and still. This vision of the future is a stark reminder of the transience of everything we know. From the moment the Big Bang set everything into motion, the universe has been on a relentless journey toward its ultimate fate. Whether that fate is a cold, dark, and distant freeze or a fiery implosion into a singularity remains one of the most profound mysteries of modern cosmology. Regardless of the outcome, the question of what will become of the universe forces us to confront the very nature of time, space, and existence itself, challenging us to rethink everything we know about the cosmos and our place within it. However, even black holes, which are often perceived as invincible cosmic entities, are not eternal. Over the course of trillions of years, they are predicted to gradually disappear through a process known as Hawking radiation, a phenomenon theorized by physicist Stephen Hawking in the 1970s. This process involves black holes emitting faint radiation, which slowly leads to their mass and energy diminishing until they eventually vanish entirely. The idea that even the most massive black holes will eventually evaporate is profound, suggesting that no part of the universe is truly permanent. As this radiation dissipates, it contributes to an increasingly frigid cosmic environment, further cooling the universe. As time stretches into the unimaginable future, the universe might ultimately reach a state known as heat death. This scenario describes a universe in which all energy is evenly distributed, creating a state of thermodynamic equilibrium. In such a state, there would be no significant events or changes, no stars burning, no galaxies colliding, no life forms thriving. The cosmos would become eerily quiet, with no dynamics to stir the cold expanse. It is a deeply thought-provoking possibility, one that challenges our understanding of existence and leaves us pondering the long-term meaning of cosmic evolution. In such a universe, time itself may seem to stretch out infinitely, but without the vibrancy and complexity that we associate with life and change. The potential endings of the universe, often envisioned as either the Big Rip or heat death, represent two starkly contrasting futures. These scenarios are shaped by the fundamental forces and energy dynamics at play in the cosmos, particularly the mysterious force known as dark energy. Dark energy is the driving factor behind the accelerated expansion of the universe, and it remains one of the most profound enigmas in modern cosmology. The Big Rip is a captivating theory that envisions a future in which the universe's expansion continues to accelerate uncontrollably. In this scenario, the force of dark energy becomes so dominant that it begins to overpower every other force in the universe, from the gravitational pull holding galaxies together to the forces that bind atoms. As this acceleration intensifies, structures at every scale, from massive galaxy clusters to the tiniest subatomic particles, would eventually be torn apart. This catastrophic unraveling would occur over a timeline that could span billions of years, culminating in a universe where everything, matter, energy, and space itself, is ripped apart in a dramatic and irreversible finale. In contrast, the heat-death scenario is grounded in the concept of thermodynamic equilibrium. This scenario unfolds on an incredibly long timescale, stretching far beyond the current age of the universe. As stars burn out and galaxies drift farther apart, the universe would slowly move toward a state where all energy is evenly distributed across space. In this cold, dark future, there would be no stars shining, no life forms evolving, and no significant interactions taking place. The universe would become a stable, static expanse, devoid of any structure or change, much like an empty theater after the final curtain has fallen. It would be a universe in which nothing happens, a place of absolute stillness and unchanging uniformity. When we think about which of these two scenarios is more plausible, it is important to consider what we currently know about the universe. Observations suggest that dark energy is indeed accelerating the expansion of the cosmos, yet the true nature of dark energy remains one of the biggest unsolved mysteries in cosmology. Depending on how dark energy behaves over the coming billions of years, it could lead us toward either a big rip or a gradual heat death. The unfolding of either scenario is largely dependent on the long-term evolution of dark energy, a force whose exact properties we have yet to fully understand. As research continues, the questions surrounding the ultimate fate of the universe only grow more profound, highlighting the complex interplay of forces that will eventually determine the destiny of everything that exists. Another significant challenge for cosmologists is determining whether the universe is finite or infinite in extent. Both possibilities have far-reaching implications for how we understand the cosmos. Current measurements, including those of the cosmic microwave background radiation, suggest that the universe is incredibly vast and may appear flat, meaning that on a large scale, its geometry does not curve inwards or outwards. Yet, whether this vastness extends infinitely or loops back on itself remains an area of active exploration. If the universe is finite, it would imply a definite volume of space, with limits to the matter, energy, and structures that we observe. In this scenario, the universe might take the form of a higher dimensional sphere or another geometric shape, where traveling far enough in one direction could eventually bring you back to your starting point. This concept leads to intriguing philosophical questions about the nature of boundaries. Does the universe have an edge or a boundary? And if so, what lies beyond it? Such a finite universe raises fundamental questions about existence itself, challenging our intuition and forcing us to reconsider what beyond the universe might mean. Could there be something outside of it, or is the universe truly all there is? These questions have profound implications for how we think about space, time, and our place in the cosmos. Conversely, the concept of an infinite universe presents a mind-bending view of existence, suggesting that space stretches endlessly in every direction, filled with an immeasurable, potentially boundless distribution of galaxies, stars, and interstellar matter. An infinite cosmos challenges our understanding of reality, offering a radical perspective on the nature of the universe itself. It implies that no matter how far one travels, new regions of space are always waiting to be explored, each teeming with possibly infinite variations of cosmic phenomena. This notion aligns with the idea of infinite possibilities, where every conceivable combination of matter and energy could exist somewhere in the vastness of the cosmos. The implications of a finite versus an infinite universe extend far beyond mere measurements or geographical distances. They strike at the heart of philosophical questions about existence itself, probing our understanding of the universe's origins, its ultimate destiny, and our place within it. A finite universe might hint at a clear beginning and an eventual end, possibly suggesting a specific moment of creation and a conclusive fate. In contrast, an infinite universe challenges conventional ideas about singularity, prompting us to reconsider the ultimate nature of space, time, and reality. As scientists strive to unravel these profound mysteries, their quest for understanding illuminates the delicate interplay between observation, theory, and the fundamental laws governing the universe. Their investigations point to deeper questions about the very fabric of space and time, urging us to reconsider what we know about the cosmos. Based on current knowledge and observations in cosmology, several possible scenarios have emerged regarding the ultimate fate of the universe. Each scenario is intricately tied to the ongoing expansion of the universe, the mysterious force known as dark energy, and the density of matter and energy that permeates all of existence. One of the leading theories is the Big Freeze, which predicts that the universe will continue expanding at an accelerating pace. This scenario is primarily driven by dark energy, a force that is pushing galaxies further apart at an ever-increasing rate. Over time, this relentless expansion would cause galaxies to drift farther from one another, stars to burn out, and matter to become increasingly diffuse. Eventually, the universe would settle into a state of thermodynamic equilibrium, where it would experience a gradual cooling over trillions of years. In this future, cosmic activity would dwindle, leaving behind a dark, cold, and empty universe where only the remnants of stellar processes, faint traces of once vibrant stars, lurk in the void. On the other hand, the Big Rip presents a far more dramatic and cataclysmic scenario. This hypothesis suggests that if dark energy continues to grow unchecked, it could eventually overcome all other forces in the universe, leading to an exponential increase in the rate of expansion. Such an increase would ultimately tear apart everything: galaxies, stars, planets, and even atoms, disintegrating the very fabric of the cosmos. This end, although seemingly catastrophic, is one of the speculative possibilities derived from our current understanding of dark energy and the forces at work in the universe. Another potential fate is the Big Crunch, a scenario that could unfold if the density of matter in the universe were sufficient to halt its current expansion. If gravitational forces were strong enough, they could reverse the universe's expansion, causing everything to collapse inward. In this outcome, all matter and energy would converge, eventually reaching a singularity, a state of infinite density and gravity, similar to the conditions at the beginning of the universe. Although current observations suggest that the universe's expansion is accelerating, future shifts in the dynamics of dark energy could bring the Big Crunch into consideration for certain cosmological models. Each of these theories reflects the profound complexity of cosmic evolution, as well as the enigmatic nature of dark energy, a force that continues to baffle researchers. As scientists gather more data and refine their models, the search for answers about the ultimate fate of the universe not only seeks to answer pressing scientific questions, but also promises to unlock deeper truths about the cosmos and our role within it. Turning from the distant reaches of the universe to the intimate origins of Earth's own companion, the Moon, we find that its genesis is most commonly explained by the giant impact hypothesis. According to this theory, the Moon was formed from the debris resulting from a colossal collision between the early Earth and a Mars-sized body, often referred to as Theia. This cataclysmic event is believed to have occurred approximately 4.5 billion years ago, shortly after the formation of the solar system. Following this impact, a significant amount of material was ejected into Earth's orbit. Over time, this debris gradually coalesced and eventually formed the Moon we see today. The giant impact hypothesis offers a compelling explanation for several key characteristics of the Moon. For instance, the composition of lunar rocks brought back to Earth by the Apollo missions reveals striking similarities to Earth's own materials, particularly in their isotopic signatures. This suggests that the Moon did not originate from a separate body in the solar system, but was instead formed from Earth's outer layers. Furthermore, the unique size ratio of the Moon to Earth further supports this theory. The Moon is relatively large compared to Earth's size, especially when compared to the size ratios of other moons in the solar system, further distinguishing it as a special case. Simulations and computer models of the giant impact have further clarified the plausibility of this scenario. These models show how the impact could have caused both Earth and the colliding object to enter a molten state, allowing for the amalgamation of materials that eventually cooled and solidified into the Moon. In fact, These models demonstrate how the material ejected into space from the impact would have settled into orbit around Earth, eventually forming the familiar satellite that has accompanied our planet for billions of years. Thus, the story of the moon's formation is not only a tale of a violent cosmic collision, but also a testament to the complex processes that govern the evolution of celestial bodies. As our understanding of both the universe and our own solar system continues to evolve, the exploration of these cosmic origins offers an ever-expanding window into the past, and perhaps even into the future. As the moon gradually stabilized in its orbit, it began to undergo a series of profound processes that would shape its very structure and surface. One such process, known as differentiation, played a pivotal role in developing the moon's internal architecture, while volcanic activity, another key factor, helped give rise to the expansive basaltic plains that we recognize today as the Maria. These events, seemingly quiet in their origins, were crucial in not only molding the moon, but also in offering crucial insights into the early solar system's formation. By understanding the moon's evolution, we gain valuable knowledge about the dynamic and complex forces that shaped the planetary bodies in our celestial neighborhood. The moon's near side and far side present a strikingly different picture, a contrast that can be attributed to a fascinating phenomenon called tidal locking. This occurs when the gravitational forces between the Earth and the moon become so intricately tied that the moon rotates on its axis in exactly the same amount of time it takes to orbit our planet. This synchrony results in the same side of the moon, its near side, always facing Earth, while the far side remains hidden from direct view. Such a phenomenon has profound effects on the geological makeup of the moon's surface. The near side of the moon, exposed to Earth's gravitational pull, is home to vast, smooth expanses known as the Maria. These dark, basaltic plains were formed by ancient volcanic eruptions where lava flows filled vast impact basins. Volcanism was more prevalent here due to the thinner crust, allowing volcanic activity to shape much of the surface. The near side also contains larger lowland areas where these eruptions occurred, giving it a distinct appearance compared to the far side. On the other hand, the far side presents a stark contrast. Its surface is heavily cratered, marked by the passage of time and countless impacts, with far fewer Maria to be found. The far side's crust is thicker, which hindered volcanic resurfacing, and as a result, it has remained relatively unchanged compared to the near side. Initially, the far side's mysterious nature kept it shrouded in enigma, but the Soviet lunar missions in the 1960s and 1970s finally broke this mystery wide open. These missions provided the first glimpses of the rugged terrain, revealing a landscape filled with craters and lunar highlands that had been hidden from view for eons. This dichotomy between the near and far sides also helps explain the different geological histories of these two regions. While the moon's near side saw volcanic resurfacing and activity, the far side's surface was largely untouched by such processes. The far side's greater crust thickness, a result of the unique gravitational relationship between Earth and the moon, has effectively served as a barrier to volcanic activity, leaving behind a much older, more pockmarked surface. This contrast enriches our understanding of the moon's evolution and deepens our appreciation of the intricate dynamics that shape our solar system. Another enigma of the moon that has fascinated scientists and observers for centuries is the phenomenon of transient lunar phenomena, mysterious flashes of light that occasionally appear on the lunar surface. These flashes can vary in form, ranging from brief illuminations to more prolonged glows, and they seem to occur at random, further adding to their intrigue. Over time, a variety of explanations have been proposed to account for these fleeting bursts of light, but none have yet provided a definitive answer. One common hypothesis is that the flashes are the result of micrometeorite impacts. When tiny meteoroids collide with the lunar surface at incredible speeds, the energy released can create bright, short-lived flashes of light. Given that the moon lacks an atmosphere to shield it from such impacts, these tiny objects often strike the surface without being burned up in the atmosphere, resulting in explosive events that generate visible flashes. These flashes are often observed by astronomers on Earth, providing another layer of mystery to the moon's already captivating surface. Another possibility is that these flashes may be caused by the reflection of sunlight off the moon's surface, or by interactions between the lunar regolith, the loose, dusty layer on the moon's surface, and sunlight. Shifting particles or subtle changes in the regolith's microscopic features, perhaps due to the effects of solar wind or seismic activity, could also lead to momentary changes in brightness. These brief fluctuations might give the appearance of flashes of light. Moreover, lunar eclipses or particular alignments with the sun could amplify these effects, making the transient phenomena more noticeable to observers on Earth. In some instances, scientists have suggested that the flashes could be linked to outgassing events on the moon. While the moon is largely geologically dormant compared to Earth, it is still capable of releasing small amounts of gas from its interior. These outgassing events could interact with the solar radiation, creating a brief flash of light that could be visible from Earth. However, despite numerous theories, the exact cause of these transient lunar phenomena remains an open question. As technology continues to advance and observational techniques improve, it is possible that new discoveries will eventually shed light on these enigmatic events, offering a deeper understanding of the moon's dynamic environment. Beyond the moon itself, there is another fascinating topic in celestial mechanics that has captured the imagination of astronomers: the possibility of natural satellites orbiting Earth beyond the moon. While the moon is the most prominent and well-known of these natural satellites, astronomers have discovered other objects that momentarily become captured by Earth's gravitational field, albeit temporarily. One such phenomenon is the presence of temporary satellites, often referred to as mini-moons. These small asteroids, ranging from a few meters to several kilometers in diameter, occasionally enter Earth's orbit, becoming temporary companions to our planet. They remain in orbit for a period of several months to a few years before escaping Earth's gravitational pull and returning to their travels through space. One notable example of a mini-moon is 2006 RH1, which was discovered in 2006 and orbited Earth for approximately 11 months before breaking free and drifting back into space. These mini-moons provide a fascinating glimpse into the gravitational dynamics of our solar system, showcasing how Earth can capture passing space debris, albeit only for short periods. They offer scientists a unique opportunity to study the interactions between small celestial objects and Earth's gravity. Furthermore, the existence of quasi-satellites, objects that orbit the sun in such a way they appear to remain in close proximity to Earth for extended periods, adds another layer of complexity to our understanding of the moon and its role in the Earth-Moon system. For instance, the asteroid 1166P NEAT, also known as Icarus, follows an orbit that brings it close to Earth for extended periods, creating the illusion that it is in orbit around our planet. Though it does not technically orbit Earth, its orbital path creates a unique relationship with our planet, offering yet another fascinating twist to the study of celestial mechanics. However, the conditions required for a stable, long-term natural satellite, like Earth's moon, are incredibly rare and unique. A combination of factors, such as the satellite's size, mass, and its optimal distance from its parent planet, makes it exceedingly difficult for other celestial objects to attain a similar status. The moon's size in relation to Earth, along with its gravitational influence, plays a pivotal role in stabilizing Earth's orbit, affecting our planet's axial tilt, and even driving the ebb and flow of the tides. These interactions create a delicate balance that sustains the moon's role as Earth's dominant satellite. While there may be potential for other stable natural satellites based on gravitational dynamics, the moon remains a singular case. It is a reminder of how rare such cosmic relationships are. The search for temporary satellites and quasi-satellites, objects that are caught briefly in Earth's gravitational field, continues, offering glimpses into the dynamic and ever-changing nature of the universe. These celestial bodies reveal the complexities of gravitational interactions and the unpredictable movements that shape the celestial landscape around Earth. In a similarly mysterious corner of the cosmos lies Taby's star, officially designated KIC 8462852, located approximately 1,500 light-years away in the constellation Cygnus. This star first captured the attention of astronomers in 2015 when the Kepler Space Telescope recorded its highly irregular fluctuations in brightness. What made Taby's star so intriguing was the erratic dimming of its light, a phenomenon that had no immediate, clear explanation. Several hypotheses have been proposed to account for this strange behavior, but none have definitively resolved the mystery. One of the more sensational theories suggests the possibility of an artificial structure, perhaps a Dyson sphere, constructed by an advanced extraterrestrial civilization. This hypothetical megastructure could, in theory, cause significant light blockage as it orbited the star. While the idea of a Dyson sphere is captivating, it remains speculative and is considered highly unlikely by the majority of scientists. The prevailing theories, however, focus on more natural causes. One of the most widely discussed explanations is the presence of a large cloud of dust or debris that occasionally passes in front of the star, intermittently blocking its light. Such clouds could be composed of material that scatters or absorbs light, casting temporary shadows across the star's surface. Another theory proposes that the star itself exhibits intrinsic variability, possibly due to stellar activity or pulsations, causing its brightness to fluctuate unpredictably. Some researchers have also speculated that companion objects such as comets or protoplanets could be obstructing the star's light as they pass between it and Earth. This would explain some of the sporadic dimming events. The possibility that a large population of icy bodies like comets may orbit the star adds another layer of complexity to the puzzle. While the precise cause of Taby's star's enigmatic dimming patterns remains elusive, ongoing research and observations continue to shed light on this cosmic riddle. The investigation into this star not only deepens our understanding of stellar behavior, but also provides insights into the vast and varied phenomena that populate the universe. Each new discovery, no matter how small, pushes the boundaries of what we know about the cosmos. Equally profound is the ongoing exploration of the nature of consciousness, a question that has confounded philosophers, neuroscientists, and cosmologists for centuries. Two primary perspectives dominate the discourse on consciousness. One proposes that consciousness is a fundamental property of the universe, while the other suggests that it arises from the intricate networks and systems of the brain. The first view posits that consciousness is not merely a byproduct of biological processes, but rather an essential and fundamental aspect of reality. Just as space, time, and matter are integral to the fabric of the universe, consciousness may also be an intrinsic part of it. This theory suggests that consciousness could exist independently of physical systems, potentially permeating the cosmos in ways we do not yet understand. Proponents of this view sometimes draw on concepts from quantum mechanics or explore philosophical ideas like panpsychism, which posits that all matter, from the smallest particles to the largest structures, may possess some form of consciousness or experience. If consciousness is indeed a fundamental force of the universe, it could have far-reaching implications for how we understand sense itself. On the other hand, the dominant view in neuroscience and psychology is that consciousness emerges from the highly organized complexity of neural networks in the brain. According to this perspective, consciousness is not a separate, independent force, but a byproduct of the interactions among neurons, synapses, and biochemical processes that occur within the brain. The intricate dance of information processing within the brain gives rise to the subjective experience of awareness. As our knowledge of brain function deepens, particularly through advances in neurobiology and cognitive science, there is growing support for the idea that consciousness is an emergent property, an outcome of highly organized biological systems, rather than a fundamental aspect of reality. The debate becomes even more layered when considering the implications of each perspective. If consciousness is fundamental to the universe, it may suggest that awareness is an inherent quality of reality itself, extending far beyond human experience. This could lead to a radically different understanding of life, existence, and the very nature of the cosmos. If consciousness is an emergent property, however, it challenges us to reframe our understanding of the brain and its capabilities, opening up new avenues of inquiry into the very nature of awareness. In both the case of Taby's star and the exploration of consciousness, we encounter mysteries that have yet to be fully explained. They represent the ongoing quest to understand the universe, whether through the lens of astronomy or the intricacies of the human mind. Both are fundamental to our search for knowledge, as each new discovery brings us one step closer to unraveling the vast complexities of the cosmos and our place within it. However, if consciousness emerges from complexity, it underscores the crucial role of brain organization and the evolutionary processes that shape it, emphasizing the distinctiveness of conscious beings in the vast expanse of the cosmos. Understanding consciousness requires a multifaceted exploration, one that crosses the boundaries of science, philosophy, and even metaphysics. As researchers continue to grapple with this profound and intricate question, the quest for insights into consciousness shapes not only our comprehension of the human experience, but also provokes deeper inquiries into the very nature of reality itself. The concept that the universe could possess some form of consciousness invites profound philosophical and scientific discussions. This idea, often referred to as cosmic or universal consciousness, proposes that consciousness is not merely a phenomenon arising from complex life forms, but might be an intrinsic quality embedded within the universe itself. While this notion remains speculative, it has spurred a range of perspectives and theories, each exploring its profound implications. One approach to understanding this concept is rooted in the philosophical framework of panpsychism. According to this view, consciousness might be a fundamental aspect of all entities, even those traditionally considered inanimate. From this standpoint, everything in the universe, from subatomic particles to the most colossal cosmic structures, could possess some form of awareness or experience, albeit at vastly different levels of complexity. This perspective reimagines the universe as a vast, interconnected web, where consciousness is woven into the very fabric of reality, leading to the possibility that a collective consciousness could emerge from the myriad interactions of these diverse elements. Another consideration emerges from the dynamics of complex systems and information processing. Some theorists suggest that if consciousness arises from the intricate networks of neurons in the brain, then larger systems, such as the universe itself, might exhibit behaviors that mimic consciousness. This would be akin to the flow of information in living systems, where complex behaviors emerge from the interplay of many interconnected parts working in unison. In this scenario, consciousness might not be localized in one specific area, but could manifest through the dynamics of a larger system, displaying emergent properties as complexity increases. Yet empirical evidence to support the idea of a universally conscious entity remains elusive. Unlike human consciousness, which is marked by subjective awareness and self-reflection, the concept of cosmic consciousness lacks clear mechanisms or measurable attributes. Most contemporary scientific inquiry tends to focus on consciousness as an emergent property of biological systems, placing significant emphasis on physical structures, particularly the brain, as the origin of subjective experiences. As this debate continues, the exploration of whether the universe itself could possess a form of awareness challenges our deepest understanding of existence and the nature of reality. It opens philosophical avenues that invite us to reconsider our place within the cosmos, enriching the discussions that are realms of science and philosophy. The relationship between consciousness and quantum mechanics has also long been a source of intrigue and debate among physicists, philosophers, and cognitive scientists. Some theorists propose that quantum mechanics might provide valuable insights into the nature of consciousness, while others assert that consciousness arises independently of any physical phenomena. This connection is often examined through the fundamental principles of quantum mechanics and how they might correlate with conscious experience. One key area of exploration centers around the concept of observation in quantum mechanics. In this framework, the act of measurement appears to influence the behavior of quantum systems. For example, particles such as electrons can exist in multiple states simultaneously, described by a mathematical construct known as a wave function. However, once a measurement is made, the system seems to collapse into a single state, a phenomenon known as wave function collapse. Some theorists, including the physicist Eugene Wigner, have pondered whether conscious observation plays a necessary role in this collapse. According to this hypothesis, consciousness might be integral to determining the state of quantum systems, suggesting a profound interplay between the mind and the quantum world. A more developed theory linking consciousness and quantum mechanics is known as orchestrated objective reduction, OR, proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff. This hypothesis suggests that consciousness arises from quantum processes occurring within microtubules, tiny structural components inside neurons in the brain. Penrose and Hameroff argue that these quantum events could give rise to moments of conscious awareness, as well as decision-making processes. The theory posits that these quantum phenomena might be responsible for our experience of consciousness, potentially providing a bridge between the mind and the quantum realm. Despite the compelling nature of these theories, empirical evidence remains sparse, and the relationship between consciousness and quantum mechanics is far from being fully understood. Yet, the continued exploration of these concepts pushes the boundaries of both science and philosophy, opening new avenues for the study of consciousness and its potential connection to the fabric of the universe. In seeking answers, we not only expand our understanding of consciousness itself, but also challenge the very foundations of reality, leading to deeper questions about the nature of existence, observation, and the mind's place in the cosmos. However, this theory has faced significant skepticism within the scientific community, largely due to the immense challenges associated with preserving quantum coherence in the brain's warm and chaotic environment. The brain is far from the controlled, isolated environments typically required for the delicate processes of quantum mechanics. The noise and heat within the brain, which constantly bombard its molecular and atomic structures, create a stark contrast to the pristine conditions in which quantum effects are usually observed. On the other hand, a substantial body of scientists and researchers vehemently argues against drawing any direct connection between consciousness and quantum mechanics. These critics maintain that consciousness can be fully explained within the framework of classical neuroscience and cognitive processes, without invoking the complexities of quantum phenomena. According to their perspective, while quantum mechanics undeniably governs the behavior of particles at the subatomic level, this influence does not extend to the macroscopic domain where conscious experience takes place. They assert that consciousness is an emergent property of complex neural networks, a result of the intricate interconnections between neurons, entirely independent of any quantum effects. This disagreement about the role of quantum mechanics in consciousness reflects a broader tension within both fields, neuroscience and quantum physics. The question of whether quantum effects play a significant role in the emergence of consciousness remains a deeply provocative and unsettled inquiry. As advancements continue in both neuroscience and quantum physics, our understanding of consciousness might evolve, leading to new perspectives that could reshape our conception of reality itself. The very existence of consciousness challenges and enriches our understanding of the universe in profound ways, intertwining philosophy, science, and metaphysics. Consciousness is not merely a passive phenomenon, but a complex, active force that shapes how we perceive the world. By studying consciousness, we are drawn into an exploration of some of the most fundamental questions about existence, reality, and the nature of perception. This journey through the mysteries of consciousness often leads us to transformative implications that could shift our entire worldview. One of the most profound effects consciousness has on our understanding of the universe lies in the subjective nature of experience. Each conscious being perceives the universe through its own distinct sensory framework, leading to a wide variety of interpretations of reality. This subjectivity underscores the complexity of how we acquire knowledge and comprehend phenomena. Consciousness, in this sense, does not merely mirror the world. It adds a layer of intricacy, providing a unique perspective on the cosmos. The ways in which different individuals and cultures experience reality reveal the rich tapestry of consciousness, one that is deeply personal and yet inherently shared across humanity. As we delve deeper into the nature of consciousness, we are compelled to consider whether any semblance of reality exists independently of an observer. This question takes us into the realms of philosophical inquiry and quantum mechanics, where the act of observation seems to play a pivotal role. Could it be that reality, as we understand it, is somehow intertwined with the consciousness that perceives it? This line of thought blurs the boundaries between the objective world and subjective experience, drawing us closer to the idea that consciousness and reality might be inseparable. Additionally, the exploration of consciousness raises profound questions about the nature of existence itself. If consciousness is viewed as an emergent property arising from complex neural interactions, it suggests that the phenomena of life are the result of intricate patterns of neural activity. Yet, if consciousness is considered a fundamental aspect of reality, something that exists not merely as a byproduct of matter, but as an integral part of the fabric of existence, it could radically alter how we perceive life, matter, and the universe as a whole. This perspective might lead to theories that propose interconnectedness, with consciousness acting as a binding force that permeates both living and non-living systems. Such theories could encourage a more holistic view of the universe, where conscious experience does not just emerge from reality, but contributes to shaping its very structure. The search for a deeper understanding of consciousness also propels research across diverse fields, from neuroscience to astrophysics. As scientists strive to uncover how consciousness arises from the brain's neural processes, they often venture into the outermost boundaries of both physical laws and philosophical inquiry. Scientific inquiries into consciousness may lead to groundbreaking discoveries in cognition, potentially transforming our understanding of human behavior, artificial intelligence, and even the potential for consciousness to exist beyond biological systems. Consciousness, in this sense, shapes the very way we explore the universe. It forces us to ask questions about the fundamental nature of reality, our place within the vast cosmos, and the interconnectedness of all things. As we probe deeper into the intricate relationship between consciousness and the universe, we may ultimately arrive at a richer, more nuanced understanding of existence itself, one that could forever change how we view the world and our role in it. The connection between consciousness and the observer effect in quantum mechanics is another area of intense fascination, captivating both scientists and philosophers alike. The observer effect refers to the phenomenon where the act of measuring or observing a quantum system can influence the state of that system. In quantum mechanics, particles exist in a superposition of states. Essentially, they can be in multiple configurations at once until a measurement is made. At the moment of observation, the superposition collapses and the particle assumes a definite state. This curious behavior has led some to speculate that consciousness might play a critical role in this collapse, influencing the outcomes of quantum measurements. One of the most famous proponents of the consciousness-observer connection was physicist Eugene Wigner. Wigner posited that consciousness itself is necessary for the collapse of the wave function. According to this view, the mere presence of a conscious observer is what causes the quantum system to transition from a state of possibility to a single, concrete reality. This intriguing perspective suggests that consciousness might be intrinsically tied to the most fundamental processes of quantum mechanics, raising profound philosophical questions about the relationship between mind and matter. If consciousness is indeed a necessary component in determining the state of a quantum system, this would imply that the very fabric of reality could be in some way contingent upon conscious observation. However, many physicists and scholars disagree with this interpretation, arguing that the observer effect does not require consciousness at all. In quantum mechanics, the term observer is typically understood as any interaction that leads to a measurement, not necessarily a conscious awareness. This can include any physical interaction that causes a system to collapse into a particular state. Under this interpretation, consciousness is not a required factor in the process of measurement. Instead, the measurement itself, regardless of whether anyone is consciously observing it, is enough to influence the quantum system. This interpretation aligns with the Copenhagen interpretation of quantum mechanics, which emphasizes the importance of the measurement process without delving into the role of the observer's consciousness. This ongoing debate, whether consciousness is essential for quantum measurement or whether it is simply a byproduct of physical interactions, remains one of the most fascinating and unresolved questions in both quantum physics and philosophy. As scientists continue to probe the mysteries of quantum mechanics, the relationship between consciousness and the observer effect will likely remain a central point of inquiry, one that could have far-reaching implications for our understanding of the universe. Quantum mechanics continues to offer a fascinating, though often perplexing, window into the nature of reality. At the heart of these complexities lies the observer effect, a concept that challenges our traditional notions of how reality is perceived. Some alternative interpretations of quantum mechanics, such as the many-worlds interpretation, further complicate the relationship between consciousness and the observer effect. According to this interpretation, all possible outcomes of a quantum event unfold in parallel realities within an expansive multiverse. In this view, consciousness is no longer necessary to influence the course of reality. Instead, every potential scenario exists simultaneously without requiring any act of conscious observation to determine its outcome. Despite the allure of this idea, the prevailing scientific consensus suggests a more nuanced perspective on the observer effect. Rather than inherently depending on consciousness, the observer effect is considered a fundamental characteristic of quantum mechanics itself. While it certainly prompts deeper inquiries into the nature of reality, observation, and human experience, the role of consciousness remains elusive. What seems clear is that as quantum research continues to evolve, our understanding of this intricate relationship between consciousness and quantum physics may undergo profound shifts. These shifts could have far-reaching implications for both scientific inquiry and philosophical discourse, forcing us to reconsider what we truly understand about the universe and our place within it. One of the most provocative ideas to emerge in both scientific and philosophical circles is the simulation hypothesis. The notion that our universe might not be an authentic physical reality, but rather a sophisticated simulation running on an immensely powerful computer. This idea has gained increasing traction in recent years, spurring widespread debates about the very nature of existence. Could it be that what we perceive as reality is simply a highly detailed, artificial construct generated by a super-intelligent civilization or an advanced form of artificial intelligence? The possibilities suggested by the simulation hypothesis challenge our deepest assumptions about reality and our place within it. The core argument behind the simulation hypothesis stems from the rapid advances in technology, particularly in the realm of computer simulations. As our own computational capabilities grow, the prospect of creating highly detailed, interactive simulations of reality becomes more plausible. Researchers and theorists have pointed out that should a civilization reach a level of technological sophistication far beyond our own, it could theoretically create entire simulated universes, complete with their own physical laws and conscious beings. This suggests that if an advanced civilization possessed enough computing power, they could create a simulation indistinguishable from real life. Philosopher Nick Bostrom has articulated a well-known version of the simulation hypothesis, proposing that one of the following must be true. First, advanced civilizations are unlikely to run many simulations of their past. Second, they might go extinct before acquiring the technology to do so. Or third, we are almost certainly living in a simulation. This framework has opened up intriguing philosophical questions, particularly about the very nature of existence. If we live in a simulation, it raises profound implications about free will, identity, and the essence of consciousness itself. What happens to our understanding of reality if we accept that it might not be real at all? Despite its allure, critics of the simulation hypothesis argue that it suffers from a lack of concrete evidence. Some suggest that it may be unfalsifiable, that is, inherently impossible to prove or disprove, and that in its speculative nature, it doesn't offer substantial explanatory power. Rather than clarifying the nature of reality, it could simply shift the problem of what is real, one step further back, now asking whether our universe is an illusion created by a higher intelligence. While fascinating, the simulation hypothesis remains largely philosophical, offering more in the way of profound speculation than scientific proof. Nevertheless, the hypothesis encourages us to think more deeply about existence itself. Whether or not we are living in a simulation, it prompts questions about the nature of consciousness, reality, and human experience. As we continue to explore the universe through the lens of scientific inquiry, the idea of a simulated universe challenges traditional frameworks and invites new avenues of philosophical thought. Could it be that the very nature of our existence is not what it seems? Could the boundaries of consciousness be far more expansive than we have ever imagined? The potential ramifications of the simulation hypothesis are immense, especially if we were to accept the idea that our universe is indeed an advanced simulation. If this were the case, several key philosophical and scientific considerations would emerge, potentially reshaping our understanding of the world around us. First, the hypothesis would force us to reconsider the nature of existence itself. If the universe is a simulation, then what we perceive as the laws of physics, the constants of nature, and even the passage of time might not be fundamental truths, but rather programmed constructs, rules established by the creators of the simulation. This rethinking of physical laws challenges our very conception of what is real, suggesting that the world we experience could be a carefully crafted illusion. It forces us to ask, what does it mean for something to be authentic if its very foundation is artificial? Beyond this, the simulation hypothesis also raises serious questions about free will and autonomy. If our reality is a simulation, then our actions, decisions, and experiences could be preordained by the underlying code that drives the simulation. This would challenge the very concept of free will and autonomy, leading to philosophical debates about determinism. Are we truly in control of our lives, or are our choices simply the outcome of a pre-written script? If we were to accept that we exist within a predetermined framework, what would this mean for our sense of agency, and how would it affect our moral responsibilities? Furthermore, the simulation hypothesis invites new discussions about the nature of consciousness. Could consciousness itself be a product of the simulation, or is it an independent entity interacting with the simulated reality? Some theorists speculate that within the context of a simulation, consciousness might not be confined to biological entities like humans, but could instead be replicated digitally. This line of thought expands the possibilities of understanding consciousness, prompting us to consider the implications for artificial intelligence and the creation of sentient beings within digital frameworks. Could consciousness arise within a purely synthetic environment? In addition to these philosophical considerations, the simulation hypothesis also raises profound ethical questions. If we are living within a simulated reality, what moral obligations would the creators of the simulation have toward us? If we are, in fact, conscious beings within a construct of their design, what ethical responsibilities would they have to ensure our well-being and preserve our existence? These questions prompt inquiries into the ethical dimensions of simulation design, as well as the treatment of sentient beings within such a framework. Could we, as simulated beings, hold the same moral worth as conscious beings in the real world? Ultimately, whether we are living in a simulation or not, the hypothesis forces us to grapple with some of the most fundamental questions about existence. What is real? What does it mean to be conscious? How much control do we truly have over our lives? The implications are vast, not only for our understanding of reality, but for our conception of ourselves and our place within the cosmos. As we continue to explore the universe and push the boundaries of our knowledge, the simulation hypothesis challenges us to reconsider the very fabric of existence itself. Furthermore, should we ever uncover methods to manipulate or alter the simulation, the moral consequences of such actions could ignite profound debates concerning the rights of conscious entities within this simulated framework. These discussions would be far-reaching, challenging our most fundamental ethical principles and introducing new dimensions to the concept of personhood. What rights, if any, should conscious beings within a simulation possess? Are they any less real than beings in what we consider the real universe? And if so, what does that mean for how we view consciousness itself? At its core, the simulation hypothesis confronts us with some of the most foundational questions about the nature of existence. By posing such inquiries, it presses us to reconsider essential concepts like free will, consciousness, and morality. Are our thoughts, choices, and experiences truly our own, or are they pre-programmed? This hypothesis doesn't just invite intellectual curiosity, it forces a reckoning with what it actually means to exist at all. It invites a deep, often uncomfortable rethinking of the very fabric of reality, a process that pushes the limits of both scientific exploration and philosophical speculation. The challenge of determining whether we live in a simulated universe is a multifaceted one, and it spans across realms of philosophy, science, and technology. While the notion of a simulation might seem speculative, there are serious thinkers who have proposed a variety of methods to test this idea. One approach focuses on detecting anomalies or glitches in the laws of physics, unexpected irregularities that might indicate a deeper computational architecture beneath the surface of reality. If the universe operates like a computer program, there may be observable deviations from the expected patterns of natural laws. For example, researchers could look at phenomena within quantum mechanics or cosmic events for signs that don't align with our current understanding of physics. These discrepancies might be the equivalent of bugs in a simulation, errors in the code that could suggest a non-physical origin to our reality. Another method hinges on exploring the computational limitations of simulating complex systems. In the same way that computer graphics have their own set of boundaries, the physical universe might display constraints that only become visible when we push the system to its limits. If we could establish the maximum computational resources required to simulate physical interactions or cosmic phenomena, we might find that our universe operates near those limits. Such a finding could lend support to the hypothesis that the world around us is indeed a simulation, where certain phenomena behave in ways that are dictated by an underlying computational architecture. Meanwhile, the rapid advancement of virtual reality technology is also providing new avenues for exploring this idea. As we create increasingly sophisticated virtual environments that mimic the real world, we are inching closer to understanding how perception and consciousness could be shaped by digital constructs. While this may not provide definitive proof of a simulated universe, it could certainly offer valuable insights into how immersive experiences alter our understanding of reality. By studying virtual environments and their effects on human consciousness, we might learn more about the very nature of perception itself, blurring the line between what is real and what is simulated. There is also a fascinating theory that looks at high-energy cosmic rays or particles, suggesting that they might provide clues about the simulated nature of our universe. Some researchers propose that if the universe is indeed a simulation, there could be patterns or specific anomalies in the distribution of cosmic rays that reflect the underlying computational structure. By analyzing these particles and how they behave, we might uncover signatures that align with what would be expected in a simulated reality, suggesting that, just as in computer programs, there are specific limits and constraints to how the universe is rendered. However, despite these potential methods of investigation, testing the simulation hypothesis is fraught with immense philosophical and practical challenges. At its heart, the hypothesis is difficult, if not impossible, to prove or disprove definitively. The nature of the question itself raises broader existential concerns, questions about the very limits of human knowledge and understanding. What if there are things beyond our capacity to grasp? And if we are indeed living in a simulation, what does that say about the universe and our place within it? If we entertain the possibility that our universe is a simulation, it leads to profound implications regarding the existence of a creator or designers. The idea that the universe is a construct of a higher intelligence raises questions about the nature of those responsible for its creation. Were they trying to build a perfect simulation, or was it an experiment? Perhaps a means of studying life, consciousness, or even the concept of free will. The creators would need to possess a level of technological sophistication far beyond anything we currently understand. The laws of physics, the cosmological structures we observe, and even the intricacies of consciousness itself would have to be meticulously crafted by a force that surpasses human comprehension. This raises additional questions. Why would such designers, if they exist, create a reality that feels so tangible, so real? Were they interested in exploring the nature of existence or testing the limits of their own technological prowess? Or perhaps they are observing us, not as gods, but as detached scientists studying the unfolding drama of simulated life. These questions challenge our very ideas about purpose, intention, and existence. Why create beings capable of reflection, capable of contemplating their own reality, if those beings are ultimately products of a machine? The dynamics between the creator and the created are critical, not just for understanding the mechanics of the simulation, but for exploring our own position within it. Are we truly autonomous, or are we simply following a set of predetermined parameters encoded by the designers? This introduces themes of responsibility and moral obligation. If the designers are aware of the sentience within their creation, do they have a responsibility toward the beings they have created? Do they have a moral obligation to ensure their well-being, or is our existence entirely at their whim? This concept also invites theological reflections. If a creator designed this universe, are they analogous to the divine figures of various religious traditions? Could they be regarded as gods, or perhaps a class of entities whose goals and motivations are entirely different from those traditionally ascribed to deities? Classic philosophical questions about fate and free will take on new dimensions in this context. If we are part of a program, do we have any true autonomy, or are our choices merely illusions within a complex system of predestined outcomes? Would understanding the nature of our creators change how we view our own existence? Would it alter the way we understand the relationship between purpose, free will, and destiny in a simulated world? Ultimately, the simulation hypothesis forces us to confront questions about existence, reality, and the very limits of human knowledge. Whether or not we live in a simulation, the pursuit of answers to these questions shapes the very nature of human inquiry and challenges us to explore new frontiers in science, philosophy, and technology. The conversation itself is a testament to the evolving complexity of the questions we ask about our place in the universe and whether we truly understand the nature of the reality we inhabit. However, the simulation hypothesis itself does not necessarily demand the existence of a creator, as some variations of the theory suggest that the universe could have emerged spontaneously or through natural processes, much like how our technological advancements now enable us to create complex simulations without requiring a conscious designer. This perspective introduces a radically different viewpoint, one that asserts the universe may function entirely independently of any overseeing intelligence, challenging the assumption that simulations, whether digital or otherwise, must require a deliberate, intentional creator. The implication of this notion raises significant philosophical questions about the nature of existence, reality, and the very fabric of consciousness itself. Whether one adheres to the belief that a creator is essential to the simulation or not, these inquiries provoke deep reflections on intelligence, purpose, and the intricate relationship between creation and creator. Ultimately, these thoughts enhance and enrich the ongoing dialogue about our understanding of existence and our place within the cosmos. Living in a simulated universe, if such a hypothesis proves to be true, would confront humanity with profound philosophical and existential challenges, forcing us to rethink our assumptions about reality, identity, and existence itself. Engaging with the idea of a simulated reality calls us to revisit foundational concepts that shape human thought, experience, and the meaning we attach to both. One of the most significant philosophical implications of a simulated universe involves the nature of reality itself. If our universe is indeed a simulation, it raises fundamental questions about what is real versus what is illusory. Could our entire existence, our thoughts, emotions, experiences, and relationships, be nothing more than an engineered construct? This uncertainty mirrors the skepticism of philosophers like René Descartes, who centuries ago famously questioned the reliability of perception and the certainty of knowledge. Descartes' philosophical musings on whether reality could be an illusion now find new resonance in the simulation hypothesis. The thought that everything we experience might be engineered by an external force pushes us to reconsider the very validity of our perceptions and the authenticity of the relationships we form with one another. If the universe is a simulation, it suggests that what we believe to be objective reality may, in fact, be a carefully orchestrated environment designed for purposes we may never fully understand. Another key implication of the simulated universe hypothesis concerns free will and moral responsibility. If our lives unfold within a simulation crafted by an external entity or force, the question of autonomy becomes pressing. Are the choices we make truly our own, or are they manipulated or predetermined by the parameters of the simulation? This dilemma can provoke existential anxiety, as individuals might begin to grapple with the unsettling possibility that their lives, their decisions, and their paths are merely part of a script designed by a higher intelligence. This tension between perceived freedom and possible determinism is one of the core challenges of the simulation hypothesis, leading to profound questions about the nature of agency. If our reality is engineered, can we be held morally accountable for our actions, or is moral responsibility merely a product of the illusion of free will? In addition to the concerns about free will, the existence of a simulated universe compels us to explore the nature of consciousness itself. If consciousness can emerge within a simulation, if artificial systems can host self-aware entities, what does this imply about the essence of being? Is consciousness a phenomenon unique to biological organisms, or could it be replicated within machines or digital environments? The simulation hypothesis pushes the boundaries of our understanding of consciousness, inviting us to consider that it may not be confined to organic life forms. Could consciousness in some form be a universal property that transcends biology? Might it exist as a fundamental aspect of the universe, potentially giving rise to non-biological forms of sentience? The notion that consciousness could emerge from artificial environments blurs the lines between what we consider alive and what is artificially constructed, leading to questions about the distinction between life and machine. Furthermore, contemplating the existence of a simulated universe inevitably raises questions about the ultimate purpose of that simulation. If we are indeed part of a simulation, what is the end goal? Are we subjects of an experiment, mere entertainment for more advanced intelligences, or participants in a grand philosophical inquiry conducted by entities far beyond our comprehension? This line of questioning provokes reflections on the meaning of existence, on the purpose of life, and on our place in the grand cosmic scheme. If our reality is fabricated, is our purpose dictated by the designers, or do we carve out our own meaning within the constraints of the simulation? These profound questions about the meaning and direction of our existence challenge the conventional notions of purpose, destiny, and free will, encouraging a reevaluation of what it means to live a real life. Lastly, the very contemplation of living in a simulated universe fosters a sense of interconnectedness and humility. It reminds us that our understanding of the cosmos, of reality itself, may be severely limited. We might only be scratching the surface of a vast, multi-layered reality governed by rules and principles that transcend our current understanding. The possibility that our existence is part of a grander simulation opens our minds to the intricate complexity of the universe and the mysteries that lie beyond our perception. It urges us to embrace uncertainty and remain open to the unknown, to the infinite layers of reality that might shape our experiences in ways we cannot yet fully comprehend. The exploration of these implications does more than stir philosophical debate. It enhances the very human experience, deepening our appreciation for the complexity and mystery of existence. The simulation hypothesis, whether true or not, serves as a tool for expanding our understanding of the universe, of consciousness, and of our place within it. The anthropic principle is another compelling concept that ties into these existential questions. Philosophically and scientifically, it attempts to explain why the universe is structured in such a way that life, and by extension, conscious beings can exist. It posits that the universe's fundamental physical laws and constants are finely tuned to permit the emergence of life. Without these precise conditions, the existence of conscious observers would be impossible. This raises profound questions about the relationship between life and the cosmos. How much of the universe's design, if any, is intentional? Is there a deeper connection between consciousness and the physical world? The anthropic principle exists in various forms, two of the most commonly discussed being the weak and strong versions. The weak anthropic principle suggests that the universe must be capable of supporting life, as life must exist to observe the universe. In simpler terms, we find ourselves in a universe that is suitable for life because without it, we would not be here to notice the fine-tuning. This principle essentially emphasizes a self-selection bias. We can only observe a universe that allows for our existence because if the conditions weren't right, we wouldn't be here to ponder them. In contrast, the strong anthropic principle suggests that the universe's physical properties are not merely coincidental, but are inherently structured to allow for the emergence of life. This perspective implies that life is not just one possibility among many, but rather a fundamental aspect of cosmic reality. From this view, the existence of conscious beings is not an accident, but a necessity, baked into the very fabric of the universe. A further extension of the anthropic principle, sometimes referred to as the final anthropic principle, goes even further. It suggests that intelligent life will inevitably emerge in the universe, and that the existence of conscious observers is an intrinsic condition for the universe itself to exist. This raises fundamental philosophical and metaphysical questions about determinism and the ultimate purpose of the universe. Is the universe constructed for the sake of consciousness? And if so, what does that mean for our understanding of existence and reality itself? These inquiries invite us to consider our place in a vast, interconnected cosmos, one that may be inherently geared towards the emergence of life and consciousness, not just as a possibility, but as a cosmic imperative. The multiverse variant of the anthropic principle presents a fascinating and thought-provoking perspective on the nature of our universe. It suggests that our universe is just one among many in a vast and diverse multiverse, each with its own set of physical laws and parameters. In this framework, the specific conditions that allow for life in our universe are not uniquely special or coincidental. Rather, they are simply one possible realization among an infinite number of others. The anthropic principle, in this context, serves as a lens through which we can understand the apparent fine-tuning of the universe. It posits that while many universes may not be hospitable to life, we find ourselves in one that happens to support it. This concept invites profound discussions across multiple disciplines, including cosmology, philosophy, and theology. It forces us to confront some of the most fundamental questions about the nature of existence. Why does the universe appear to be structured in a way that permits conscious life? Does this suggest an underlying purpose or design behind the cosmos? Or is it merely a product of chance, or something even more enigmatic, like the multiverse? One of the most intriguing aspects of this fine-tuning lies in the fundamental constants and laws of physics, which seem to be precisely calibrated to allow for the emergence of life as we know it. The universe's parameters, such as the gravitational constant, the electromagnetic force, and the strong nuclear force, appear to be set in a delicate balance that enables the formation of stars, planets, and ultimately, life. This precise calibration raises important questions. What if these constants were even slightly different? The consequences could be dramatic. If the gravitational constant were weaker, stars like our sun might not form, and the complex planetary systems necessary for life would not arise. On the other hand, if the constant were stronger, stars would burn out too quickly, leaving insufficient time for life to evolve. The balance is so sensitive that even a tiny deviation could render the universe incapable of supporting life. Similarly, the structure of atomic and molecular interactions exemplifies fine-tuning. A crucial example lies in the formation of carbon atoms, a fundamental building block of life. The energy levels of carbon nuclei are finely tuned to allow for the formation of stable carbon atoms, which can bond with various other elements, forming the complex organic molecules that life depends on. If these energy levels were altered, even slightly, carbon might not be as abundant, or it could be entirely absent, fundamentally changing the chemistry required for life to exist. Another key aspect of fine-tuning is the rate of the universe's expansion, which is influenced by dark energy. If the universe had expanded too quickly after the Big Bang, galaxies would not have formed, and there would be no stars or planets, rendering life impossible. Conversely, if the expansion had been slower, the universe might have collapsed on itself before life could emerge. This delicate balance of cosmic expansion is critical in shaping the conditions necessary for a habitable environment. These examples raise an essential philosophical question. Does the apparent fine-tuning of the universe imply some form of design or purpose? Some proponents of this view argue that the precise calibration of physical laws and constants suggests the involvement of a creator or a guiding intelligence behind the universe. Others, however, propose alternative explanations, including the idea of the multiverse. According to this theory, countless universes exist, each with varying constants and laws. In such a scenario, we happen to live in one of the rare universes where the parameters are aligned in a way that supports life. This perspective reduces the improbability of finding a life-supporting universe, as there would be many others with vastly different characteristics, and the probability of life evolving in any one of them is not as unlikely as it might initially appear. The multiverse theory gains further support from certain aspects of modern physics, particularly the inflationary model of the early universe. This model suggests that in the moments following the Big Bang, space expanded at an incredibly rapid rate, leading to the formation of pocket or bubble universes, each with its own set of physical properties. These universes could be generated through quantum processes, giving rise to a vast array of universes with varying fundamental constants. Some of these universes might support life, while others might be inhospitable. In this view, the fine-tuning we observe in our own universe is not a remarkable coincidence, but rather a product of the vastness of the multiverse. However, while the multiverse theory offers a compelling explanation for the fine-tuning we observe, it remains a highly debated and speculative concept. Critics argue that it challenges the scientific principle of observable evidence, as many of these alternate universes may be fundamentally inaccessible to us. This raises important philosophical questions about the nature of scientific inquiry and the definition of reality itself. If we cannot observe or measure these other universes, can we really claim that they exist? And if they do exist, what does that mean for our understanding of the universe we inhabit? The fine-tuning of the universe also prompts significant theological and philosophical discussions, particularly regarding the existence of a creator or designer. The anthropic principle has profound implications for these debates, as it suggests that the universe's fundamental constants and laws are set within a specific range that allows for the emergence of conscious observers, like humans. One interpretation of the anthropic principle is that the universe's fine-tuning is not accidental, but rather a result of purposeful design by an intelligent creator. This view aligns with the strong anthropic principle, which posits that the conditions necessary for life are not mere coincidences, but are somehow aligned with the emergence of conscious beings. In this context, the anthropic principle could be seen as supporting theistic or deistic perspectives, suggesting that a higher intelligence intentionally designed or fine-tuned the universe for specific outcomes. On the other hand, the weak anthropic principle emphasizes that we can only observe a universe that is conducive to life because we exist within it. According to this view, the universe's parameters must allow for observers, but this does not necessarily imply that the universe was designed with life in mind. Rather, it can be interpreted as a self-selection bias, where the mere existence of observers informs our understanding of the environment we inhabit. This interpretation does not support the notion of a creator, but instead opens the door to alternative explanations, such as the multiverse theory. In this scenario, our universe is simply one of many possible worlds, each with its own set of conditions. The multiverse theory, in conjunction with the anthropic principle, offers a potentially satisfying explanation for the apparent fine-tuning of the universe. It suggests that our universe is just one of many, and that the conditions necessary for life are not unique to us, but are a rare, albeit possible, outcome in the vast expanse of the multiverse. However, this theory also raises many unresolved questions and challenges, particularly regarding the limits of scientific knowledge and the philosophical implications of a universe that may be one among countless others. As we continue to explore the nature of the universe, the anthropic principle and the multiverse theory offer intriguing possibilities for understanding the origins of life, the fine-tuning of the cosmos, and the very nature of existence itself. Whether we ultimately find answers in the realm of science, philosophy, or theology, these discussions will continue to shape our understanding of the universe and our place within it. The anthropic principle, with its profound implications, sparks a range of philosophical reflections about the nature of existence and our place within the universe. At its core, the principle suggests that the universe, as we know it, appears to be finely tuned to allow for the existence of conscious life. This fine-tuning raises profound questions. What is the purpose behind such an arrangement? Is the universe's remarkable nature meant to convey significance or meaning, or does it merely reflect a random occurrence? If we accept that the universe's conditions are not arbitrary, then the inquiry naturally shifts toward the role of a potential intentional creator or designer. But beyond offering support for such a perspective, the anthropic principle opens the door to alternative explanations that challenge traditional views and invite us to question the assumptions about the origins of existence. In exploring these questions, the anthropic principle serves as a bridge between empirical observations in cosmology and broader philosophical and theological discussions. It invites humanity to reflect on deep existential questions, probing the very nature of reality and our role within it. As our understanding of the universe expands, so too does the scope of our curiosity, pushing us to reconsider the meaning behind the conditions that allow for conscious thought and self-awareness. The anthropic principle significantly influences our perception of the universe, prompting us to examine not only the universe's vastness, but also the delicate balance of forces that make our existence possible. It underscores the apparent fine-tuning of the fundamental constants of nature, such as gravity, electromagnetism, and the strong and weak nuclear forces, suggesting that these constants are precisely calibrated to allow life to flourish. This realization is not just an intellectual exercise, but a call to reflect on the relationship between human beings and the cosmos, encouraging us to see the universe not as a random collection of matter, but as a finely tuned, interconnected system in which our existence is inextricably linked to the larger forces at play. Such a perspective can inspire a profound sense of awe, encouraging us to appreciate both the cosmos and our role within it. It raises the question of whether we are here for a specific reason. If the universe is indeed tailored to support conscious observers, might our existence have a higher purpose? Or perhaps our presence in such a perfectly calibrated universe highlights nothing more than the statistical likelihood of life emerging under the right conditions. This line of inquiry opens up vast possibilities, exploring the intersection between science, philosophy, and spirituality. It challenges us to re-examine the meaning of existence and the potential reasons behind our conscious awareness in a seemingly infinite and indifferent universe. As we ponder these existential questions, the anthropic principle also invites us to consider our responsibilities. If the universe is as finely tuned as it appears, then perhaps our survival and flourishing depend on a precarious balance. This awareness fosters a sense of stewardship, encouraging us to recognize the importance of protecting the environment and sustaining the conditions that allow life to thrive. We are reminded that our existence, fragile as it is, depends on the delicate interplay of natural forces, and that with such knowledge comes a duty to care for the planet that sustains us. On the other hand, the anthropic principle can also lead to existential humility. While human beings have made remarkable intellectual and technological strides, the principle highlights the limitations of our understanding. The universe we inhabit could have been entirely different, with conditions that would not support life as we know it. This realization serves as a humbling reminder that, despite our impressive achievements, our existence is contingent upon a very specific set of circumstances that could have easily been otherwise. It encourages us to acknowledge the fragile nature of life and the intricate balance of forces that enable our existence. The implications of the anthropic principle are far-reaching, intertwining our understanding of existence, purpose, and responsibility. It challenges us to reconsider our relationship with the universe and our role within it, pushing us to reflect on the interconnectedness of all things. As we explore these profound ideas, we are prompted to engage in both scientific inquiry and philosophical contemplation, seeking to understand our ultimate role in the vast cosmic tapestry. The more we explore, the more we realize how little we truly know and how much remains to be discovered. Indeed, our journey through the mysteries of the universe is only just beginning. Every new discovery uncovers new questions, and each answered question reveals a deeper layer of complexity. The universe, with all its vastness and intricacy, seems to guard its secrets jealously. Yet it is this very enigma that makes the pursuit of knowledge so exhilarating. As we push the boundaries of human understanding, we find ourselves not only expanding our scientific knowledge, but also reshaping our perception of what is possible. In the future, we may uncover the elusive nature of dark matter and dark energy, or perhaps we will discover signs of life on distant worlds. We might unlock the strange mysteries of quantum physics, or learn to manipulate the very fabric of space and time. Or perhaps, in the end, we will simply become better at asking questions, seeing the universe with clearer eyes and deeper understanding. Whatever the future holds, one thing is certain: the mysteries of the cosmos will continue to inspire and captivate us. In the grand scheme of things, the universe is not a static, unchanging entity. It is a dynamic, evolving puzzle, one that beckons us to explore its depths and uncover its secrets. The pursuit of knowledge is not merely a scientific endeavor, it is a deeply human endeavor, one that speaks to our curiosity, our need for meaning, and our desire to understand the vastness that surrounds us. As we continue to probe the mysteries of the universe, we are reminded that the journey itself is as valuable as the answers we seek. The universe, with all its complexity and wonder, will continue to inspire us, and as long as we keep questioning, exploring, and reaching for the stars, we can be certain that the journey will always be worth it.